We're actually live now. So hey everyone, great to be here. We're the watch party from Lausanne at EPFL. We've got about 30 people here in the room from EPFL, ETH, ENS in Lyon. We've got a visitor from India and a few other people from the region. We're about halfway through our morning, or almost through our morning, and we're going to do now a paper, performance isolation for 5G RAN slices across multiple interfering cells. It's by authors from UIUC and EPFL. So we'll play the talk, and then we'll have a brief discussion afterwards.
Everyone, my name is Temur, and today I'll be presenting our work, Performance Isolation for 5G RAN Slices across multiple interfering cells. This is work done in collaboration with my colleague Yongju, our collaborator Hetem, and my advisor Radhika. This work is motivated by how cellular networks are evolving. Operators aren't just running a single network, they're running multiple independent services on the same physical infrastructure. That's exactly what RAN slicing enables. So we'll start there. What RAN slicing basically means is that a single network operator, such as T-Mobile, can create logical partitions of its resources into multiple and allocate those resources to multiple independent slices. These slices can consist of application-based slices such as resource allocation, isolated slices for robotics or drone control, or they can also represent MVNOs such as Mint Mobile or Google Fi. Each of these slices can have their own set of users, and each of these slices can also have their own set of unique objectives based on which they allocate resources to their users and schedule their users. Another interesting question to ponder over is that given the ubiquitous popularity of cellular networks, what happens when demand spikes and we need more capacity? So in order to scale up the capacity of their deployments, what network operators usually do is that they augment the coverage of a macro cell, of a bigger cell, by deploying small cells within its own vicinity. And it is common practice for these small cells to operate on the same frequency as the macro cell to extract the maximum possible utility out of frequency spectrum, which is an extremely expensive and valuable resource. A consequence of this frequency reuse is that users who are in the overlapping regions between these cells tend to face interference and hence see deteriorated channel quality. In the past, people have looked at both of these problems in isolation. So people have looked at the problem of resource allocation for RAN slicing in single cell deployments, and people have also looked at the problem of multi-cell interference management without RAN slicing. The core thesis of our work is to be able to do both of these in conjunction. So essentially, how do we enable multi-objective RAN slicing? This is what our work, Radio Ninja, aims to do. Before diving into our work, let's start with some background. So in order to understand the challenge of our problems, let me tell you how each of these concepts are dealt with individually. First, we'll look at how resource allocation works in cellular networks and particularly in RAN slicing. So in cellular networks, how it works out is that you have a base station, which covers a physical area. The resources that I'm talking about are arranged in this time frequency grid. Each of these boxes represents a resource block, which is the smallest unit of allocation which can be done to a user. The y-axis represents the frequency subchannel, and the x-axis represents the time slot for which it is allocated, called the transmission time interval. So in RAN slicing, how these resources are distributed is that based on some pre-agreed SLA, the network operator, T-Mobile, will allocate a partition of its resources to slice 1 and another partition of its resources to slice 2. And then each of these slices can have the illusion that they're operating on isolated physical infrastructure, and they can both schedule their users based on their own independent objectives, such as maximum throughput or proportional fairness, and they can schedule their users accordingly. So that was RAN slicing, resource allocation for RAN slicing. The other part is that I want to basically how do these past works do interference management in the presence of multi-cell deployments. So how interference works out in multi-cell deployments is that we have a cell operating on a certain frequency. We augment its capacity by deploying a small cell nearby. We have a set of users, and all of these users are scheduled on the base stations that they're connected to. Now, given the fact that they're operating on the same frequency, a user which lies in the overlapping region between the two cells can face interference. So in this case, U1 is interference prone. A common which leads to a deteriorated channel quality for this user U1. A common strategy for mitigating the impact of this interference is to mute the interfering cell, in this case cell 1, on the frequency, the resource block that it is causing interference on. So in this case, cell 1 is muted on the first resource block, which leads to improved channel quality for U1 at cell 2. So given by taking this muting decision, we have a benefit, which is improved channel quality for U1, and we have a cost, which is that we have one less resource block at cell 1, and therefore user U2 does not get scheduled. So how do we reason about this muting decision? Essentially, we're benefiting one user and we're harming another user. So how do we compare this benefit versus cost across different users? And when is it acceptable to hinder one user to help out another? So in a non-slicing scenario where a single operator owns the entire infrastructure and all of its users belong to that same operator, an operator can have an objective such as maximizing throughput. So it can translate this lost resource block into some sort of throughput objective. For example, one less resource block means one less Mbps of throughput, and the improved channel quality means 4 Mbps gain in throughput. So as long as the benefit is greater than the cost, the operator decides to go ahead with the muting decision. But let's see how slicing complicates this. So instead of having a single slice with a single objective, now we have two independent slices, essentially two independent entities, each of them wanting performance isolation, and each of them working with a different objective. The problem is that different slices require performance isolation, but they're scheduled on the same resource block. If we go by the same technique that we used in the prior example where we only had a single objective, this is how the allocation would end up. We will improve the channel quality for U1 at the expense of not scheduling U2. But is that fair? Because essentially what we're doing is that we are improving the channel quality for U1, which belongs to the green slice, at the expense of U2, which belongs to the orange slice. So essentially, we're benefiting the green slice at the expense of the orange slice. And this violates the core promise of RAN slicing, which is to provide performance isolation. So how do we justify this choice? And moreover, even if we were to put performance isolation aside for a second, how do we even evaluate the utility of this decision across different metrics? So the orange slice thinks in terms of maximizing throughput, while for the green slice, the currency is proportional fairness, which is basically maximizing the sum of log of throughput. So these are two completely incomparable objectives. How do we even evaluate this decision across these different objectives? So a simple naive solution which comes to mind is that the core problem is that we have a slice mismatch on the same frequency, which complicates things. How about we allocate the same resource block to the same slice across all the cells? So we update the allocation this way. So now we have the orange slice allocated on both the resource blocks, and we can simply take decisions maximizing the slice's objective while ensuring performance isolation. But there's a slight hiccup with that, which is related to the channel quality variation in wireless networks. So in wireless networks, different users, based on channel propagation characteristics, can have different utility associated with different resources. So I'll illustrate this through a quick example. So we can have a channel quality agnostic allocation where U3 and U1 are scheduled. U3 is scheduled on resource 1 and U1 is scheduled on resource 2. And this is the amount of data rate that they can achieve. And if we were to simply swap the allocations for the same users on those two frequencies, both of those users can do better. Everybody wins simply by being channel quality aware. which channel is best for which user. Past work has shown that channel quality aware allocation can result in up to 72% higher throughput. So this means that this naive approach of just chaining the same frequency to the same slice across all the cells can lead to extreme underutilization of the frequency spectrum. So we cannot do this. This brings us back to our original problem, that how do we perform interference management while ensuring performance isolation between slices and enabling channel quality aware resource allocation. So in our work, we observe that the main idea, the one key thing, is that we should do fine-grained accountability of a muted resource. What we mean by that is that instead of thinking of a muted resource as a wasted resource, we count the muted resource as a resource consumed by the benefiting slice and deduct from its share at the muted cell. So in this case, cell the green slice benefits at cell 2. Its user U1 has improved channel quality. So slice 2's share at cell 1 is reduced. So essentially, U4 will not get scheduled and U2 still gets scheduled. So what's happening over here now is that the green slice makes a decision to improve the channel quality of one of its users on another base station while sacrificing one of its own other users. And this ensures that performance isolation is maintained. So it seems like we have boiled down the problem of muting to simply if the benefit of muting is greater than the cost of muting, we go ahead with the muting decision. But in our work, we learned that evaluating either side of this inequality comes up with its own share of challenges. How do we evaluate benefit and how do we evaluate cost? I'll briefly go through over the challenges that we face and we solve, and you can find the more details of it in the paper. So firstly, simply looking at improved channel quality as the benefit is wrong. Benefit is actually counterfactual. What I mean by that is that we need to know which users would have been scheduled without muting and which users would have been scheduled with muting in order to truly assess the delta created by muting. Secondly, true benefit, in order to accurately, so a muting decision creates a ripple effect across all of the future allocations. So in order to accurately assess the true benefit of muting, we need to constantly rerun the scheduler after every muting decision, which is prohibitively expensive given the sub-millisecond time bounds that we have. So in order to circumvent this, we come up with a fast heuristic to estimate the benefit from score deltas under the hypothesis of muting. As far as the challenges in calculating the cost are concerned, one thing that we do for fairness is that when multiple slices benefit from a single muting decision, the cost of muting is shared amongst all the benefiting slices. But this creates a chicken and egg cost attribution problem. Cost is split between the k benefiting slices, but after finding out the value of the cost, which was derived by 1 over k, one of the k slices might back out. Since this updates the fraction 1 over k, all of the k slices then reevaluate their cost benefit analysis again, and this cycle could go on. And lastly, in order to accurately assess this cost as well, we once again have to rerun the scheduler, which is prohibitively expensive. And in order to circumvent that, we come up with this idea of a reference schedule where we run a schedule once. We estimate the utility per resource block for a given slice, and we use that to approximate decisions in our system. For evaluation, we do trace-driven evaluations using real-world cellular traces that we collect with up to 5 cells, 250 users, and 12 slices. Our baseline is Radio Saber, which is a channel quality aware scheduler without any interference management. We compare against two different schemes. One is single objective muting, which optimizes for one global metric across all slices, agnostic of the individual slice level objectives, and thus it violates slice level isolation and per slice objectives. And secondly, RSEP, which allocates the same set of frequency resources across all the cells similar to the naive solution that we discussed. So it loses out on the channel quality awareness aspect. The key result that we find is that Radio Ninja provides significant improvements while preserving slice level isolation and ensuring that no slice is worse off. So over here, we can see that with single objective muting, the throughput slice, the single objective muting with maximizing for throughput hurts the fairness slices, The one maximizing for proportional fairness hurts the throughput slices. Channel quality unaware allocation simply leads to an underutilized spectrum, while Radio Ninja consistently outperforms all of the other baselines, resulting in significant improvements for all the slices involved. So in conclusion, we identify a fundamental challenge in enabling future 5G deployments, which is how to enable multi-objective interference management for RAN slicing. We deal with two key challenges. First is ensuring performance isolation across slices, and secondly, reconciling slices with conflicting objectives. We do this by doing a per slice cost-benefit trade-off without any aggregation across slices. The third challenge is to enable all of this in extremely tight sub-millisecond time bounds, and we utilize heuristics to approximate cost and benefit. And we observe that Radio Ninja provides 20 to 60% improvement in corresponding slice level objectives while ensuring performance isolation. Thank you.
Hello, everyone. Thank you for joining.
Okay. Our camera's not so good, but we're now going to have some discussion of this paper. We're fortunate to have at least one of the authors in the audience. I think what we'll do in the room is, if you have a short comment or question, I'll just relay it. If it's a long answer, like I think you might want to come up if we ask you a question, maybe come up close to the mic because it's not going to carry all the way through the room.
I have a question with respect to MIMO. Most modern systems they have MIMO capacity, and then with MIMO the situation changes. Because, you can have a higher utilization of the resource blocks because it depends on the activity of MIMO setting. So my question is, how do you combine this approach, or how do you extend this approach to take into account MIMO, which changes the picture significantly?
Okay, so just to relay the question, most modern wireless systems are based on MIMO, and MIMO has more nuanced ways of managing these kinds of resources. So the question is sort of how do these techniques comport with MIMO? Is that fair? Do you want to come up? So we're lucky to have Haitham here, who's one of the senior authors on this work. My mic symbol is on. I think we're good. Yep. I think we're good.
That's something else. The vMix.
Yeah, that's the mixer people.
Oh, okay. Okay.
We can double check because I don't want to create a feedback loop.
No. That's fine. So I think MIMO creates another axis of which complicates the problem further. I mean, one way to look at it is just kind of how much MIMO would improve the channel. It becomes much harder when you think of multi-user MIMO, where you can serve multiple users on the same block. So the way I would think about it is just another axis that you can look at in terms of like channel and kind of how many users, but it does complicate the problem even further. If we think of MIMO just as to improve the capacity of one user, then we can think of it as the same way we think of how much channel this user gets on this resource block. You think with MIMO, how much would it get? But if we think of multi-user, then it's a very complicated. It becomes very complicated. Yeah, this is my.
This is it represents why but my question, why is just what's the the burn off source blocks for there because they
So
Repeat the question.
Oh, sorry. So the question is what is the time scale of kind of this? At what time scale does this take place, the muting of resources, and how often do operators kind of do this today? So I think my view is operators don't do it as much today, just because basically everything is based on throughput. So we still have less where we have a slice that requires, let's say, latency to be prioritized or reliability to be prioritized over throughput. And as long as throughput is kind of with MVNOs, throughput is kind of the most valuable kind of objective, then you can run it as kind of the way you do without kind of isolation. So in terms of like, is it complicated today? I'm not so sure, but there are kind of now we are seeing that more operators do provide slices for, let's say, emergency vehicles. Like here in Lausanne, Swisscom does have a separate slice for emergency, like ambulances, firefighters. And how do they operate it? I don't know, but I assume they just prioritize this slice over kind of other slice or dedicate resources to it. But it's a bit of a different problem just because like emergency vehicles are not like as available and as spread out as like cell phones. In terms of muting, so again, I don't know exact kind of implementations, but this is kind of in terms of interference management, this is an old problem when it comes without slicing. So there is muting is one option. There are other options that kind of people do in terms of joint transmissions, and but muting is kind of the simplest to implement just because you don't need to know kind of the channels. Oh, the time scale question of how often this happens. So I think basically, at least in what we've done, it has to happen in orders of, let's say, 100 milliseconds or something. Just you cannot do it faster because it becomes a lot of overhead. But you also want to be able to kind of track the channels as people move and as interference changes. So doing it faster becomes a large overhead. Doing it slower becomes working on less up-to-date information.
So maybe I'll ask the high level NINES question. I mean, NINES is this venue that's supposed to be about really charting, the future of networking and a little bit, kind of pointed further over the horizon. So I'm not a wireless person, but this paper has a bunch of kind of classic ideas about how we allocate resources, how we, deal with multiple objectives, how we come up with models for making those decisions, and then you actually built it and deployed it. Can you just comment a bit on sort of what you see the sort of future map is for this area and these next steps, and why you're excited about this?
I think, I mean, part of the reason I'm excited about it is because so far it's all, I mean, we've had work on kind of let's optimize things other than throughput, but
sorry, if we could mute Imperial for a few more minutes, we're just finishing up. Thank you.
So if my view is kind of the future is to have kind of this dedicated performance per kind of, let's say, application. So rather than build one cellular network that is going to satisfy all different applications, all different users, irrespective of what they're doing, having kind of a network that is sliced to kind of guarantee some demands based on the application or based on the users. I think this is what's kind of new in kind of, let's say, in cellular moving forward. And now like the idea has been there, but now it's being implemented. And so now we kind of face the challenges. Okay, how do you do this with interference? How you do this with load balancing? How you do this with so many different topics that, yes, these topics were studied, but the moment you introduce this idea that now you don't have an objective that is consistent across all users, suddenly the problem becomes much harder.
All right. Any last thoughts on this paper? Okay. Otherwise, I think we'll turn it over to Imperial a couple minutes early. So we're going to sign off for the next hour or so. I think there's a panel from London, and then we'll come back at 1 with some more papers and discussion and one live talk. All right. Thanks.
Hello? Can you hear us online? Nate? Amazing. Thank you so much. And you can see the chairs and everything. So if people sit here, they're visible. Perfect. Okay. Yes, we'll bring people in and we'll start in a moment.
Fantastic. All right. Thanks, everyone. Thanks also for your patience as we worked out some of the issue. And welcome to this second session of the NINES pod at Imperial. So what we thought for this session is to have a panel with representatives from both industry and academia in really trying to share some of their insights, how they see this big AI revolution changing the way in which we build systems, in which we build network, also trying to distinguish between what is fundamental and what is just marketing and hype and so on. So we assemble a dream team set of speakers. So first of all, we have Mark Handley, which I don't think you need many introduction, but maybe I'll just can do. So Mark Handley is a leading figure in the networking community. He has done so many things that I'm not even gonna start to mention. I'm gonna mention just one that was recently. So he was the key designer behind the NDP protocol, was a new congestion control protocol. He won the SICOM Best Paper Award in 2017. I believe, and also he won the Best Presentation Award, or if not, he won my Best Presentation Award. It's actually on YouTube, and I recommend watching it. And this was really influential, both in the academic settings, because it really changed the way in which people think about congestion control, especially on the receiver-driven side, but also in the industrial setting, because this was one of the key pillars that led to the new congestion control in the Ultra Ethernet Consortium. And then Mark is a professor at UCL, but then also as part of this, he joined Broadcom. And more recently, like 1 year ago, 2 years ago, yeah, he joined OpenAI, which probably, again, some of you may have heard about, and designing the network. Then we have Dushyant, who is a researcher, as a senior principal researcher in Microsoft Research in Cambridge. Again, he has done lots of things across storage, compute, and network. And specifically in this talk, he will talk more about some of the new hardwares that we are seeing coming up in the industry, and again how this can also change some of the way in which we do design systems, and some of the challenges and opportunities for researchers. Then we have Marwan Faid from Cloudflare. Again, also mixed background between academia. He was first a professor at St. Andrews, and then he joined Cloudflare like 2 years ago, I think 6 years ago. Wow, a long time. Which again will provide, I think it complements really well, because it provides a perspective from what's happened outside data center. And so some of the long haul connectivity, some of the content delivery network issue. Then as you see here, there were 4 chairs, because the first speaker was supposed to be Professor Nick McEwan. Again, very well-known figure in the networking community. Professor at Stanford, who is currently in the UK for a sabbatical at Oxford. Among many things, it was at the start of the revolution for software-defined network and the Tofino switch. Unfortunately, he couldn't be here today due to a last-minute emergency. But I want to leave the chair here, because I think you are going to be the last speaker. So I really would like, so what we are going to do after this, I just invented on the fly. No, so what we're going to do is that after the 3 talks, we are going to do a panel with the 3 speakers and you. And I really would like to take this as an opportunity to really have discussion. I think, sometimes, we hear a lot of great talk, but, there is not much time of interaction. I think one of the reasons why there was a pod at Imperial was really to stimulate the discussion and engagement between students, professors, representatives from industry. So please, let's really take this opportunity to really have, a discussion about, I have a few questions just to warm up the audience, but then, I really expect from you guys to have tough question, all of this, they have a tough skin, so I'm sure they can take, the hard question, and really to ask, what you have the opportunity to have, representatives from industry and university, and really ask them, what you really are passionate about, maybe something that you are concerned about, something that you're really hopeful about, and so really let's make it fun. Okay, I spoke for too long, so Mark, over to you.
Hi, so I want to talk about building big dumb networks. And I really would like to tell you exactly what OpenAI is doing, and my management are okay with that. But the first rule of NDAs is you don't talk about the NDA. So currently we're still under NDAs to various people that I can't talk about. And so what I'll talk about is hypothetically what one might build if one were so inclined to do so, and you can read between the lines. So this is one of our supercomputers that we're building. This one is in Abilene, Texas, and you get some kind of idea of the scale. These are 2 buildings full of GPUs, and you can see they're building more. There will be 8 on this site by the mid this year. these first two buildings are fully operational and we're running stuff in them right now. And so what I'm talking about might conceivably relate to what we're doing in those buildings if I wasn't under NDA. Okay, so what I want to do is give you basically a very high level design sort of flow through of what I'm concerned about when I'm thinking about the whole thing when it comes to networking for AI training. And so why is this hard? First thing is just the scale. I mean, you've seen the size of these buildings. You can infer what's going on inside them in terms of number of GPUs and things like that. The second thing that makes it hard is the nature of the job. At least for pre-training, it's a synchronized computation. You need every single GPU to go in lockstep, and you're talking about things that fill two of those buildings in a single computation. That's difficult. To do that, we need a huge amount of bandwidth between the GPUs, and the only way to do that is to build massively parallel networks. You've got many paths through the network. The individual links we're using, this is all 800 gigabits per second now for scale out, 7.2 terabits for scale up per GPU. And that's very high speed. So you're not going to talk about software stacks. This is all hardware networking. It's all got to be RDMA or things of that form. You simply can't do this in a software stack. And then at this kind of scale,
some complaints about the sound. So if you want to use this one, if you want to stand here, there is already a mic. If you want to use this one, you can move a bit further out. So you
see if I can get to a check. Okay, that one's not working now. Now, can people still hear me? If people can still hear me, then we're good. Is that a yes or a no? Okay. Oh well. I will continue. We can plug that mic back in if necessary. Are we good? Or obviously not.
give it a try.
Okay.
Some positive feedback.
Some positive feedback. Okay. Hopefully it's better. We were probably picking up both mics. The other thing is at that kind of scale, when you're looking at, I'll pull a number out of the air, 100,000 GPUs in a building. Not exactly 100,000, but you can round up or down by a few billion here, a few billion there. Just pretty soon you're talking real money, but rough those sort of numbers. You've got continuous failures happening. So we're basically trying to design this stuff so that it does a synchronous computation across order 100,000 GPUs, and stuff is failing all the time. And so that last one, stuff failing all the time, actually in the end dominates everything. You've got to design for things that are continuously failing. And if you don't do that, your performance ends up basically being pulled down to nothing. So we're not worried about the odd 1% on congestion control or things like that. We really care about, can we build something with synchronous computation on a network of stuff where things are always in the process of failing. When it comes to the actual problems of scale, the reason why we're doing these really big computations is because there's basically way too many parameters to hold in one GPU and way too much data. And so we need to split a single computation across at least tens of thousands of GPUs. These are the numbers from Llama. I can't publish our numbers, but their numbers are public. So you get an idea of the amount of data and the amount of parameters, and all of this data has to meet all of those parameters. So you can sort of do the back of the envelope numbers, so maths you need to do. It's a lot of maths. So how do you do this? You basically parallelize the job, and there's different forms of parallelism. Tensor parallelism, where you split a matrix across multiple GPUs and do a single matrix operation on multiple GPUs. We have pipeline parallelism, where the different steps of the transformer are pipelined across different GPUs, and so obviously have communication between them. We have data parallelism, as in you train one set of GPUs on one set of data, another set of GPUs on another set of data, and very frequently synchronize between them. And then, because this results in models that are basically too big to be able to afford to actually do inference on, more recently, everybody's doing a mixture of experts where you do a slightly sparser training. Not all of the data meets all of the GPUs, but how you do that adds some complexity too. So that's what we're doing. We're parallelizing stuff across all these GPUs. But what does the network look like? The communication is organized into what's known as collectives. If you hang out in AI circles, it's the only thing you think about. If you don't hang out in AI circles, the term never comes up anywhere else in the world. But basically, these collectives fall into a number of really well-known communication patterns. There's OR gather, where you're putting data together. There's OR reduce, where you're basically adding the parameters. You're trying to be average, really. There's reduce scatter, where you're averaging the parameters of a particular value, and you want the result to only end up at one GPU at the end, because we're trying to actually distribute the results for that round. All-to-all comes with a mixture of experts. These are really common patterns. And these are normally implemented in collective libraries, such as Nickel from NVIDIA, and all the main companies have their own. So this is a synchronous computation. The downside of that is the start of each communication round is exactly synchronized. You couldn't come up with a worse traffic pattern for a network. None of this stat muxing stuff works. So you have to cope with everything starts simultaneously, and everybody wants to go at full speed. That's really bad for the network. And then, because it's synchronous computation, if a single transfer goes slow, the whole thing pulls down. So you don't care about the mean throughput or anything like that. You care about the 100th percentile, nothing else, which makes it, again, a very hard problem to solve, especially in the presence of tons of failures. So just so I get an idea, this is a reduced scatter running on a hypercube. And what we're doing is we're basically averaging pairs of parameters, one round, then the next round, and then the next round. And it just gives you an idea of sort of the nature of the traffic patterns you're running. Reduced scatter on a hypercube is not something we're currently running in production, but it is something we've run in production in the past. Different companies will have different ways of doing this particular thing. But this is the sort of communication pattern that we're looking at, of course, but you need to scale it a lot bigger. So you can imagine if any one of these small transfers goes slow, everything else depends on it. And so everything goes slow, and you pull that whole job step down. And so we're really trying to optimize that very last transfer. The 100th percentile is the only thing that matters. Now, the thing that's really expensive is not the network. The thing that's really expensive is the GPUs. So we're trying to make sure that the GPUs are 100% occupied in terms of the amount of computation they can do. Nobody ever succeeds. People make big stories about how well they do, but actually nobody gets close. But the reality is you can do semi-close. And the way you do this is by various different techniques. You can interleave the processing of different parts of the data. And then so the computation of one part is interleaved with the communication from another part. You can get close by making sure that you can really optimize that transport protocol. So we get really try to pull in the tail end of what can cause a transfer to go slow. That's difficult to do traditionally. We're doing some techniques which actually work pretty well on that front. And then you can also be doing multiple collectives at the same time. That will inevitably happen in 3D communication. So you've got multiple communication patterns overlaid onto the same network, not just one collective running at once. Okay, so let's talk next about what topology we build. We're doing nothing fancy. Ideally, what you'll want is to allow full line rate between any pair of GPUs. And the reason you want to do that is because you don't really know in advance exactly which GPUs are going to run which part of the computation. I mean, you sort of do. You scatter them across the network, but because those various different nodes failed in various different places, you have to place them onto the network to place around. And you don't get arbitrary choice as to where you place stuff, because we have not only the scale out network, which is what I'm talking about, but the scale up network, which in NVIDIA's case is NVLink. And so we have 72 GPUs in a rack connected, each of them at 7.2 terabits per second. That's the scale up network. And so we want a chunk of those to be able to do the tensor parallelism and some other stuff. And so you have to place chunks of computation into racks. But then which rack runs which part of the overall thing varies. But we want to be able to, when something fails, we want to be able to, okay, we're going to move the stuff that was in that rack to a different rack and continue. And so that's the sort of problem that we're trying to solve. You don't want to have to optimize carefully on which things are placed where. And to do that, you basically want to have a network gives you enough capacity. But then things are always failing. These are the numbers from Meta when they were doing Llama 3. They were at 16,000 GPUs. It's a 2-month run. They were getting a failure about every 3 hours on average. Now, scale up the size of the network by an order of magnitude and extrapolate, and you get an idea of where the problem is. Things are always failing. Okay, so what are we building? We're going to do the normal thing. We're going to build a cross topology factory. That gives you full bisection bandwidth. So the good thing out here is your GPUs, as your Ethernet switches, and we build a network with the same capacity each layer, which means there aren't any bottlenecks except at the receiver. So we don't really have to solve any internal congestion problems in this. So this is what we're building out of. This is the current Broadcom Tomahawk 5 chip. NVIDIA have their Spectrum 4 and Spectrum 5, which are basically similar specs. So you're looking at a 51 terabits per second switch. That's your building block for building these networks. That can give you 128 400 gigabit ports, or 64 800 gigabit ports, or 512 100 gigabit ports, depending on how you use it. So let's work on the assumption we're using it as a 400 gigabit network, because that's what NVIDIA's CX8 NICs are, and Broadcom's Thor 2, and so forth. So how big a network can we build? Let's say we start off with a 3-tier network and 400 gigabit per second NIC, and we want to build a full bisection bandwidth. You can basically do the maths. You've got 64 GPUs per tier 0 switch. The T0s have the same number of uplinks as downlinks, so that connects you to 64 tier 1s, which gives you 4K GPUs in a pod. And you keep doing the maths, and you end up and say, okay, great, we can build a big 3-tier network with full bisection bandwidth, so long as we're prepared to throw money at it. And we can get 500,000 GPUs in one network. No problem, we're done. And yeah, no problem, we're done. So you can build big enough. This is exactly what XAI did with their Colossus computer that they brought up end of 24, beginning of 25, that sort of time scale. With a 3-tier network, you're done. You don't have to do anything too smart. Now roll forward. Now we're on 800 gigabits per second NICs. Now what? Well, if you redo the same maths, you suddenly discover that we can only connect 64,000 GPUs. All we did was double the speed of the NIC, and now we're in trouble. We can't build a network that's large enough for what we want to build. So now we've got to do something different. And so what XAI did doesn't work for us. So you've got some choices. You can go to 4 tiers of network. Every tier you add adds power, adds switches, adds management overhead, adds things that will fail, cost you money, but most importantly, cost you latency. So we don't want to do that. You can oversubscribe the network, but now we've got a congestion control problem. We have to think about where things are placed, and we don't really want to do that. You can build a multi-rail architecture where not everything can talk to everything else, and that is indeed what most people do to some degree here. But you also have other choices. We'll come back to that question in a minute. Suppose we built a network, though. How are we going to route that network? The traditional thing everybody does is ECMP. So here we've got source and destination. You use BGP or some SDN or whatever to compute all the possible paths that are actually still working in your network, because remember, a whole bunch of these links have failed. And that will compute all the many possible paths. And when you send a flow through the network, the switch does a hash of the source and destination ports and addresses, and that determines which of the many possible paths in the ECMP set the packet goes out of. Great. So for a single rocky flow, RDMA over converged Ethernet flow, you take a single path through the network. No problem. Different flows take different paths, and you're all generally speaking okay. Except, of course, you're doing a random hash, and you get flow collisions, and you get flow collisions all the time, especially when we're trying to run these high-intensity synchronous workloads. You'll get a lot of flow collisions. And every time you get a 2-way flow collision, you're going at half speed. Every time you get a 3-way flow collision, you're going at a third speed, and so on. Remember, I only care about that very last, slowest flow. So I need no flow collisions to be able to get the performance of my network. And the chance of getting that out of ECMP is approximately 0. So people throw a lot of RDMA Q pairs at the problem to try and mitigate the issue, but you still never really mitigate the issue. You still get unlucky. And so you're basically dependent on being lucky all the time, and you never get lucky. So how do you solve this? So this is stuff which Paolo talked about our NDP paper, but this has made its way from NDP through into Ultra Ethernet and also into what we're doing. And so you do packet spraying. And so what you do instead is you change an entropy value that is in the packet. And the obvious one that's easy to change is the UDP source port. And we change that with every packet we send, which means every different packet of your flow takes a different path through the network, just based on the hashing. And this means that we no longer have this problem of big flow collisions. It's not perfectly evenly load balanced across the core of the network, but it's really pretty good. And so just this one change means that we've almost completely solved the load balancing problem. Not quite solved, I'll come back to that again, but almost solved in one go. The downside though, traditionally RDMA, which is the only thing you could usefully buy for Ethernet, required one path through the network. So you need to change the transport protocol. You need a transport protocol that is reorder tolerant, which means that when a packet arrives at the destination, the receiving NIC knows exactly where in memory to put it and transfers it to the right place in memory, no matter what order they arrive. And it also makes things somewhat harder from the point of view of doing congestion control and doing retransmissions, because you have difficulty figuring out which packets actually got lost because they're all arriving in a random order. So this adds some complexity, but it removes the load balancing problem from the network. And so my network got more stupid. And that's what I want. I want my network to be more stupid. I want to basically be able to not have to carefully manage how things go through this. This is a CDF of simulations of sprayed traffic through the network. There is still a tail on this graph. This ideally would be here at about 200-ish microseconds for this 2 megabyte transfer. We've got about a 20% cost. This is just a simulation if we're doing fairly naive spraying. But we brought it down from this with Rocky, which is where the end of the tail was with Rocky. So this by itself has got you most of the way to where you need to be. And there's some stuff we can do to pull that tail down a bit further. So this was all sort of academic papers a few years back. We did a startup got bought by Broadcom. Broadcom took the ideas and pushed them and formed an industry consortium called the Ultra Ethernet Consortium, which has spent the last 3 to 4 years standardizing this stuff, and the spec is finally out. And so you can actually go and read the 800 and something page spec, which talks about how modern Ethernet RDMA NICs can actually do these techniques. So it does packet spraying, it implements packet trimming, which is not something I've talked about, but within the NDP paper. This is now implemented in pretty much all modern Ethernet switches, so you can actually depend on it as a primitive. It does selective acknowledgement, it does out-of-order placements and congestion control and things like that. So this is where a lot of the industry has decided that they want to go. And you will very shortly be able to go out there and buy an Ultra Ethernet NIC. You can't quite yet. Actually, AMD might sell you one that's really close, but you can't quite go out there and buy a fully compliant Ultra Ethernet NIC. Now, I'm talking about Ultra Ethernet and not what we're doing, because I can't talk about what we're doing, but take this stuff and blur the edges. Okay, so now we've got a network protocol that can do out-of-order placement and things like that, and is designed for spraying. What can we do with it? Well, remember I said we couldn't build a big enough network? Well, can we get to 100,000 GPU plus in 2 tiers of network? Because if I can do that, I can pull the latencies down quite a bit. The answer is yes, and you can do it because our Tomahawk 5 switch can only support 64 ports at 400 gigabits per second, but it can do 512 ports at 100 gigabits per second. And if your building block is a really high radix switch, you can build small radius networks. And so if you do the maths, you can come up with, well, no problem. We can build 131,000 GPUs in a 2-tier network now, which is great, but only at 100 gigabits per second. I want 800. Well, no problem. I'm just going to build 8 of them. And I'll take my 800 gigabit per second NIC, map it out as 8 100 gigabit ports, and connect them to 8 parallel networks. Traditionally, that would have made no sense, because I couldn't sensibly map the workload onto that. But remember, I've got a transport protocol now that can spray across many paths. It can just as well spray across 8 parallel networks. It doesn't care. So I've got a transport protocol that can spray arbitrarily across different paths. It doesn't mind that actually the first hop of those paths is switched within the NIC as opposed to outside the NIC. It's the same. So now I can build an 800 gigabit per second network in 2 tiers with 8 planes. And actually, if I use multiple rails, I can go bigger than that. But this is simple. So we can build it. And we can build a high radix full bisection bandwidth network for the sort of scales that we actually need to be able to do. But if you then go and do the math and say, well, okay, how many links do we have? Well, for this hypothetical network, it's 1.6 million optical links in a single building. That's quite a lot. and 5,000 switches. Stuff's going to be failing all the time. Now, you would hope, you've got this lovely U-shaped curve you expect from hardware. You want to get down the U-shaped curve and then you're really happy at the bottom, except for the vast majority of the value of your building is the first part of the U, because that's when your GPUs are the newest and when they have most value. So you really have to be operating effectively on the top part of the U-shaped curve. So that's unfortunate, really. It just means we've got a lot of failures happening all the time. And as we send in people to fix the failures, they cause more failures and you're not fun. So unless you're designing stuff so that it works in a failed network all the time, you're in trouble. Now, I said before that we do traditionally BGP for routing. And BGP is great at finding paths. It scales really well. But what happens when things are failing all the time? Well, firstly, BGP is not very fast at reconverging. Maybe we can use an SDN to fix that problem, but it doesn't solve the whole problem. Consider what's going on with equal cost multipath. Your routing protocol, whatever it is computing many parallel paths to destinations. And so in the happy case, all of these uplinks can reach all destinations, except the ones that are directly connected. Great, we only need one ECMP set in our forwarding table. The problem is that I get one failure, and now we're no longer in the happy case. One downlink has failed, and now this switch actually has a different ECMP set for this pod than for everybody else. And now roll forward and assume we've got some failure rate. Let's pull some number out of the air. Let's say 5% of our links have failed. That pretty much means that for every pod, we've got a different ECMP set. And so now the size of the routing table is blowing up proportional to, it's not just the number of entries here, but also the number of destinations we're sending to. And you end up with a really, really large number of ECMP sets. You may or may not be able to get that in hardware, but keeping it up to date is hard. Not even sure we can get it in hardware. So the amount of state is basically the number of destinations times the number of failures, roughly. And the number of failures is approximately 1 per pod, so it's very large. So we're going to be in trouble if we do that. And it's slow to reconverge, and we're dependent on a complex control plane that we have limited insight into what's going on, and it's really hard to understand what's going on in these networks because the amount of instrumentation you can get out is way less than you would like. So this is our traditional solution. We do hash-based ECMP. BGP to give many paths, we do hashes. We're not going to do that. We're not going to do ECMP. We're not going to do any of this stuff. Remember I said this title of this is Big Dumb Networks? We're going to be more dumb than this. This is pretty dumb, but we're going to be more dumb. We're going to go for static routing. Okay, so I've got a network where things are failing all the time and I'm having to route around the failures, but I'm going to statically route the thing. We bring the network up and it will not change for years. How do we do it? We're going to do source routing. The NIC spraying across these many paths can actually have enough state to figure out which path each of them takes. It's not actually, if you do the routing in a sensible way, the amount of state you need in the NIC to do it is very small. You have to be a bit careful how you address stuff, but it's not much state. And so now we can have a network which is, it's entirely static. We bring the network up. If we fail the control plane sometime after it comes up, to find out what's failed. But you could, and it wouldn't matter. How do we do source routing? We use IPv6 segment routing, SRv6. So IPv6 addresses are very big. It turns out that actually that's useful. Not by the reason you think, but actually because you can embed a path into a single address. And so the way this works is you take an SRv6 address, there's a prefix there to identify which particular routing domain you're in, and then each of these things along the path is going to be the ID of a switch. They're not globally unique IDs, so they don't need to be very big. Your switch, when a packet comes in, matches on the first 48 bits. It goes, huh, that's me. I'm using 0. It's a match. The next thing I'm going to do is to take that address and shift everything to the left. So we modify the destination address in the switch, do a left shift, and now we do a lookup on the left 48 bits, and that gives us, via a static routing, that sends out the next path. And so as the packet goes through the network, the address shifts. And we're basically directly source routing, using a single IP address to get things through the network. It's a very simple mechanism. It turns out that it's available in pretty much every modern Ethernet switch. Although when we talked to the vendors, they said, oh, yes, we can do that. And what they meant was the hardware can in principle do that, but we didn't write the software stack yet. They have now, but you have to be careful what questions you ask of your hardware vendors. So how do I build a big, fast network? The answer is I use multiple planes and a low radix topology because I have low radius topology because I have high radix switches. Can do anything I want to do in the two-tier cross topology, at least for the next few years. Can use source routing, so every path through the network is entirely static. And then I use a smart NIC. I'm not talking about necessarily programmable NICs, although some of the ones we have support for are programmable. We have implementations of our protocol from multiple vendors who I would love to name but can't. And so that load balances the traffic by spraying it across many paths using source routing. It figures out which paths don't work and stops using them within a round trip time. So the failures we're handling really fast. One round trip time, the link fails, it's out of our set. Now, the network now is extremely stupid. I don't have different places that are all trying to adapt. I've got no dynamic routing over which we're doing another layer of dynamic routing in the end systems. The only routing that's happening is happening in the NIC. And that lets me manage this network in a way where I don't have to reason about what the switches do. I can send probes through my network and I know the path my probe takes to monitor whether the network is working is going to be exactly the same path that the transport protocol uses for the same label because it's all static, it never changes. Okay.
The reaction to failure is that you stop using the path. There's
The
no
only-
adaptation that happens.
The only reaction to failure is the transport protocol stops using the path. Now, we can do a map of which things have failed and optimize the startup of a queue pair so that we don't actually have to test those paths. But actually, right now, we're not doing that. But right now, we just bring up a queue pair, it fires a bunch of packets across path, figure out which ones work, and use the ones that still work. Really simple. We don't even need to have any complex control plane to make it work.
For a transient link flapping type situation, what's your signal for when it comes back to the path?
So there's,
When repeating the question.
okay, so the question is, if we have a transient link flapping situation, what's our signal for when we bring it back? So there's multiple nuances to that question. I'm trying to figure out what I actually should say. I can go into different levels. If the link goes down and stays down, we want to be able to report it to our provider to say, go fix it. If the link goes down and comes back up again, there's several different things. If the link flaps between the tier 0 and the tier 1 switches, basically I don't really care. I've got enough capacity, I have enough locality that I'm not congesting those links. If it goes down, I can be a bit conservative about it coming back up. So what the NIC will actually do is it will put it in the bad pool, and at some later point, it will send some probes on that path. And if the path has come back up, we'll say, okay, we're getting it back. That's on the short time scale. Now, the harder problem is what happens between the NIC and the tier 0 switch. Because if I've got a 4-plane network, I'm losing 25% of my capacity, and that means I'm dragging the job down. If I've got an 8-plane network, I only use an eighth of the capacity. I'm still dragging the job down a bit by that. So the question then is, there's some statistical analysis you need to do to figure out how long on average do my port flaps take? Therefore, how long do I wait using one fewer plane before I conclude that that node should be evicted from the job? And there's stuff there which I can't talk about. But if it's between tier 0 and tier 1, I honestly don't really care much. If it's between the NIC and the tier 0, I will eventually decide that I don't want to use that node and will remap to some other node. But there's a cost from doing that because I have to restart a part of the job. And so I don't want to do that too often. So I will wait a little while, conclude it's not coming back, and then decide to not use that node. Or I will, if it comes back up in that time period, then I'm back and we're happy. If it flaps a lot, I'll map it out and tell my provider it needs to be fixed. I don't want flapping links between tier 0 and tier 1. I don't really care if they flap between between NIC and tier 0. I don't really care if they're flapping tier 0 and tier 1. They'll get mapped out for the appropriate amount of time. But I don't need a control plane to do that, other than what the NIC senses by using the network. Anyway,
So, I do want to say this out loud. Just as a thought.
I can't believe I said this talk out loud.
So as a thought experiment, let's say BGP is not good enough. This is the other end of the extreme and exploiting about how much you can do. What if, is it possible you could do something like a on that path. Meaning you're exposing all the multiple paths, get the really fast payload, and our source right. That works here as a
So the observation is I need to spray to get the performance. Once I'm spraying to get the performance, the control plane is always going to be slower than the transport protocol. The transport protocol can detect a failure in a round trip time. The control plane is never going to be able to do that no matter what I do. The best possible control plane is going to be too slow. So I can map failures out faster in the transport protocol than any control plane could ever do it. So I don't gain from doing that. And I add a layer of complexity that I really don't want. It's much, much easier if the switch config never has to change. You know, we boot it on day one, and 4 years later, it's running the same config, the same routing table, nothing changes. That's much simpler if I can do it. And so I had to buy into some complexity in the NIC in order to make this stuff work in the first place. As soon as I've got the complexity in the NIC for other purposes, it means I can I don't want complexity in 2 places. I don't want complexity at all, but I certainly don't want it in 2 places. So I can take that complexity out of the switches and just leave what's left in the NIC, because I had to have it there anyway. So that's the sort of the philosophy. I don't think I would gain anything from having a better control plane.
Can you explain to us a little bit the cost of the dumbness, if there is any such cost? Are there parts of the network that are underutilized or?
Generally, no, because we can always bring stuff. You can always build a mapping protocol over the network and then tell the NICs which paths are down and which paths have come back up and things like that without them sensing it for themselves. It's easy to do a divide and conquer algorithm, especially when you've got source routing, so you can absolutely reliably map out paths with particular IDs. So it's very easy for us to build a fancy control plane on the top, but I don't want to have to depend on it. You know, so even if I don't do that, this stuff all works. The price I pay is it might take me a little bit longer to discover something has come back up. The other price I pay is actually interesting discussions with our providers about what they should do when things fail. You know, providers are very used to the idea of something failed, we're going to turn off BGP on that port and you won't use it. But actually, they don't get the option to do that because we don't get to change the routes. So we have this interesting interaction with our providers when they're actually in the process of fixing things and they're unplugging and plugging things, and we see links coming up and down all over the place. We get exposed to that because the switch is still up. So it adds some complexity from that point of view in terms of the relationship between us and the people who are doing the fixing of the actual physical links in the data center. Normally, you would want, the traditional way you do it is that link is turned off as far as the user is concerned. BGP routes around it. They get to the point where they're happy it's back up and now it's used. Our switches are still trying to fire packets into that link. So then we can actually put we can tell the NIC, by the way, don't use that path. So there's a bunch of complexity you might build on top of it to try and optimize that case. In the end, it doesn't really make that much difference because the NIC is so good at mapping out failed paths anyway. But you can optimize that if you care. You're talking about beyond cross topologies, or are you talking? So the general principle of if I want full bisection bandwidth, no matter what the workload looks like, I probably have to build something which has at least something like a cross topology. Once you've built something like a cross topology, it doesn't really matter whether the workload is synchronous or not. The nice thing about this is it works well for a synchronous network because I have enough bandwidth and I load balance the network perfectly that I don't cause issues with that synchronized workload. But it still works well for non-synchronized workloads. It's not the question really comes down to if the workload isn't synchronous, do I need full bisection bandwidth, or can I afford to build a cheaper network? The same spraying techniques and dumbness and things work even if you have congestion that can happen in the network, but you have to actually, you're then more reliant on the congestion control algorithm sensing that there's congestion and doing the right thing. Because it becomes harder if you get congestion in the network to tell the difference between congestion and something that's failed. We use packet trimming for that. So yeah, if we get congestion, we trim the packet, we get a knack back for that packet. So it's easy to tell which packets got lost due to something that was failed. which packets got lost due to congestion. If you don't have that, it becomes a little bit harder. But in general, all the same techniques apply even if you don't build a full bisection bandwidth, even if your workload is not synchronous, so long as you want something which has a very large number of parallel paths. And you're willing to put some smarts into the NIC. You know, if you have to buy into putting smarts into the NIC, then the rest of it sort of comes for free.
Question about this last flow completion slide. So let's imagine you have a full data information. Then there's going to be a bunch of flows that could also go. But wondering why you're only concerned about the last one, because it's not only the last one that would drag the whole operation down.
It's basically the slowest flow of the transfer. Yes, that's what I mean by the last. For any particular round, it's the last flow that's the problem. How are we doing on time anyway? Should we be moving on?
You want to wait and have all the questions at the end, or?
Yeah, no, but on the other hand, I also like
Yeah. You tell me when you shut up. I'm happy to answer questions until you.
Yeah. No, I think it's good. I think maybe if we're maybe trying to the next time maybe 10 minutes. That do you have more? Because I was thinking maybe if we finish in the next 10 minutes, then we can have solutions, and then we can go into panel.
Okay, I'm happy to answer questions as long as people want to ask them.
Yeah.
So you tell us when to stop.
Yeah. I guess do you have more slides?
No, I'm done on slides. That's it for slides.
So maybe if that's okay, maybe let's we'll go with your question. Let's ask specific question, then we can do some of the more general ones from the panel. That's okay.
Hey.
How many more GPUs can you fit? Like how much more?
The limiting factor ends up not being the network.
Do you mind repeat the
So
question? Because
the answer, the question I think, tell me if I got it wrong, was how big can you actually scale in terms of number of GPUs within one network? And it turns out it's not quite the right question. The limiting factor at the moment is not how many GPUs I can put in one network, but how much power I can supply to one building. We end up power limited before we end up network limited. And there's a certain scale, which I won't talk about, beyond which it's not reasonable to keep building bigger buildings, and you just have to build more buildings. And at that point, you've got a natural break between different networks. And so the question then is, do I want to then make those multiple buildings behave like one building? And at that point, you're buying into longer range optics, and there's more of a cost for linking buildings than there is doing within buildings. So you probably, at some point, don't build larger full bisection bandwidth. You build links between buildings where there are bottlenecks. But at a certain scale, it doesn't matter because there's always some locality. You can always arrange for reasonable locality at a certain scale. Well, each company has their own different secret sauce as to where that scale is. But right now, the number of GPUs I can fit in a single full bisection bandwidth fits within any building I can supply power to. That's the limiting factor.
is there any kind of scenario where you can't say you cannot always wait? Is there any limitation?
You need to. So the question is, are there any scenarios in which spraying isn't a good thing? That's the question. The thing about spraying is you pay a latency price for whichever packet arrives last. So spraying is not, there is inevitably some complexity to it. The NIC has a harder job figuring out what got lost. Packet trimming helps, but isn't a complete panacea because you do lose packets for other reasons sometimes. But if you can't keep the latencies down in your network, then because you're spraying across all paths, you will end up sampling the worst path. And so you will always have packets that are going across the worst path. So your goal is not to have any worst paths. That means that if you're going to spray, you probably want to spray everything. You probably don't want to mix in the sprayed and non-spray traffic in the same network. So otherwise, some of the paths will have more load on them and others, therefore some of the queues will be bigger, and your sprayed traffic will always sample the ones that have the biggest queues in addition to everything else. Now you can do some active load balancing to detect when that happens and say, actually, I don't really want to be on that path. And Odds-Free Ethernet does that. It uses ECN as a signal of the queue is too large on a particular path and we want to load balance off of that path. But in general, you are, by spraying, going to sample the worst case that you have to offer. And so you want to make sure that the worst case is really good, or completely failed, in which case I'll stop using it. But stuff in the middle where some paths have big queues, you want to avoid that at all costs, which means you either need some degree of active load balancing to detect when it happened to get off it, or just make sure it never happens in the first place. And it's actually easier to make sure it never happens in the first place, just by saying the backend network only does spray traffic.
Okay, should take maybe one last question and then.
Question about starter.
Mhm.
Given this network is the best kind of solution.
So from the network point of view, we try, you really need an external microphone here. The question is, what do we do about stragglers? The goal is not to produce them. Now, we don't succeed, but the goal is to produce them rarely. So the stragglers can be caused by network issues. They can be caused by GPU issues. There's all sorts of things. From a network point of view, the goal is to make sure the network is as evenly loaded as possible. The retransmissions, when we do lose the packets, are as fast as possible. If the retransmission is not in the last round trip time, it doesn't actually cost us latency. If the retransmission is in the last round trip time, it costs us latency and causes some straggler effect. So your goal is, as far as possible, to not have retransmissions, except maybe at the start. The ones at the start don't really have any great cost. The ones at the end have whatever the latency of getting that last retransmission through is. So from a network transfer point of view, the goal is not to create stragglers, or if you, and you do that by basically not having any loss except maybe at the start, which inevitably, if a link fails partway through a transfer, we will end up with a straggler affected by that link. But if it's just like one step, it's not a big deal. The links fail often, but they don't fail that often. That's something we worry too much about in that respect. The other problem with these things is you would think, oh, but at least the GPUs are deterministic. But it turns out that's not true either. Even the computation varies considerably between GPUs. Your two GPUs in the same node can vary by as much as 10% in terms of their performance. The GPUs are always running up against the power envelope. So the GPUs are always power throttling whenever you're doing a big workload. And so how they power throttle matters. And so you've got all these other effects going on as well that you really fight to keep even. I've seen various proposals for people saying they want to pre-schedule the whole network in an optical circuit switch network. Great, but you're going to have to hedge a lot against all these other sources of uncertainty. There's just too many sources of uncertainty that you can get away with tightly scheduling anything. So you have to factor in the fact that you will have stragglers at every layer in the stack, including the GPU. But you can minimize the effect. You can't never get rid of it. I showed you that CDF that had a tail. You can pull the tail down, but it's always going to be a tail.
So I would suggest maybe let's stop here with Mark, if I forgot to go to then we'll move to the next talk from Lucian, and then we will, have again Mark back in the panel.
Where? Yes. Okay. Oh.
Great. Thank you, Marius. Thanks, Mark. That was amazing. Hard act to follow, but I will try. I'll try to keep this short because I know there's the panel discussion, which I'm looking forward to, and I'm sure you are as well. I'm going to give you a little bit of a feel about how we're thinking about systems and networking research in our team that we're calling Future of AI Infrastructure here. You've got Paolo here, he's one of the senior members of our team. Hitesh couldn't be with us here today. It's a relatively small team, and so we're figuring out how do we pick the research problems that matter for Microsoft going forward. I think the first thing is there's lots of grounds for optimism in terms of systems research. right? I'm sure all of you have seen some variant of this graph before. Basically, the resource consumption of AI workloads is literally going up exponentially. I know people use the term exponentially a lot, but this is an exponential. And increasingly, it is the most important workload, at least speaking for Microsoft. And obviously, OpenAI, I'm sure, has a similar view. And what is driving this insane amount of resource consumption is it really seems to be true that those bigger models are unlocking those amazing new capabilities. Every day, I see new ones, right? I just tried out a Copilot thing yesterday, and it doesn't just write my code for me, it tells me how I should plan my coding. It's just absolutely amazing. Like every 6 months, there seems to be one of these step changes. But it all comes at the cost of this absolutely mad number of GPUs and insanely big networks. And so in a sense, that progress, relies on the scale and therefore also on the efficiency with which we run this hardware, because it is not cheap. It's not cheap in terms of megawatts. It's not cheap in terms of billions of dollars. The numbers are just staggering. And in a sense, from a researcher point of view, that's great for systems researchers because scale and efficiency are what we do, right? So there's lots of interesting problems to work on. Got to mention Moore's law at some point, so let's get it out of the way. It is ending. We can't rely on it anymore. And it's not just about compute. In fact, compute is, I would say, a lesser worry than, say, networking or memory bandwidth nowadays for AI. But across all of these, we are hitting various hardware scaling limits, right? So the transistors are not giving as they used to. And so what that means is we really need to think about across the stack. And AI workloads give us that opportunity. The workloads are different. They're so big that we can specialize the stacks for them. We can even specialize the hardware for them in some cases. And so across this, we're thinking, how do we co-design? What's the right set of research problems that are really going to unlock that scale and efficiency that we need? And something we believe, at least, is that this is sort of interdisciplinary. Because the sort of down the stack, we've got to think about new hardware that's coming, some of which we're working on. Paolo leads a hugely successful team working on optical networking, some of which our hardware partners might be working on. But also up the stack, at some point, these might involve changes to the models themselves. So this area of ML systems co-design is, I feel, it's a very active area, but still there's so much more to be explored there, right? And so that's what we're trying to do. And we're being distributed and interdisciplinary, not just in terms of discipline, but also actually we genuinely span MSR labs. You're seeing the sort of Cambridge side of things here. It is numerically the most of us, but we have collaborators across Microsoft, indeed, and in some cases with external partners. So that's kind of what we're trying to do. And everything I'm going to say here is you should view it as this is the start of our journey, right? This is something we've been doing for maybe a couple of years, if that. Right? I want to go back to this question of scale, and I, have some eye candy always helps, right? This is a photo from a Microsoft blog of one of our latest data centers. This is sort of one of our Fairwater data centers, right? And actually, the photo doesn't even capture all of it. You can see bits are cropped. And those wind turbine-looking things in the middle are just the cooling. Actually, they're just one part of the cooling, the air cooling part of this, right? It's insane. The thing is huge number of acres, prodigious number of megawatts that I wouldn't be allowed to tell you even if I knew how many, but it's a lot, right? It's crazy. Inside the data center, equally crazy, right? We pack so much hardware and so much power into each rack that it is becoming a problem. I'll come back to this in a bit, right? And so, there's all these apocalyptic headlines about we're melting the planet and so on and so forth. But quite apart from that, in a very real sense, this level of scale needs new solutions because we can't sustain it. Frankly, we can't keep building bigger, denser data centers. And like I said, there's only so much we can expect from the silicon, right? So NVIDIA and others are doing amazing things, but they're doing amazing things in terms of making essentially the chips bigger and more power hungry. And somehow, so far, it kind of works without melting, though the failure rates, as Mark alluded to, are very problematic. Right? Because turns out as you make the chips bigger rather than more power efficient, you get all these problems with yield, with manufacturing costs, and with the power and the thermals. Right? So this doesn't seem sustainable. We can't just rely on bigger GPUs. Right? Oh, I'm going backwards. And so in particular, right, one of the immediate challenges that we have is the so-called size of your package. So if you look inside one of these GPUs, it's really amazing, really state-of-the-art stuff. There's a reason that the amount of power consumption per GPU is going up in this crazy way from generation to generation of NVIDIA is because actually it is many, many chips on one giant thing called an interposer. And you add up the power of all of those and it's still in one very small packet and it has to be all cooled together, right? So that interposer, you can see a rough idea of scale. There's 2 full reticle compute dies in there on a Blackwell, right? And full reticle is about this big. It's already big, right? Then you surround it with a bunch of high bandwidth memory. I'll talk more about HBM, right? And all that is on this giant silicon chip. You package it, and then somehow you have to power it and cool it, right? So I've talked about how the hardware by itself, or at least the silicon by itself, isn't going to get us there. What is it that we can do? And one of the things we can do is look at what makes these workloads different and try to exploit that. And there's a lot that makes them different, right? So it's surprising that every time I think back to other distributed systems I built, you know, how much different these AI workloads are, right? The things we used to worry about, we no longer do, right? There's no pointer chasing. You know exactly what you're going to access. You might even know when you're going to access it, right? In a sense, it's embarrassingly parallel. So it should be easier, right? But there's other things that make it very hard, right? And the bandwidth, and I'll keep coming back to bandwidth, is one of them. Network bandwidth, which you've heard about from Mark, but also memory bandwidth, and I'll talk about that, right? And how do we deal with this insatiable hunger for bandwidth that these workloads have? So I'm going to talk about 2 things. One is sort of more about the network bandwidth side of things, and then the memory bandwidth side of things. There's also a third very interesting thing that we're pursuing in our team, which is very interesting, but possibly of less interest to systems and networking crowd, which is how do you program these things in the future, okay? So remember I showed you that graph about how the per GPU power is going up. This graph looks almost the same, but it's not the same graph because the y-axis is the per rack power. And now we're talking hundreds of kilowatts rather than individual kilowatts. I mean, all these numbers are kind of crazy, to be honest, right? Back when Microsoft started building data centers, we thought 15 kilowatts per rack was fantastic. And obviously, these things won't fit in that budget at all, right? And if you think about the consequences of having this very high rack power density, one of the immediate consequences is the cooling gets expensive, right? And so this is a photo of a Blackwell rack. And as far as I can tell, it didn't come labeled, so I'm guessing a little bit, but as far as I can tell, just that left-hand blue bit is the actual GPUs, right? The right hand seems to be mostly there so that we can cool the GPUs and get the heat out to the next level of heat exchange. I would argue that is not a great ratio, right? You've only got a third of it doing useful work, the rest of it is cooling, right? So we're already sort of in this regime where we're designing these things just so we can cool them. Not great, right? Why are people packing things with this insane rack density? It's not to save space. Okay, actually, we've got spare space because we're power limited, right? It is one of the very key reasons is because you need the bandwidth. So the scale-up network that NVIDIA provides within its racks, and which now scales to 72 GPUs at 7.2 terabits per GPU, needs short cables, right? Because it's copper, and copper at those bandwidths will not go more than a couple of meters, right? The scale-out network, the one that you heard a lot about from Mark, you can use optics, right? And you can go much further, right? But you pay for it in much lower bandwidth per GPU, right? So at this level, there's sort of heavy oversubscription, if that's how you want to think about it, right? And so breaking this trade-off, right, was itself a sort of huge research effort. You can ask Paolo lots more about it because he's the man who did it, or at least he runs the team who did it, right? Can we get sort of the reach of copper, but without all the, reach of optics, but without all the disadvantages that come with traditional optics, right? And so there's a SIGCOMM paper from last year. I'm just going to try and summarize it in one slide. Paolo, I apologize if I don't do it justice, right? The core concept is we have to move away from this idea that your link is a small number of very high-speed channels to a much more parallel setup where you have, 2 orders of magnitude more channels, but they each run at a much lower clock rate and a much lower signaling rate, therefore, right? So go look at the SICOM paper for more. But sort of, and there's other advantages to this, which is that you can make it cheap, which is really important, right? Use commodity technologies, get the power down, get the reliability up. Where I want to get to is it's not actually problem solved because we've sort of shifted where the long pole is. Because assuming you get this crazy amount of bandwidth and with the reach, and therefore your instinct is immediately to build a bigger, say, scale-up network, what about the switching? Right? Switches still consume a lot of power. And this is where it's funny that you just mentioned this, Mark. We're looking at whether this very old idea of circuit switching, optical switching, does it finally make sense? And hopefully to this crowd, I don't need to tell you about the differences between a packet switch and a circuit switch. But the basic observation here is that circuit switches are great for almost everything, right? They consume less power because they're passive. They don't need extra transceivers if you do optical to optical. Right? The cut-through latency, in case you care about it, is basically 0, speed of light. And at least the hardware we're seeing today, they're roughly on par on terms of port count with the state-of-the-art packet switches. Obviously, there's never a free lunch. You lose a lot of flexibility, right? At least the kind of circuit switches we're seeing out there today, you're going to pay the significant cost in reconfiguring your circuits. For example, if your workload shifts, or if your workload, even when it doesn't shift, maybe it doesn't have enough paths, and you need to reconfigure while you're executing. If there are failures, right? And so I'm going to stop there because that's kind of where we are today in the research. We don't know the answers to some of these questions. We are making good progress, but I think it's a very interesting area to look at. John.
So in all the AI scaling talks, I never hear anything related to the sort of demographics. So in the world, you have a certain number of people, they have a certain amount of disposable wealth, they have a certain amount of information they can produce and consume. They also have a certain amount of water and energy that are required to exist. So surely there's a scaling limit, which is really simply determined by supply and demand matching humans to AI. So this infinite growth curve makes no sense. Let me give you a data point. Recently, a housing project in East Anglia, north of Cambridge, was stopped because there's not enough electricity to supply the houses in the area to the minimum requirement for humans because it's all being used by data centers in the area. So there's an economic reality here which makes no sense. If you don't have people producing wealth and growth to use all this infrastructure, then you have no business case. But it's a fundamental one. We have one planet, right? So has anyone actually put that line on here? Because it should be pretty easy to work it out. You've got these really simple curves, which should show you where you're heading. We know what it costs. If you do town planning, you can go out and look it up, and your local council will tell you what you have to provide if you put a new factory here, a new school here, and a bunch of houses over here to actually make it livable for humans. Now, what's the match between those two things? Not just not just being environmental, just actually saying, well, actually, if there's no people, there's no economy, this makes no sense. And there's a minimum set of things that people need, just like the AI infrastructure, not just the AI, any data center infrastructure, or even just the production, fab for chips that you're talking about, some of those things, which we don't like having in Europe and North America because they pollute, but that is an environmental thing. But just the economics of this make, starting to look like nobody's done this very simple calculation.
Okay, I'll try to summarize the question. I might paraphrase a bit, John. I think the question is sort of, apart from the technological limits, what are the environmental and economic limits on this growth?
It is technological. There's, water, electricity,
indeed. It's a great question. I don't know the answer off the top of my head. We don't seem to have hit them yet clearly, but even without hitting those hard limits, it is imposing a huge cost, right? And that is something we need to be aware of. And I think the best answer we've got so far is to claw back efficiency at every level of the stack, right? Because the one thing we'd like not to do is to backpedal on the capabilities that these AIs offer. My hope, maybe I'm being overly optimistic, is when we get over this hump, these AI capabilities will eventually pay for themselves. And I think it's not a secret to say at the moment they do not. They do not from the point of view of our providers. So that's a pain point for us, Microsoft. But arguably they do not from the viewpoint of society as a whole. But I'm going to go out on a limb and say that's a hump we have to get over. And eventually these things will pay for themselves in terms of what they will unlock. It's a speculation. Sorry, Mark, you had a...
This is the sort of question we probably want to have.
In the panel, yes.
Supposed to
Thank
put you
you.
on the spot here.
Thank you.
So let's come back to that question later.
Thank you, Mark.
We're all sitting
Absolutely. Go on. It doesn't, yeah. Oh, sorry, go ahead, yes.
So maybe this intersects with Mark's talk as well, but I suppose we are both kind of structuring for example, the networking part and the hardware part on these AI workloads, right? But isn't this something that we've already seen and we just maybe moved from kind of like a distributed or like with different computational kind of requirements workloads to the new AI workloads. So we're going back to what we used to do before when everything was more analog and needed less reconfigurability, kind of.
Let's
Hopefully.
maybe keep it for
Okay,
the
sorry.
panel. It seems to be quite a broad question. Thank you. So let me just get through the last few, and then yeah, I just want to talk about memory because it's my pet peeve, right? Another graph which you've probably seen a variant of before. If you haven't, you should, which is the compute memory gap is widening. So I remember back when I was doing my PhD, we'd have all these computer architecture students, and they talk about this thing called the memory wall. And I just ignored it because I thought it's some ISCA stuff. And what do I care? But actually, I should care, and so should you. Because in terms of GPUs and AI workloads, that compute memory gap has widened by 10x in 12 years, right? And that's despite throwing all kinds of advanced technology at the memory end of things. It's just that the compute has been outstripping it, right? And there's lots of implications to that. So what are we throwing in technology-wise at the memory end? There's something called high bandwidth memory, right? And high bandwidth memory in the AI hardware tool today is kind of necessary evil. No one actually likes it, but they don't have anything better, right? And it's extremely advanced. I mean, it's amazing stuff, right? You make DRAM, and then you stack it vertically. You put this die underneath. You run thousands of these vertical channels called TSVs. Then you put that next to the GPU, like literally next to it, and there's a bigger chip called an interposer underneath, and it stitches them together with very many parallel channels, again, all to get the bandwidth, right? And the upshot of all this is it's really expensive and complex to manufacture, right? This is the most advanced fab technology there is, that TSMC can provide. But that does mean that it adds costs, it lowers reliability, the power and the thermals are always an issue. And the sad fact is, at least for some parts of the workload, it's still not enough bandwidth. We're still memory bound. This is crazy. So, what do we do about it? Can we do anything, right? And just to sort of reinforce this memory bound point, but also reinforce the point about the workload does have a range, I've got on the y-axis, on a log scale, right, how many effective teraflops you could get out of a Blackwell GPU for different computations that we do routinely. And I'm focusing mainly on inference here, which has been our research focus. So it's a little bit different from the training scenarios Mark was talking about. And what you'll see is at the left end, right, if you basically have a compute-heavy operation, life's good, right? You basically hit the orange bar, which is the maximum rated teraflops that a Blackwell can give you anyway. So you're keeping the compute fully utilized. That's fantastic. At the right end, you're under 1% utilization of compute. That Blackwell is not doing much for you because it is memory bound, right? So all those lovely tensor units and all that are just sitting there waiting for data, right? And there are some indications that this is getting worse, because in terms of unlocking these AI capabilities, what people seem to want to do is have longer context. That's very memory bound, accessing the context. Agentic workload, which makes the context even bigger than anything you or I could type in a reasonable time. Multimodal models, once we go to things like images and videos, the size of those contexts is going to blow up as well. So this is not a problem that's going away. And what's interesting is people are specializing but they're specializing for the compute end of that spectrum. So some of you might have heard of NVIDIA CPX. It's a very interesting design. At least one variant of the CPX tries to solve the problems of HBM by not having any, which sounds great, right? It's got tremendous compute, 4 times the compute of the Blackwell, at half the memory bandwidth because you got rid of this. So you've now widened that 10x gap by another 8x, right? So the right end of the spectrum is going to be even worse. It's not going to do anything for it, right? So kind of we also need to specialize for bandwidth is the takeaway we got from this, right? Because if you only improve one end of that spectrum, we all know Amdahl's law, that end is going to matter less and less, right? What is it that fundamentally limits bandwidth? It's very simple. This is where I should have listened to my ISCA friends, but now I read the papers. It is not about the memory itself. It's about moving the data between the memory and the compute and the energy cost of moving the data between the memory and the compute, right? So this is a little paper from NVIDIA and Stanford from a few years ago, and they show you that sort of path that it takes from a DRAM cell all the way to the edge of the GPU. And there's several bits, right? Across the DRAM die, down the TSVs, across the interposer, and so on and so forth. But the main thing I want you to take away is, of all that, only that top red bit, that's the picojoules for the actual memory. All the rest of it is moving it to the GPU, right? And there's fundamental physics reasons why if you want to move a bit by a certain distance, then it's going to cost you this many picojoules, right? And so that is fundamentally what is going to limit your bandwidth, right? Which is why, here's another old idea. I mentioned circuit switching. Here's another old idea, programming in memory or programming near memory, right? It's seeing a resurgence of interest because people have locked onto this fact that this is pretty much the only way to get around this physics of moving data over the distance is you shrink the distance, right? Move the compute closer to the memory. There's many ways to do this. I'll skip the details of exactly how the hardware works. You know, there's older ways, newer ways, etc. One of the very recent promising ways is to sort of leverage the structure of things like HBM itself, which do have a place we could slide some compute in at the bottom of that 3D stacking, which physically is a lot closer to the memory than the GPU can ever be, right? So that's very interesting, and we're looking at that. You're probably thinking, well, that's great if I design hardware. Where does the systems and networking part come in? Where that comes in is, how do you attach it to the rest of the system? So there are papers that claim you can run everything on such devices. I don't buy it, because then you'll swing it the other way. You'll become compute bound on the compute bound end of things, and you'll be probably just as inefficient. So we need a heterogeneous system. And when you build a heterogeneous system, then you need to interconnect these devices. And there's very interesting questions about how exactly do you interconnect them. Is it over the scale-out network? Is it a scale-up network? Is it a custom interconnect? Is it optical? We use circuit switching. What happens when things fail? All the networking questions, but in this new sort of setup, right? So that's very interesting, and that's something we'd like to look at. So what I want to finish on is this observation that actually AI is big enough and important enough that we can take chunks of this workload and we can specialize the hardware for it, right? So we can think about a future where you've got compute-optimized devices, bandwidth-optimized devices, but then you've got to connect them up somehow. Maybe a circuit switch, maybe some other kind of network. We're also looking at, you know, how does some of the optical technology we're looking at change this picture? You know, if we had really high bandwidth optics, would that make life easier? Could we be more disaggregated? New memory technologies, you know, do we need a capacity tier that still provides very high bandwidth, but can be cheap per gigabyte because HBM is not, right? And we're also looking out even further. This, I will be honest, that is much more sort of out there, science fiction sounding stuff, but we have teams looking at it in FAE, right? One is looking at 3D stacking of the optics on top of the compute or the memory. This is really interesting because it could unlock a lot of bandwidth, but it will also unlock a lot of challenges. And the other is, you know, changing the compute model altogether in order to analog optical computing. And we've got an ongoing project on that in Cambridge. Happy to talk about it more or find the right people for you. And so I'm just going to pause there. This justice space I covered, I've tried to keep it scoped, but even justice space, there's literally any number of papers about it. These are only the ones we've written in our little team, right? But my personal pitch to you guys, especially researchers just starting out, is if you're looking for a place for interesting workloads, interesting hard scale problems in sort of the systems and networking areas, AI workloads are really here to stay, right? They're not a fad, right? They are the workload of the next decade, at least, possibly more. And and they present very many challenges that we need this research community to sort of lean into.
Are we on? Okay. I think I'm gonna change directions. So I'm reusing a few old slides here, but I'm gonna hope to put a new spin on them. I think it would be a mistake. So one of the impressions that students might walk away with after today, seeing the first two talks, is the only problems that are worth solving are in the data center for AI. And I don't think either of the two presenters would actually make that claim. So I'm going to give you a slightly different perspective. The other spin I'm going to take is I'm not going to focus on Cloudflare specific problems. I want to take the perspective of, I've been an academic, that's where my heart lives. I've spent some time in industry, and if I'm walking back, what are the big observations that I would take away to sort of build upon? So at a high level, non-technical, I will say, I think, and please push back on me on this one, I think there are only two ways that work gets done in the world. And the first is they are problems that are driven by money, directly or indirectly. And I would argue a lot of the AI in the data center space fits in that class. But the other one is there's an individual or a collection of individuals who care enough about something to drive it through. Okay? And if you're trying to figure out how to move forward and problems to work on, probably you want to pick in one of these two camps, like something that you know actually has a measurable impact financially, directly or indirectly. John's question was related to that. Or it's something that you find particularly important and you're willing to care about it, damn the world and what they say. Okay? So most of this, I think, is in that second bucket, but actually does matter. Mark said something really lovely, and I wish more people said this. The innovation of the internet is not packet forwarding, it's statistical multiplexing. One of the nice things about being in the data center, I think the nice observation is you can actually do away with that. There's a lot of homogeneity that you get. Doesn't exist, of course, on the open internet. So let's just acknowledge that. The other thing, which kind of is in opposition to that idea, is in a modern internet, to anyone who operates pieces of the internet, it turns out packets are incidental. No one cares. There's no money ascribed to them. You can't actually allocate resources to a packet. The unit of granularity that people want to think about are the connections. Okay? The connections are the first-class citizen, as it were. And the last piece is, I want the network to be dumb too. I think this talk is going to end up being there's a tension between what we want the network to be as a technical community and what people want from the network. But fundamentally, I think a lot of it is going to reduce to how we do versions of authentication and identity. So when I walk around Cloudflare to the NetOps people and the systems ops people and I say, hey, I'm about to give a talk, have I covered all the bases correctly? And the first time I asked the question, they said, well, yeah, except you're missing layer 8. I'm like, layer 8? What do you mean layer 8? You mean human beings? And they said, yeah, let's be honest. Like the biggest sources of tension on the open internet relate to human beings. So let's talk a little bit about those. The first is, what is the role of transparency or visibility? Okay, there is increasingly less and less visibility about what happens in the open internet. And that is naturally going to be a problem for societies that increasingly rely on an open internet. They want to understand what it's doing, what's happening to the things that they transmit, how they might be able to change or control or not control. That level of visibility is bit by bit disappearing. In fact, there's enough anecdotal data to say ICMP is increasingly disappearing from networks around the world. If you don't originate an ICMP packet from within the network, you're not going to get a response. And that's really the only tool that we have. So one problem to think about is how can we increase transparency and visibility on the open internet? The second, and honestly, from my perspective, this is the single biggest threat to the internet that we love, is regional requirements. The yes in my backyard phenomenon. So whole NIMBYs, we live in the UK, the not in my backyard. Turns out there's an opposite force called yes in my backyard. It's incredibly powerful. There is no bigger threat to the internet breaking up than that. And the solution is, I love the Microsofts and the Googles of the world. They have tons of money. Their solution is to just build in region, which is something most people can't afford to do. We probably don't want to change the face of the planet to do it. Oh, and by the way, what would have happened if they'd all built their data centers in England instead of Ireland for tax breaks, and they did this pre-Brexit? All of those millions of dollars would be down the toilet. Okay, so it's not a good solution. There needs to be something better. In fact, the way we think about the internet, I think, needs to change. So what are the primitives that allow data to flow freely anywhere and still give people confidence and guarantees about how the data is being handled and who can access it? Somebody mentioned trusted execution environments being a hammer. Maybe it's a suitable tool in this case. It won't be a panacea by any stretch of the imagination. There's different versions of this, like the pizza problem. They're actually user-driven. Anybody heard of the pizza problem? I'll do this very quickly because you'll find this interesting. Okay, Private Relay is if you subscribe to iCloud Private Relay, you get this for free. And the problem is the only way that we have in the world to geolocate where you are is by your IP address. Except all the Private Relay traffic now exits out of IP addresses belonging to either Cloudflare, Akamai, or Fastly. So if you're in Manchester and you pull out your phone and you say, please show me the pizza places near me, wherever Cloudflare's data center or Fastly's data center or Akamai's data center is where you're going to see the pizza places. And that is a real problem. And they solve it with a dumb solution by manually assigning locations to IP addresses and then publishing a list of these mappings so that other operators can use them. That can't be the way forward. There has to be something better. The last one, these two hourglasses are something that are going to be familiar to many in the room. The protocol stack, the narrow waist is the internet protocol, end-to-end protocols above, point-to-point below. As long as you speak IP, you're golden. Some years later, we realized networked applications, really, HTTP is the narrow waist, similar sorts of reasons. I'm going to claim now there's a third waist that's emerging, and it's worth thinking about, and that is the infrastructure services stack. I'm happy to entertain better names, but basically the open internet and private devices, privately managed devices on the open internet up top, and then backend services and private infrastructure on the bottom. And there are a bunch of things that all of these people on the bottom require, but shouldn't have to implement themselves. So you're talking about your cache, your DOS protections, your firewalls, your zero trust, and the list goes on, software-defined wide area networking, and the list goes on and on. The trick here is this is not a technical or a protocol stack, right? There's a lot of businesses that operate in this space. And I think one of the things that would be lovely is if there were good ways to interoperate. So I can wake up one day and say, hey, today I want to use this organization, tomorrow I want to use the next one. And I should be able to just flip switches to do this. Last one, I honestly don't know much to say about it, but it's something that's occupied my mind the last couple of weeks, and it's botnets and compromised devices. So over the Christmas holidays, I know Cloudflare published a blog about this. There was a mammoth attack. I think that has scared everybody. And the rate of growth of these things, as more people in the world have more money and buy more cheap devices that have no incentive to update their software, this is going to be a problem. And I don't know what the solution is, but it's worth thinking about. And that's it. Good? Nice and short?
Any question for Well, should we just move to the panel? I think maybe let's just move to the panel. And actually, I think you touched on many of the points that, will also make for a good panel discussion. So I think that was great. So can I invite the speakers to join the panel session? And I would say, I think we have already two good questions that came out during the discussion. And maybe we can start with that. And then we'll see where it goes. John, don't leave now, because actually you are the first. Well, I think we just defer to the panel, because I think your question deserve probably like broader set of answers. Mark, do you want maybe to take that one? Sorry to put you on the spot.
Try. I'm trying to remember what the question is. So your question basically, I think, is there not just naturally a point at which we don't need to build more stuff?
Actually, no, it's a bigger picture. Okay, so it's just a resource balancing thing between different demands. So you have demand for electricity and water for data center, you have demand for electricity and water from humans, and then these are not independent, right? So if you displace humans, you have no business because you don't have any customers. So at some point you have to relate these demands, and there is a cap on the total amount of electricity we can generate on the surface of Earth in terms of various, limitations of where you get the input from, solar, wind, nuclear, whatever. And there's who gets first call, who gets second call? Well, that's based on matching. So the question is, has anyone actually done the numbers on that properly? And there's a sort of geography of it. Then you have to do it, by taking 16 square kilometer areas of the whole surface of Earth and see. And that also gives you another limit, which is how far away you are from any data center, or what's your latency and other things, or how far away you are from a food supply. They're kind of related. So it's like, where do we hit? I mean, what you said is also a reasonable question to ask as well.
Yeah. First of all, I don't know why everybody fixates on water. I mean, we don't use any water in any of our supercomputers. It's all closed loop cooling. So there's literally no water consumption. But power is the real problem. And that's the one people ought to be talking about, and it really matters. So I think that if you look at the exponentials that you talk about and so forth, there's multiple exponentials that are going on simultaneously. And one, so number of transistors and things like that, eventually that caps out, and you just have to produce more transistors. If you look at the power consumption of all of these things, we all know that nothing is ever an exponential curve forever. Everything is always a logistics curve. And the question is, where does it move from going up to leveling out? And that's always true for everything that was on an exponential. So the question then comes at what point do the economics not work? Because power costs money. Yeah, irrespective of what it costs and any other cost, it costs money. And unless the money is flowing, the electricity won't come. So eventually, the likely story is, right now we're in this strange place where we're spending money we don't have, or rather, we're spending money that other people don't have. That won't continue forever. But the revenue is growing very fast. And so there's clearly a demand for the services at the moment. And the question is, at what point does that cap off? I don't know. Our CFO would be the person to ask that question of. And they seem to believe that we've got at least another couple of years of huge growth before we have to worry about that capping off, and maybe beyond that. Maybe they're right, maybe they're wrong. I have no way of judging that.
Just a quick correction. The water problem comes up if you go to France, where they have significant nuclear power generation. They have to turn off the nuclear power stations in summer because the hot water that comes out of the power station after you've run your turbine to generate electricity kills all the fish in the rivers, and the French are not going to do without the fish. But actually, that is an environmental impact, and it is an effect directly from power generation. And we need nuclear to bridge the gap between renewable, as I'm sure everyone knows. So it's not an option for at least 10 years. So there's not zero water. It's indirect, but it is important.
Yeah, I mean, people are under the misapprehension because a load of older data centers use evaporative cooling, but nobody uses evaporative cooling these days. Certainly none of ours do. I can't speak for all of our competitors. So the question then is, when, in the end, it's money that always ends up balancing supply and demand. You can end up with temporary mismatches, but in the end, money has to match supply and demand. And so the question is, are there enough uses for this stuff to grow many orders of magnitude beyond where we are at the moment? I think there's definitely enough to grow one order of magnitude beyond where we are at the moment. 2, yeah, you can debate. 3, probably no. Just in terms of the, if you look at the economy of the world and the possible inputs to the AI companies across the board. So somewhere in that point, we're going to end up in a logistics curve starting to level off. And I just don't know where it will happen. If you look at the actual power supply, all of our training clusters are in the US. They're in the US partly because there is enough power there, and partly because of it's much easier if you're under one legislative regime for training. If you spread across legislative regimes, it gets more complicated. If you look at power in the US, there's about 5% spare capacity in the grid in total, which, unless you grow the grid significantly, that puts a firm bound on how much you can do. If you look at China, China currently has about 100% spare capacity in their grid. So they have a huge amount more they can grow any usage case there. And so the US is going to be much more limited by power long before China is, for example. You know, there is almost certainly an AI war going on between the US and China at the moment. That may be the thing that determines it. But because of the way they built out so much solar over the last few years, you know, the amount of solar China deployed last year is more than the rest of the world deployed ever. It's crazy the amount of solar that's being deployed there. And that's going to be the short-term thing that changes that.
Can I add just one more non-technical detail to that, which is, I think it's one of those places where regulation and policy can actually make a difference. So one of the reasons to build in Texas and not elsewhere in the US is that in Texas, you can earn a significant amount of revenue by turning the machines off in times of high demand. So the way the system is set up there, and there's cryptocurrency companies have well known to do this. They will build in Texas because they will be asked during summer days to turn off period in the underlying models, in the algorithms, et cetera, right? That's, you know, it's speculation, but, you know, that's what we're all hoping for, because no one thinks that in 10 years from now we'll be running the same old transformers in the same old way. We devoutly hope not. In the short term, however, we might never get there if we literally run out of dollars or megawatts to keep the innovation going, right? And so in a way, all the efficiency we can claw back over the next 5 years is about giving us that lease of life, and that's tremendously important.
Yeah, so just coming back on that efficiency question, if we turn the power of the network in our supercomputer to 0, it's not going to make a big bump at the moment. And I can't give you precise numbers because it's commercially sensitive, but the power consumption of the network in our data centers lies somewhere between 5 and 10%. If you reduce that to use no power, it wouldn't generally change the way you think about it. But that's assuming that the GPUs continue to be the way they are. And nobody in their right mind would continue to extrapolate GPUs the way we're currently doing over the next few years. So we've got to change the way we do compute. And every big player has their own in-house compute program. We're no different. We have our own in-house compute program. And so the biggest demand of that is to get the power consumption of the compute down. And at that point, now we start to care about the network. So it's not that right now, if you made the networks more power efficient, we would care. Actually, we wouldn't care all that much. It just doesn't bump the needle. But we will once we get the power of compute down substantially. And there's quite a long way you can go from what currently you're doing on a Blackwell to where you could be, especially on the inference side. It's hard on training, but on inference, you can do a lot better than we're currently doing. And at that point, we really care about getting the power of the network down as well.
Nice interfaces. I think we got layers and nice interfaces in the past because, you know, we had the ISPs. The ISPs needed, I mean, their business was to provide connectivity. No ISP, I think, could do it on their own, right? So they had to have protocols and help one another. And if I understand correctly, there are many entities today, each of which could on its own provide the functionality of the entire stack you were showing on the right. So I think each of them would not want an internet, but they would want the parallel universes. Like each one of them has the entire internet or whatever we want to call this. It's not really internet anymore. So is there hope is the question. So is there hope that we will see, does anybody care? I think you said there is big money and then there are some cases where many of us, so are there enough people care to have the interface and flat out this nice stack that you showed on the right?
Are we being recorded or just streamed? Streamed is, let's assume it's being recorded because I can't control the open internet.
We are.
I think there are a few competing realities. One is, this is one of those where money and caring about something really genuinely come into conflict. Now, this is not to wear the Cloudflare hat, but I know for a long time when I first got to Cloudflare, the CEO would walk around saying he doesn't believe that lock-in is a good business strategy. And oftentimes products would be released, and this is one of the questions, is does this lead to people being locked in? Because they should want to pay someone, not have to pay someone. Egress fees was, I mean, the company made a big stink about this. People would love to move off Amazon and try something else, but the cost of moving data off of Amazon is years worth of monthly bills. On the flip side, some of this happens because you want to compete. So if I think about the zero trust case and the storage case, Zscaler has their config file. Anyone wants to compete in the zero trust domain has to be able to read that config file. And it almost becomes a de facto sort of API. How the thing is implemented maybe is separate from the things that are promised by the configuration. Amazon's S3 storage, I think people offer storage options, and really they only are viable if they can read S3 configuration type things. So there are some business tensions, I think, that force us to move in that direction. But I think I would love it. We had an intern who at 16 years old during COVID decided to deploy his own full stack CDN from layer 2 ECMP load balancing all the way up to certificate management, and would tell you that the certificate management was easily the hardest problem to solve. And he did it by reading a bunch of open docs and specifications and participating in mailing lists because he wanted to learn about computer networking. And I remember having to reach out to the CEO to say, like, does he have to stop this and let go of it? And the CEO's attitude was, no, we want that kind. Like, it's not a threat to the big operation. That level of innovation is something we should welcome. I would love to find ways, whether there are technical elements to get there or formal method, like something to help encourage or foster or facilitate. I don't know what those are, but I would love to see it, you know, like you said, to prevent the big universes. Now, I will say this, I also have written a document that I've not published about how AI operators are literally, because of the demands, are going to change the structure of the internet. And in fact, that might be the fastest path to these sort of isolated universes that you're talking about, is not even so much those services, but it's just, it's AI wanting to be closer to users. And most of those services, like how do you cache an AI interaction? So I think that is actually a huge risk at this stage. Maybe I'll find a way to publish it. Oh, sorry, that was Siri. It's not a satisfying answer, but I do think there's hope. I think there are ways forward. And I'm happy to talk about those offline.
Just to add on that, like recent, like history speaks against you. So, like there's like more and more cases of like hyperscale, like large like trillion-dollar corporations, that they actually make their products, they lock them in, they make them worse.
Sorry, I just wanted to add something on the part. I don't have any questions, but I think that what you're saying is a bit maybe idealistic, but that reality, there's like public like listings of meetings that Google are agreeing to make like their search product wars to increase ad revenue. Like there's
So,
like
I think this is really important. Now, this is very personal. I walk around, people who know me well will tell you that I walk around saying the world is terrible, specifically because it can always be better. Okay? And it looks like what you're talking about is always true, but actually it's not. I mean, Bell was torn up in the last century. And right now we talk every now and then about breaking up the Googles of the world. So there are, I think any large operator will tell you, I've heard CEOs in public saying, it doesn't matter how big you are, if you don't follow the laws of a country, you will, like, you can't beat a government. It's just, it's not possible. So I don't think it's as simple as the prophetic dystopia is always going to be where we're headed. I think there are plenty of counterexamples to that.
not in the last 20 years though, or like
Including in the last 20 years. Absolutely.
I mean, maybe it's far.
And we can take that one offline.
Another discussion. Yeah.
Okay, no, I think this is great, but let's also like to switch gear a second, going on some of the questions that you were also asking about the more technical stuff, because my worry is that, with these are great questions, but, they can take, the whole afternoon. And I think, we should, I think we are going to the pub afterwards. I think this will also be like, good time to take some of this question. I think you have a good point, and maybe I'll summarize and you can add, but if I understand your question was that, it seems that to some extent it's almost like back to the future. So we're going back to the past in order to design the future. I think, we are rediscovering some ideas that, we have been used in the past, or perhaps they were not used in the past, and now they find a new life in this new world. And I think this could be like a good framing maybe for some of the things that both Dushan and
But I think these two need to
Mark
answer.
were-
I'm going to add, is it really that we're going back, or is it just that they were so brilliant to come up with these things at the right, that they're persistent through time?
I mean, there's nothing ever new, is there? I mean, it's really a question. I mean, engineering is always trade-offs. And so at any particular instance in time, different trade-offs win. But the pool of things people invented before never disappears. And so at any particular instance in time, different things end up being closer to an optimum solution. This question about, are we going back to circuit switching? That's a really good question.
The internet is circuit switched by and large.
The-
A large portion.
Yeah, I'd certain that you can do it at different levels, but yes. And in AI data centers, you could definitely imagine that it would make some sense to go along a circuit switched architecture at some point in the future. I mean, we're pretty much committed through the end of 2027 to doing what we're doing at the moment. But beyond that, it becomes harder and harder to actually see that the power consumption makes sense going the way we're going at the moment. And especially once you start to get into trying to do, if I look at what we're doing on our own silicon, it gets, you really want to get the NICs very close to the processing, and that gets harder and harder to do. Currently, the sort of stuff we're doing right now, the NICs are completely separate boards from a CPU. So you end up with different trade-offs, and in different trade-off spaces, the closer you try to get the networking to the CPU, the less smart you can be, because the less power you can burn on per bit. And so the ultimate in low power per bit is obviously circuit switch stuff. And so you can see the trends that it would actually make some sense to end up doing some form of circuit switching. Now, the optical circuit switching, there's a different question, because you can do electronic circuit switching too. And so there's a whole bunch of stuff in this space that might make sense for particular tasks, because we're trying to come up with a different optimization from what we previously did. If you want generality, packet switching is great. If you want to get the power per bit down, and that's the only thing you care about, packet switching is probably not the optimum solution, and there are better solutions out there, but you'll pay a price for them. You'll lose flexibility. So, are we just doing the same things again and again and churning? Yeah, of course we are, because there's only so many good ideas. And maybe every now and then we add a slight tweak to the good idea set, but ideas go around and come around, and there's different engineering optimalities at different times.
Of course, I agree with you. This is all about engineering, right? Finding the right trade-off. But I guess sometimes being a researcher, like reading proceedings of conferences, I feel like the research community really gets kind of like polarized by the last trend, right? And then, so for example, now people that research in ISPs can't really publish that much. So like, they publish, but it's not as cool as doing data center networking, for example, right? But then maybe in 10 years time, ISPs will become cool again. But I think it's kind of like a duty for us as researchers to keep ourselves balanced, even when you accept papers to conferences. And this is kind of reflects also to, the private sector.
I mean, the reason data center networking it's been so interesting recently has been twofold. One is there's just a lot of money. But the other thing, which is actually perhaps more interesting, is that because each building has sufficient value that you can afford to deploy a single solution in one building. The problem with networking as a field in general is that it's very hard to change anything that everybody depends on, because you've got this literal Metcalfe network effect. The value of the network grows with the square of the number of endpoints. It's very hard to change that. We look at just how incredibly long it's taken to deploy IPv6, for example. But it's not true when you're in a single building and you can afford to spend billions of dollars on it. And so there's a huge potential for doing something different in this space at the moment, and different companies doing radically different things from each other. Nobody else is doing what we're doing. Nobody else is doing what Meta's doing. Nobody else is doing what Google's doing. They're all doing their own different things. And we're in a really weird point in time where people can afford to do things differently. And that's great for research, but you need to be 2 years ahead of where industry is, otherwise you're irrelevant. Academia can do that, but academia can't do that if you look at last year's papers and make an innovation on it. You have to be stepping out in front. And that's hard to do. So then you have to look at what are the trends that are fundamental, as in the power consumption of the silicon, the optics, and so forth. And what could I do differently 2 years out if I look at where those trends cross? That's the sort of place where you can start to think, well, what research can I do in academia that would have relevance 2 to 3 years from now, or 4 to 5 years from now, something like that. But if you're looking at what was published last year and doing a second revision of it, the industry moves too fast and has too many resources.
Actually, maybe Mark, if I can, because I think your last point is really important, and came out also when we were working in the coffee break, and that is sometimes I guess as a student, as a professor, you get almost intimidated. Say, okay, maybe this is a space I cannot play with because I cannot compete against OpenAI or Microsoft, Google, and so on. But actually, what I think is that actually you can, as long as you have this forward-looking vision, doing things differently and so on. So maybe, I guess, Lucian, and do you want maybe to elaborate more and see, how, students, professors, university in general, can have, an impact in this, fast-evolving field?
Not sure I have the answer, by the way. I have a few thoughts. I wanted to reinforce what Mark said earlier, but also, Amir, a variant of the observation you make often pops up as a question that people ask me, which is sort of, oh, where's the novelty, And personally, over the course of my career, what I've realized is, what really matters is that you've picked the right problem or problem space. And, the reason why it matters might be different. Perhaps it matters for commercial reasons because, it's really important for Microsoft and, we're sinking money into it. Personal reasons, you're very passionate about it, just intellectually, it's a really important problem that, and then at least if you're in the networking game, I think it's perfectly fine to use existing solutions tastefully, because the proof of the pudding is it a good solution, not is it different from everything everyone's done before in some weird paper reviewer person's judgment, right? So I think there's that trap of falling into this sort of novelty trap where we forget to ask the first question, is it an important problem and is it a good solution? And that's really important to keep in mind. Paolo wanted me to say something about how we might collaborate given the difficulties of scale.
It goes along those lines, I think.
And I think one of the things I realize, and it might come as a surprise to some of my academic colleagues, but even when you're within a hyperscaler, you face these challenges in a sense that often the problems we want to tackle are scale challenges. But we're taking some risks. We're proposing slightly weird stuff that might not work, circuit switching, what have you. We don't have the luxury of rolling it out for real at scale just to see if it works. That's a risk that no one's going to take. So we've all got to be smart about this. Modeling, simulation, extrapolation, all these are tremendously important, right? And I think the systems community, the SOSP type community particularly, I feel, hasn't really embraced this, right? And they should, right? There is a sort of, if you didn't build it for real and run it on real hardware, then we don't care. But the fact of the matter is there are so many interesting questions to be answered, and not all of them can be answered at scale on real hardware because half of them won't work. That's kind of part of the research. So I think we've got to be sort of more thoughtful about, what are the research questions we're asking and how many of them can we answer without actually deploying this thing on 100,000 GPUs? Because you can only deploy very few things and only the ones that you're pretty confident will not break.
No question.
Okay. One of the kind of fundamental step changes that we saw in AI was the transition from recurrent neural networks to transformers. And I think this was due to
a fundamental increase in parallelizability in processing an input, which kind of unlocked the parallelizability within a GPU, and meant we could start pushing the amount of data that we're feeding into these models and the number of parameters we can use, like to huge numbers that we had never seen before. And then we got these huge improvements in performance. I'm wondering if are we due an innovation like this that kind of co-designs the ML architecture with the networks themselves? That, for example, most of the talk, your talk, Mark, we talked about the synchronous processes that are inherent to large model training. I'm just wondering if we're due an innovation in some kind of ML architecture that can break the need for that synchronicity, and then how that might change the way that we build our data centers and the way that we train our models. And where might this kind of innovation come from? Would we expect it from the ML community or the systems community? Yeah, that's and how would that actually change these things?
Yeah. So you raise a really good question, which is, so I talked specifically about synchronous pre-training because it's the hardest thing. But it's not the majority of what we do. I mean, the majority of what we do is actually not synchronous pre-training. It's a lot of post-training, data, all of those sort of things. Actually, a lot more GPU cycles go on. But synchronous pre-training is the thing that is the hardest. So it's the thing that ends up driving the building design and everything else, because that's the limiting factor. If you can't start with pre-training, you can't do the rest of it. Now, your question is, so do we really need to be synchronous? And the answer is no, there's nothing fundamental that says that you need to be synchronous. It's just, it's much, much easier to do synchronous than asynchronous. On the other hand, when my boss comes and asks me, so is there a single thing that we could do that would make life work better from the network point of view? And I said, yeah, do it asynchronously. Because if you can break that synchronous lock, well, then we gain degrees of freedom that make things much, much simpler to do. But it's very hard from an ML point of view, because you can at least reason about what the outcome ought to be with a synchronous pre-training job. And it's much, much harder for the ML folks to reason about what should happen if you do those things differently. But if we have to keep scaling up, we will have to do things differently at some point. And so that will be a question of where that innovation won't come from the networking side, it'll come from the ML side, folks realizing that they can't keep going in the same direction. It's possible. I mean, they don't tend to listen that much to us. There's more of a pipeline from them to us rather than us back to them. But at some point, they realize that we can't do what they're asking us to do, and at some point it will be fundamental rather than just we have to work harder.
Okay, so my question's more about the GPU architecture itself. So you're talking about how you've got like a block of memory and a block of like compute. And the problem being like transferring like data from the GPU memory to the actual like compute cores. I saw a paper from like over 50 years ago now, like proposing alternating cores and memory. So you're having like per core memory. Is there a reason we don't do something like that?
Well, I think the immediate answer is people are trying to do stuff like that. But it's got technological trade-offs. So there's many ways to do what you're describing. So there are companies like Grok and Cerebras, and they try to do it with SRAM, right? And so you can put the SRAM very near the compute cores, and it's got a few other advantages, but it's also got significant disadvantages compared to DRAM, right? It's less dense for one thing, so it costs more. There are people who go to the other extreme, and possibly is what you're thinking of. I don't know when Dave Patterson was writing about IRAM, but it's been a while, which is to take your DRAM chip and try to stuff compute in there, and then that swings to the other extreme where the compute is extremely inefficient now on a DRAM process, right? So there's sort of, it boils down to the way these different chips are constructed and the process and what gives them economies of scale, what makes them efficient and cheap. I think this idea of moving compute closer to memory in general, though, is seeing a resurgence for precisely this reason. Is hard as it may be, it feels like it's achievable as opposed to like breaking some laws of physics and somehow transporting bits across distance without paying for energy, which, that seems much harder, right? So I would bet in a qualified way on some architecture over the next few years, maybe 5-year time frame, that does it. Exactly how and for which workload remains to be seen.
So these workloads are expensive enough and special purpose enough that people are trying everything you can think of. So not just a question of moving compute close to memory. The other big trend at the moment is moving the compute into the Ethernet switches. You may laugh, but NVIDIA have Sharp, which is basically they're doing reductions in the switch. Ultra Ethernet Consortium has in-network compute, which is you can actually do an all reduce in the switches. And when I first heard this, I thought, you guys are nuts. Switch is a really, really bad place to actually do compute. And they came back with it. No, look, I work you through the math and all the back of the envelope math, and it actually turns out that the compute is cheap. Moving the bits is expensive. Once you're moving the bits through the switch, actually adding them together is actually not hard. People are trying all these different things, but if you do that, the power budget of the switch doesn't move very much. The difficulty is actually not in the ALU. The difficulty is making sure the data is from the different streams is in the switch at the same time in order to be able to add it up. And so there's tons of different approaches here that are trying to move compute to where the data is. And in this case, the data is in transit. But adding it up there actually makes a lot of sense and removes so much of the compute that you need to do in an expensive GPU. People are trying a lot of different things. These workloads are sufficiently large, sufficiently expensive that it's worth trying special things and moving away from what we've done in the past.
So, so I'm gonna go back to the Marwan's point where he said like there are two types of problems. Maybe you all can answer as well. So one is type of the problems where we can throw more money at the problem and maybe eventually get it solved, and then there's the other side of the spectrum. So we are in an environment where there is lots of AI problems and data center, and it's just exciting, and lots of people just hammering the same problem. And I feel like, especially for academia, like we're reaching a point where we are literally thrashing, and there is lots of duplicated work, while we get a lot of, most of the academia is just taxpayers' money, and the companies can just kind of, have some money, throw more money at it, and then just solve it. My question is like, would you still justify working in this crowded area, which is very, very getting like every day is getting more competitive, and it's just getting more difficult?
So I'll try really quickly on this. I'm really interested to hear
think,
what these two people say. Because right now you have the luxury of chasing things that could be driven out of sheer love and passion. Yes, you have to frame it in a way that's relevant and so on, but that's an important distinction to make. The second is kind of comes back to this earlier question, which is like all the hard problems are in AI and the important problem. I don't think that's true at all. I think the level of activity that you're seeing is reflective only of the level of curiosity and exploration. All bets are off and people are taking risks. I think that's really what we're seeing. So one should not constrain their thinking by, is this something that OpenAI would want to adopt? Like you heard, everybody's doing something different. Set them aside, go nuts, maybe see what comes out.
The nature of research is that it takes like 1,000 things that people have tried before one of them actually catches on. It's just the nature of the game. We don't expect the vast majority of things we do to actually change the world, but one every now and then hopefully will. In terms of what you work on, I think you've got to pick topics which where you're not directly competing with what industry is doing, because you can't outcompete industry. There's no way you can outcompete industry, but you can look in places where industry isn't yet looking. Industry is remarkably short-sighted for the most part. Maybe Microsoft a little less than most, but most of industry is remarkably short-sighted and only really cares about the end of the current year and maybe the next year and not much more. So if you look a bit further out, look at where the trends are going, look at where there's flexibility, those are the places where you can actually do research which can change the world. If you look at, well, we're trying to optimize what's going on right now for the current immediate short-term problems, industry will get there first. And they're better funded than you. So they'll get there first and deploy it. So there's really sort of questions as to where you should be working. It's tricky. But these areas where everybody is throwing literally everything in the wall and seeing what sticks, which is what's happening in the AI data center space at the moment. So much stuff is wide open. There's massive amounts of stuff that people could do. Now, the other thing is, most of this stuff, if you think, oh, I came up with a great idea, I'm going to publish my paper, the world's going to really care. I have advice for you. The world doesn't care. If every now and then you may have an idea which you think, this is better than all the stuff I've done for the last decade. This one actually may make it. You've got to go out there and sell your idea. You've got to keep working on it beyond the SIGCOMM paper. You've got to keep working on it, talk to people who might be interested, figure out where, we're deploying at OpenAI now is the direct descendant of the work we did on NDP in 2015. It's taken a decade. It's taken a decade, multiple SIGCOMM and NSDI papers in research, then a startup company, then an industry consortium, and finally a decade later, we're actually starting to do the stuff. And that only worked because me and several others, Kostin Riker in particular, decided it was worth pushing and keep pushing well beyond the SIGCOMM paper. The world is not waiting for your great idea to publish in SIGCOMM and then it will run with it for the most part. You have to actually pick your targets because most things will not succeed even if you push on them. But figure out the ones which have possibly got traction and then go out and be the advocate for the ideas and change as necessary when you get feedback from the world that the world wasn't quite interested in your original idea as you pitched it, but a slight variant of it could be, and so forth. So there's a ton of stuff you can do. But getting it published in SIGCOMM or NINES or whatever is like step one of many.
Sure. I want to pick up on, I think, something that Marwan said, which is the risk-taking aspect, right? I think that's really important. Some of what I'm about to say maybe best off as a pub conversation, but I'll start the conversation now. I'm always surprised by how little our sort of academia in general rewards risk-taking, right? The incentive schemes seem backwards to me. The most efficient thing you can do as an academic research group is something that sort of is the bare minimum to guarantee you that SIGCOMM or SOSP paper. And I honestly feel it discourages the kind of risk-taking that actually we would love to look to academia to, because Mark is right. Time horizons that in industry we can afford to look at are limited, right? So we, in a sense, we've got that ticking clock about, right, well, you've spent a year on it, you've spent 2 years on it, what have you got to show? And it's extremely hard to make the case, though we try, that, this stuff may never work and we'll only know in 5 years, but if it works, it is going to absolutely rock your world. And that is the sort of thing that I would love for people in academia to be sort of trailblazing. Right? Why that's not happening as much as we'd like, I think, yeah, maybe at the pub.
For those steering Paolo just added, maybe that's part of the motivation for NINES.
So I just comment on, as a community, we're very good at self-censoring our ideas. We're very good at taking, at basically drilling the things we work on down to sort of, oh yeah, but that idea was too mad. We're going to work on this one because it actually might be, we don't do that. I had John as my PhD supervisor, which is an interesting experience. Because John generates about 1 million mad ideas, certainly at least 10 mad ideas per day, and he never knows which ones are good. Of those, like 1 in 100 may have been a good idea, but he continuously generates mad ideas, and every now and then you hear a mad idea go back and think, that one we could work with. Unless you're generating large amounts of mad ideas, you're not going to spot that one that goes past. So yeah, be ambitious. We tend to self-censor too much.
Okay, so I got asked to say this, and I know sometimes, sorry, and I won't retaliate on that. Some things to work on that are not what they're doing at the moment. One is there's a bunch of people building neuromorphic hardware. It's not GPUs. Those people are hardware people, they're instruction set architecture, but also fabrics for connecting an actual hardware neural net. Not a GPU. It's not something that does this fancy souped up vector processing, tensor operations. So what's the stack for that? That's what we're here for. We're systems people. They have no idea what the stack looks like. What is the AI software stack for neuromorphic hardware? That's going to be 10 years' work. If the neuromorphic hardware works, and there is some stuff that Steve Ferber, who designed the ARM chip, built a system several years back that actually works, but it's really big and expensive. When somebody does a system on chip, it's going to be super interesting. 1,000 times less power consumption than a GPU for the same kind of scale neural net. So totally applicable, but nobody has a clue what that looks like. There's no like CUDA interface for such a thing, right? And there's all the other things they do. So that's the first thing. Second thing, explainable AI. So not in the world of LLMs and transformers is there any hope of making these things genuinely explainable at the moment. There's some very cool fundamental statistics and people in Imperial are actually doing it, but it's going to be a ways before they actually get somewhere, and they may never. But there are other techniques for explainable AI, nothing to do with transformers. For example, PhiML, the physics ML world, where you have a model that is based in physics first principles. There's a weather prediction system that was done in Cambridge and the Turing Institute, which again is 1,000 times less energy consumption, super precise, 2 weeks out, beats all the weather prediction systems in the world, including DeepMind's clever weather prediction AI system. But it's based in translating the physics model automatically into the structure of a neural net, and then executing that neural net by training it on data. Super interesting because it's inherently explainable, but it also is inherently only does what you wanted it to do. So this is interesting. What other areas could you do that analogy? And it's similar to retrieval augmented model stuff that people do post-training, except this is pre-training. So it's like really interesting. You only have the necessary and sufficient bits of a neural net for the models you want, but you haven't populated the model with data. So there's two things you could look at, which need a lot of systems work to make them have enough legs. Actually, the weather prediction stuff works, but using it in other areas that weren't something where we've spent decades working on the physics model of weather, but other areas where you have a different kind of model would be super interesting, right? So there's a bunch of those kind of problems which are going to leapfrog what anyone in their right mind would do in a company for the next 2 or 3 years, but you could get PhDs out of or postdoc work, and then you'd be spending the next 20 years of your life building this out for somebody, which would be cool, you know, and you make lots of money and it would be very good and save the planet at the same time. So this is 2 examples, but there are lots more. And they might be some of the mad ideas that Mark said I have. So beware.
I think this sounds like a great.
So let's take a break of tip 2. There's food outside. We need to thank Dusan the power of the food. Okay, you guys lunch.
Sorry. Yeah, I just cooked it the back.
Thank you, Paolo.
Yes.
I wasn't aware. Actually, I think with it.
Can I ask the three of you to check Discord, because there were a couple of questions for you, but they came too late and I couldn't ask them. So can you have the Discord link, right?
I've never used Discord in my life.
So welcome back to the live stream. We're from Lausanne again. We're going to do one live talk. One of the things about NINES that we've been experimenting with is having not just technical talks, but also some talks about how to conduct a career as a networking researcher. So there's a talk in London by Katarina on this topic, and then I have a talk I'm going to give here about writing papers. So let me share my screen. All right, and let me just double check that the live stream has my screen share. I don't see it yet. There we go. It's up now. Okay, great. Okay, so this is a talk about how to write a paper, or perhaps how to write a bad paper. And of course, anyone who's been in computer science for a while, you've seen the series of talks by Dave Patterson from Berkeley, often emulated by others. Dave has this very famous talk, How to Have a Bad Career in Research and Academia. So I'll show you sort of 10 commandments. Some of these are very sort of straw man kind of, tongue-in-cheek like positions, but they're things that you can think of and avoid when writing papers. I also want to acknowledge this talk was first given in the programming languages community, where I also sit, at a mentoring workshop for students, and it draws on 3 great talks by Derek Dreyer, Simon Peyton-Jones, and Benjamin Pierce. And with permission, I've used a lot of their material in this talk. So again, I'll take you through sort of 10 commandments, and I have to start by addressing the elephant in the room. LLMs are here. People are using LLMs to write papers. So, are we done? No need to worry about writing anymore. Well, if you look at the history of writing, you can go back to, the earliest sort of ways that we carved glyphs onto, stone tablets, eventually sheepskin, then the printing press. Then fast forward a bit, we have LaTeX, tech and LaTeX. It's true that, generative models are amazing. They, have basically memorized the internet, and they're able to generate very lucid prose from high-level prompts. So, I think that, yes, LLMs are going to be a big tool that people are going to use in writing, and are already being used. But I would argue, at least in 2026, beginning of 2026, they're not yet a complete replacement for traditional methods of writing. Just for fun, I tried, zero-shotting an introduction this morning, and I won't read it because it will take a few minutes, but, it's very smooth-sounding prose, totally grammatically correct English, says nothing, right? And so I think, we've all experienced this as we played with AI tools. If you just sort of give it some raw materials and ask it to write a paper, you're not going to get a great result. This is often called slop, this kind of smooth sounding word salad that doesn't really say anything of substance. Another thing that I think is a big issue that the community is dealing with is hallucinations. You may have seen recent reports of studies of NeurIPS where a bunch of papers had hallucinated citations, which are easy to find. Bodies like the ACM, have guidance which says if you submit a paper with these kinds of hallucinations, then that's a violation of professional ethics and your paper will be rejected. You may have sanctions. So I think, a lot of care is needed just with the state of LLMs today. And the other thing I would say, this phrase, again, comes from PL, but, the best writers don't just write smooth English or smooth prose in whatever language. They have a style and they have a distinctive voice. And, one of the things that happens right now with LLMs is that even if you kind of write a paper and then ask an LLM to improve it, it's going to kind of pull it back to, the eigenvalue or like some, median sort of way of communicating those ideas. And I think this makes for kind of less interesting papers. So, I do admit LLMs are a very useful tool, whether it's, producing a first draft or helping you think about turns of phrase or checking for typos. But definitely in 2026, I would say still use with care. And I think the bigger point is that, even to use an LLM effectively today, you need to hone some of the same skills about thinking and writing and how to structure your ideas. Okay, so with that in mind, the second mistake that I think people make is not identifying what you might call the technical nugget. This is an infamous example from PL. If you're active on social media like Twitter or Blue Sky, you may have seen this paper posted. It's an invited paper from Popple from a pair of PL researchers, Cousseau and Cousseau. It's a very famous result, actually. But it's a meme because it has kind of a sea of Greek letters and it's very dense and it's kind of like, whoa, this is the extreme of PL. But if you read this thing, as I have, at least the first column, there is still a technical nugget. And by the way, there's a whole backstory to this paper that I'll tell people over a beer if they're interested. It's actually a funny story how this paper came to be. But what this paper does is it actually introduces a formal calculus for thinking about abstraction. So even in this kind of sea of symbols, there's a core idea, and everything in that paper is in support of that idea. So, this idea of like, there's something that you want to convey to the readers. There's some insight, some nugget. I think that's, as a writer, that's your goal. You have something that you've discovered as a scientist. You want to convey this to the reader. It's an idea that is useful. It is hopefully general. It is usable, adaptable. People can build on it. Your goal is to get this idea into the heads of your readers. The challenge is when you've done a project, maybe you've built some system or designed some algorithm, done some measurements, you often don't know what the nugget is. And I think over millennia, humans have discovered that the act of trying to tell stories, of trying to write, is often how you figure out what these insights are. So people often say, thinking is writing, writing is thinking. The act of sitting with a tech buffer or whatever your method is and trying to write down a paper, that often helps you discover, what is the project really about. Another thing that is sometimes helpful is sometimes you do a project and there's sort of lots of things going on. I find it's typically best to kind of focus on a small number of things, like one thing. If you find that you have, 3 or 4 different things that are the main thing, often it's better to actually write, more papers. Like just focus on one thing, do it really deeply, do it well. I wouldn't say this is a hard rule. Of course, there are times that papers make multiple contributions, or there's a theoretical contribution and an applied contribution, or different maybe priorities of the contributions. But conveying the nugget and having it be really clear to the reader what that is. If you do that well, you win, and if you don't do that well, then your paper won't be as clear. And another corollary is, you can be fairly explicit about this. You can tell the reader, the contribution of this paper is. You can almost, scream it from the balcony. If you make it hard, if the reader has to do all this work to kind of like figure out, oh, here's what they did and here's why it's interesting, your paper will have a harder time getting accepted. It'll have less impact, and in general, it won't be one of those papers that people kind of remember and think about. So this is like, I think the main thing that you do is like figure out, what have I done? Why is it important to someone else? Okay, another thing that people often do is they don't tell a story. And I think this is natural, like especially if you're a student, you really want to be the expert, you want to have done the deep work, you're right at the frontier of human knowledge. And when you write a paper, you want to like show that off and bring people to kind of, also the frontier of what anyone and you being the expert know. But maybe one thing that's helpful is like, think about what happened if someone walked into your office one day and they had like, what are you doing? What's new in research? Well, you wouldn't just dive them deep into, the hardest thing you've done right away. You would tell them a story. You'd have a conversation. You maybe tell them about a problem and they might say, oh, that sounds cool. And then you'd maybe show them an example and you'd convince them this is an interesting problem and it's unsolved. And then you would tell them your idea for solving it, right? So you wouldn't just jump right into like, here's what I've done. You'd give them all this framing, kind of conveying to them, this is research, this is interesting, unknown. You'd use examples to convey it. And then you'd eventually tell them, why your idea works, some of the evidence, how it relates to other approaches, what you might do, after solving this. And so this, of course, is in close correspondence with kind of a generic paper template. If you look at a typical paper, there's actually a whole bunch of padding. There's the introduction. There's like a background section where you do an example. There's maybe some formal model. This is a PL, for a PL paper, but there's, maybe some model where you, give people sort of the context for this result. And then you finally show the results in the middle. But, together, what you actually did might only take up a third of the paper with all the, framing and such and connection to other work. So thinking about these stories and how to organize a story so that a reader who, doesn't come from your sub area of networking and then can appreciate the stuff you actually did requires care. So a couple of like hands-on tips for crafting narratives. Some of these are kind of really nuts and bolts and some of them are broader. Names, like as you're inventing some new world and telling people about the thing you've done, coming up with names to refer to key concepts helps people understand kind of what's going on. It saves space and it makes the ideas more memorable. Examples. I think there's so many times that people kind of fall over themselves trying to, tell about what they've done. If you can show people what you've done with the right example, it just all pops into focus for the reader. So an early example can help motivate the problem. A running example can help show that your idea works. And you can also use it to kind of tie the paper together. This is one of the things that great writers just do by habit. They find the right example and they weave it through the paper. And then another thing that a lot of papers sometimes miss is having kind of a narrative arc. If you're reading a paper and it's just kind of flat, we did this, we did this, we did this, we did this, here's some results. It's not that much fun, right? And if you think about a book or a movie, they have an arc, right? And there's like tension, and then it reaches some crescendo or some peak, and then things are resolved. Papers can do the same thing. So having some kind of wow moment where the reader can kind of be dazzled by seeing your idea in action, seeing maybe some application of it or some use of it, that really makes your contributions easy to appreciate and understand. Okay, so going back to this idea of the insight or the nugget and contributions. One thing that people often don't think about carefully until it's too late is, as the author, you get to define the contributions. You're not, you're not beholden to someone else's notions of what you've done. You get to say, here's our contributions. And I always think of this as being almost a contract. It's the lens through which readers will understand your paper. And it also kind of sets up, this notion of contract that like, we've done these things and you can assess for yourself whether or not we've done them. So it's a characterization of the ideas presented in the paper, and it also provides the evaluation framework. So there's a bit of a dilemma here because, of course, when you're writing a paper and you're got a, hypothetical PC that's going to evaluate a paper, maybe they're kind of adversarial, acceptance rates are low, you want to really like pump up what you've done and you want the contributions to be strong. But, the picky reviewer is going to also like make sure you say what you did. And so you need to be careful that you don't oversell, right? Your contributions can't be so strong that you're criticized as overselling. So finding the right balance where this is what we did, it's significant, it's important, but it's also backed up by the evidence that we have. So a couple of tips for contributions, and these adjectives I think are really important. They should be specific, they should be significant, and ideally as scientists, they are falsifiable. So they're not just a laundry list of sort of like descriptions of what we did. They're also not vague, they're also not minor things. They're specific, significant, and falsifiable. And as a little example, here's a list of contributions that maybe I could have written as someone who works between programming languages and networking. I haven't actually worked on this, but you can imagine writing this weak list of contributions. We investigate quantum networking from an algebraic perspective. We develop a novel semantics in a core calculus. We study meta theory. We build an implementation. We apply our framework to case studies. This is actually not too far from what you might see in a paper, but I claim these are weak or bad contributions. Much better is to tighten them up, make them specific, highlight their significance, and also make them statements that could be, true or false, depending on what's delivered on the paper. So, we present QNetCat, which extends NetCat with support for quantum teleportation. This probably makes no sense at all, but, pretend that it does. We prove that program equivalence is decidable. This is like a theoretical result, generalizing Cozen's prior work. We apply QNetCat to Bennett's environmental interaction problem and use the semantics to analytically compute a solution in quadratic time. So, each of these is like a thing that as a reader, you can understand what's been done. You can check that we've done it in the paper and assess whether it's significant. All right, so having defined the contributions, of course, the other half of the contract is you should evaluate them. And there's a really simple recipe for evaluation that I learned from Mothi from ETH, which is the following. Every claim that you make, every big claim in the paper, there's 4 things you can do in the evaluation. You should make clear the hypothesis, what is the question that's being evaluated? You should explain the methodology. What techniques are you using to test it? Is it some simulation? Is it a live experiment? Is it proving a theorem? What are the results? What does the methodology show? and then analyze the results. What are the implications of those results? Sometimes, there's some interpretation or analysis needed to understand what's happening. It's this simple. If every piece of your evaluation answers these 4 questions and makes it easy to understand, I think you have a great evaluation. And once you see this list and you start reading papers, you'll notice that people don't always kind of check these 4 boxes. So just do this and you'll be golden. The other thing, though, of course, is sometimes there's a mismatch between the claims in the early part of the paper and what the contributions deliver on. And I really think this notion of, the contributions or the introduction setting up a contract, you should also make sure that your evaluation delivers on what you claimed. Okay. We've talked a lot about narratives and sort of, how to structure key parts of paper. Another thing that a lot of papers do is they don't really organize the technical details in ways that readers can appreciate. Here's a bird's eye view of one of my papers. And I wanted to just sort of show, I'm not going to zoom in and show it to you, but I wanted to show you kind of like how it was structured. This paper had a lot going on. It won a distinguished paper award, actually. But you'll see that there's actually like multiple sort of sub-contributions, these kind of key ideas in the middle of the paper, and they interlock and kind of build on each other. So there's the kind of standard padding, there's the introduction and a background section with some examples. And then we kind of go into the actual contributions. In this case, it was a formal system. So there were some axioms, there was a automata model, there was a theoretical property of decision procedure, there were some extensions. And this structure arose through lots and lots of writing. And the things that we were doing was not just presenting all the results at once. We were kind of teasing them out piece by piece so that, as the sort of contributions layer on each other, the system becomes more and more impressive, but the reader could understand each piece. So, and it also had this idea of sort of, I call it the dessert sort of, we reached this crescendo and there was sort of like, and then there's more. So these purple sections down here, which I'm not going to explain the technical pieces of, these were really like, the paper was really done after the blue section. Like that was our main results, but then we showed, and there's even more you can do with this. So, thinking about how to take, in many cases, really dense, deep, and maybe many results, and how to make the readers appreciate it is another thing that great writers do. And a few concrete tips that help. So one is layering. You can often break down your main results into pieces, where you start with things that are kind of simple, maybe directly follow from the state of the art, and then you add them, you add more and more pieces until you get to the full complexity of everything you've done. Sometimes you do just need to cut. Either in another paper or a long version you put on archive or an appendix. Sometimes cramming too much into the main paper is a mistake and you should just split it out. And then, sometimes you find that actually you just have to narrow the scope and split your work into multiple papers. Sometimes you discover you've written a second paper at the same time as the first. All right. Another thing that people often struggle with is how to describe prior work. I've already said that, in this, if you remember back to the conversation with the friend, you probably tell them about a problem and tell them it's an unsolved problem, maybe describe how people have tried to do it before. And pretty much every computer science paper has a section called related work where you explain how what you've done relates to prior work. But there's this thing that a lot of people do, which is, you kind of, in writing the related work, just come up with a list of sort of papers in the same broad area and kind of put the prior work down and pump yourself up. It's like that prior work stinks and, we're better. And this is not the way to write a related work section. The related work section is a great opportunity. It's a chance to put your work in context and to, yes, like make the light shine brighter on what you've done. But you can do that while still being really generous with credit. So, rather than, this is in cartoon form, writing related work sections that say, them bad, us good, why not say, them good, us even better, right? This is a way, it's more than just a superficial sort of being nice. It's, giving credit to the shoulders of people who you're standing on before. And it doesn't detract from your own contributions to praise the great work that was done by others before you. The other way I think about related work is, again, like many sections are just a laundry list of like other papers, or worse, you know, you look at the PC and you're like, oh, I better cite that person's paper, they're going to ding me, right? This is like, again, not the way to do it. It's really a chance to tell your story through a different lens. So in the main part of the paper, you've probably described what you did by motivating it with some problem, describing your technical approaches and so on, and you tell a full story there. And the related work section, you can tell it through a historical lens. Maybe maybe you didn't tell the story based on temporal, you know, when stuff was developed, or some intellectual, you know, history of sort of how this area has emerged. The related work section is where you might do that. And in doing so, you can give the reader another perspective on what you've done. So yeah, I wouldn't approach it just as a way to sort of cover your ass. I would say, you know, use it as a way to reinforce your perspective on the technical landscape. You can choose, you know, the bolded paragraphs or the subsections of the related work section, and you can show people, you know, here's how I think about quality of service or internet measurement or congestion control. And you can group, the thousands of papers on those topics, select some of them and tell a story, and then explain how your contributions have changed it, you know, what new ideas you brought. So it's really a chance to again, emphasize what you've done, yes, but also relate it and in a positive way to the many people who have also worked on these topics. All right. One other thing that's maybe more mechanistic is, you know, we're all computer scientists, and for better or worse, we're a deadline-driven field. I came to computer science from history of science, where writing happens not on any deadlines. And I found it really jarring when I first learned how kind of deadline pushes go, and that, you know, your success as a grad student or a junior professor is like, how many papers can you squeeze out for each deadline? It's just, I don't know, it's just the way our field is. But I think there's this deeper point about writing and the timing of writing, which is, you know, we often think that research goes like shown here. You have some idea, you do the work, and then you write it up. And people talk about it all the way, like, it's time to do the write-up. We wrote up the paper. But as I said before, you know, writing is thinking and thinking is writing. So much better is to write as you go. So you have some idea, of course. I think that's most projects start with some idea, but then you can almost immediately start writing. And I don't mean that you're like literally writing the, you know, tech, you know, final version of your paper, but I mean, you're starting to collect ways of explaining what you're doing, right? You might be collecting up a bibliography, you might be collecting up examples, you might start trying to write down an introduction that, you know, you later throw away. But there's an interchange between writing the paper and trying to say, here's what we've done, it's significant, it's important, and doing the research, and you go back and forward between these things. Now, this particular tip comes from Simon Peyton-Jones, who's the inventor of Haskell. He is an amazing scientist, and he truly does this. He has an idea, he starts writing, and then he goes and, you know, extends his compiler or builds some better type system or whatever he's doing. I find it very hard to write early in the same way as Simon does. But I was sort of reflecting on my method, and I think it does, you know, approximate this kind of idea of writing as you do the research. So my own projects often, you know, start on the whiteboard. I like to write not on computers with, you know, paper notebooks or whiteboard. And then often I'm building some prototype. And in doing so, I'm, you know, building a system, maybe in OCaml or some other language, but I'm also writing down notes in some document, some ASCII document. And I think that this really is writing the paper. Like often the pieces of this ASCII notes that I'm maintaining as I go, it becomes the structure or the examples in the paper. And then at some point after kind of playing, you know, wrestling with the ideas and the code for a while, then I sit down and kind of get serious about writing an outline. And then eventually it turns into some, you know, LaTeX fancy version that gets submitted. So I think, you know, the particular topology of your sort of, you know, writing process graph may be different. But I think the point is, it's not a linear chain that goes from idea to research to writing. There has to be a continuous cycle in the middle as you're doing things. All right. And conversely, you know, writing, not conversely, in the same spirit, you know, writing the introduction last. I know some people approach that in how they write their papers. That is very much not something that I do. I think in writing introductions, it's really helpful to do that early. You know, as soon as you maybe give a first talk on a project, or you have a visitor and you want to tell them what you're doing, you know, having the introduction narrative and like, what's the hook? What's the, you know, how do I make the twists into what we've done? That's an important thing to work out. Another trick to introductions, and I picked sort of two famous examples. This is of course, beginning of the Bible, if you're not a Judeo-Christian person. And, it starts with, in the beginning, kind of starts from, literally the beginning of time. Here's another introduction, also famous. Maybe some of you had to read it in high school, by Homer. And, it starts famously in the midst of things, in the middle of things. Sing goddess Achilles' rage, black and murderous, that cost the Greeks incalculable pain. So it brings you right into this kind of vigorous moment of, of the story. And I think, as you're writing papers, not to slander the Almighty, but, I think writing your papers like the beginning of the Bible, maybe not always the right way to go. Bringing the reader into the middle of what you've done as quickly as possible so that you have, as much room to bring them along is a great way to go. And maybe one sort of more down to earth way to show these two differences. Here are two sort of pretend, introductions or parts of introductions that you could imagine. Example one is kind of more like the biblical version. Starts from sort of very first principles. Computer programs have bugs. It's important to eliminate these bugs. Researchers have tried. It's very important. Like at this point, you're snoring, right? It's like, okay, yeah, I get it. Example two brings you right into the middle of things. Consider the following program, which has an interesting bug, and then there's some program. We will show an automatic technique for identifying and removing such bugs. So, part of this is that, well, the first one is kind of vague and mysterious. The second one is very specific, but it really draws you in. And so, thinking about these examples, thinking about what are you going to claim as the thing you did early. This is a thing you can do when writing introductions early that really helps. So bring the reader in quickly, and examples are a great way to do it. All right. The last thing I'll say is about people. So you don't have to work with others, but I think as a field, computer scientists tend to be highly collaborative. You'll almost certainly collaborate with your advisor. You'll probably also collaborate with other students in your lab. You might collaborate with others outside your lab. And in general, we tend to be writing, like as a field, we write papers with 3, 4, 5, 25 authors. And as a grad student, your job is to really, drive projects forward, right? You're showing that you are able to do research at the highest level, and that you can sort of be the person providing thrust and steering these projects. So I often think that, there's different roles, and this part especially, I would say these are not rules or axioms or anything. These are just, some norms that and you'll find differences in different groups. But finding ways to benefit from all the structure you get from your advisor, from colleagues, from your collaborators, it can help your writing get much better. So, I always think of the first author, they're the person who probably sort of developed the main results. And depending on their seniority as a student, they probably write the technical core of the paper. There's other authors, maybe they're other students in the lab or other, senior people from other labs. They make some positive contribution and they'll often pitch in support, but they're not necessarily kind of on the hook for driving forward the main result. The senior author, probably your advisor, they often, frame the introduction, they sort of pick over the contributions, and of course they keep the overall execution on track. And then there's all the people around you who are maybe not your co-authors, but they can play a really key role too. So providing feedback on drafts, bringing you encouragement, your paper gets rejected, they tell you about their experiences and how to improve, they bring you coffee and such. But thinking about how to do this writing process, with support of a community is important. And I think, research is not easy all the time. And so, writing papers is not easy. So finding ways to do that, not just by yourself, but with a support network is really important. Okay, so a few closing thoughts. Scientists have been publishing for at least a few centuries. This is, I think, the first scientific journal. It's a French journal from Paris. And, in modern scientific life, it's really, the essential way that we sort of do our work. It's how we publish our results. It's how we evaluate people for jobs. It's how you get promoted. And working on not just your technical skills, but your writing skills is a secret weapon. Like, I think, if you are an off-scale good writer, it will help you a lot in your career. So it's worth spending time on thinking about your process and how to get, better at these skills. So this talk, gives a few lessons and a few concrete tips, but I'll also say, there's no single answer here, and that learning to write well is a lifelong journey. Even writers who are super experienced, won prizes, write novels, write books, they are constantly working on their craft. And when they write something, it's rarely the final version on the first go. They obsess over revising, and they write and they rewrite and they polish and they continue to polish and they throw it out and start over again. So, maybe the most important piece of advice is learn how to be your own kind of critic and leave yourself time to revise, because that's how the best papers get really good. It's not by just sort of doing it once, it's by revising. Another thing I'd say is, read widely. You can always learn from great writers, whether it's your peers or even writers from outside computer science. You'll expand your vocabulary, you'll learn new ways to string together nice prose, and it will generally make you a more sophisticated writer. And then fuse this into your own writing. There's a bunch of standard texts if you're interested. This Strunk and White is a bit outdated. A lot of people don't like it. I confess I still like it, but it is kind of antiquated. I think the two that I go to most often are Knuth and others have a nice piece on mathematical writing. So if you're looking for sort of the rules for how to do technical mathematical writing, this is a really nice document. It's available online for free. And then this Williams book, Style, Lessons in Clarity and Grace, is a kind of modern approach to thinking about prose. And it's an easy read, has lots of hands-on tips. And so if you're looking for something to kind of study on your own time, that's a great resource. Okay, I'll stop there. Happy to take any questions.
Thanks for the great talk. I was trying to figure out the objective you're trying to optimize while writing the paper. It appears to me that you try to optimize this objective. For example, if you go and grab a computer science student or faculty member from a computer science department, would they understand something from the paper and would they appreciate what you've been writing? But to me, the other objective that could be optimized is that, for example, if we as much details as possible in the paper, if the right person goes and reads the paper, they would get much more information from the paper, maybe useful information from the paper. But in the contrary, the average person from the computer science department would understand. And I was wondering which one is the best, basically. For example, if you read Shannon's paper on Shannon theory, I would be interested to see how would you evaluate this paper, because the paper starts with like lemma 1, lemma 2, lemma 3, no story, as much detail as possible. And it was one of the most successful papers in the history of science, I would say.
Yeah, so I'm not sure if the mic picks up the room. I'll just repeat sort of, so the question is sort of like, what's the goal here? And, you can think about different audiences and different ways to measure the success of a paper. And, some of this advice is maybe geared towards a certain style of computer science scholarship, but there's other modes as well. I won't answer your question directly, but I'll tell a quick story. So when I first became a professor, I bought a house, moved to a new town and bought a house, and actually 3 houses in a row all sold. So I bought a house. My next door neighbor was a professor who bought a house, and the married couple on the corner were also professors, and they bought a house. And we were all in different fields. So the person on the corner was a chemist, and the person, my next door neighbor, was an anthropologist, and I was a computer scientist. And it always kind of, I was talking to him about, setting up our labs or our groups, and what was our tenure promotion going to be like, and what were our goals as a scholar. And like we all had similar goals. We wanted to sort of establish our careers and advance human knowledge, but the way that we did it was really different. So the chemist, his goal was basically to write maybe 1 or 2 like science or nature papers, and he was setting up a lab. And this lab was going to, have a bunch of complicated stuff going on that ultimately, maybe at the end of 4 to 5 years, would have produced like a science paper. And the anthropologist had actually already written a book and was going to write a second book. So, she was going to go do field work. She was going to spend her years writing, and it was all going to be in this, 400-page monograph that we published by some university press. And then I, as a computer scientist, was, I wouldn't say I was trying to play the game, but if I was trying to sort of satisfy the usual measures of productivity and impact, I would write a bunch of conference papers, and these conference papers hopefully should be seen as, impactful. And that always struck me because, we're all scholars, we're all at a similar university with similar standards, and yet what we do in our work is so different. I mean, writing a book versus writing, a number of sitcom papers or something is very different. So I think to answer your question, I would say a couple things. I mean, one is, I think all of us as scientists are hopefully trying to, we're here because we want to explore some ideas and have an impact on the world. And that the scope of our impact, of course, varies. Like, as a PhD student, maybe your goal is to show that you are, a researcher capable of doing independent research at the highest level. As a professor, maybe your goals are to pursue some scientific agenda where you have some ideas you want to pursue and so on. And these evolve over the course of a career. But I think, we're all here because we want to contribute positively to sort of the wealth of human knowledge and to do things that are not just padding our CVs, but actually advancing some set of ideas. Now, as far as who the audience is, I think, in more mathematical disciplines, there's maybe less storytelling that happens, and people can jump sort of right into the details, in part because, the field of math has, I mean, first of all, things are very formal. You can give, you can sort of state your problem with one line, let G be a group, and then you're off to the races with something. That's like a little harder in a field like computer networking, where we're so broad. We encompass hardware, we encompass protocols, we encompass systems building, theory. So just, because we've chosen to sort of draw our tent in a bigger way, I think, some of this paper writing is different. But I think it's maybe the way to answer the question is yes, you should understand the context that you're in and the people that you're trying to have impact on. And so, work like Shannon's is in a certain mathematical niche and therefore can sort of get right into things. Other papers end up having to do more storytelling and provide more context. Another thing I'll quickly say, I'm sorry, I'm kind of rambling. A few times in my career, I've done papers that were, I think, truly new, or if not truly new, at least, bringing a community along to a set of ideas they hadn't been thinking of before. And these papers are incredibly hard to get published. Like when you're writing a first paper in some area, no one, including you, understands what it's about. And sometimes these papers are rejected or, misunderstood. It's worth getting these papers published because eventually, you break through, and often these are the papers that win Test of Time awards, and you kind of look back and are proud on. But you're basically trying to sort of forge ahead in a new area where there aren't people around you. When you're publishing in an established area, on the one hand, it's harder because there's all the prior work and you have to somehow do something they haven't done. But it's also easier because everyone knows, what success looks like. It's like, this problem matters and we would love to solve it. And if you provide some solution, it's easy. So these are very different kinds of papers. And you probably, you'll do some of both of them in your careers, and they'll have different kinds of framing and writing. But I think that maybe explains some of the difference, for example, with this Shannon paper.
Thanks.
If I may comment something. There is a complex debate in science, or at least I feel it like this, on incremental research or disruptive research. And it's somehow, to me, sad that all the system is pushing to do incremental research. I wrote once a paper, but it was not published anyway. Thinking about this, I wrote it with Marco, which is in the end, all the scientific system now is based on competitive research, on curriculum, on publication. You are measured by that. So they push you to count your research into thinner and thinner slices of knowledge and to publish it quickly, and it's like this. And on the one hand, this is true. And in this sense, I totally agree with you. If you work like this, you should write your paper as you do the research. Which is somehow like you develop science of its software, in the so-called spiral, which is not linear, is to do a small idea, prototype, small idea, prototype, small idea, prototype. I fully agree. Some of the researchers I've mentored, of course, I tell them that ideally, and I tell them like this, they should go for disruptive research. But it's very difficult not only to get the paper accepted, but to get the funding. I mean, the problem starts with funding. You send a very disruptive idea, and the idea tends to be killed. So many times, if you want to do something disruptive, you hide it. And you say, I'm going to do something incremental, you get the grant, and then you say, no, I'm not going to do that. I'm going to do the really disruptive thing. Now, what people should do, if you allow me to continue a little, if you do something disruptive, typically it takes you much more time than a single paper, then maybe you can write several papers, the very first shocking paper, and then several others or whatever. It's better in theory, but the system pushes you to the contrary. Okay? Shannon is this. He thought a lot. People were doing codes and they were doing it incrementally. I do this code and I improve it, and another guy did another code and improved it. And then he said, no, we need a fundamental theory to understand code. And then we need information. But it's much harder to go down. Okay, so it's up to everyone to decide which one you want to go. If you do this, you go against the system. You are swimming against the current. Reward is huge. Typically, the first paper in the topic, you get lots of citations later, everyone cites you, you are rewarded as the inventor of. I finish. What you said about being killed is totally true. The first paper on fractal traffic was sent to Infocom, was rejected. Next year, the guy sent exactly the same paper to Infocom, best paper award. Because
this is very common. Yeah.
It had published in small conferences, everyone was, oh yes, fractal traffic, fractal traffic. Then when it was no, it was accepted and considered best. So what you said is, I mean, I agree with everything you said. I just wanted to say like a counterpoint, or maybe one we should think on this more fundamental disruptive science. I don't know.
So I want to, it sounds like we violently agree. And I want to respect our coffee break. So I'll just, maybe we'll take yours over coffee. But I'll say, very much like NINES was created to try to create another outlet for more of this, at least somewhat disruptive kinds of thinkings. I think, when communities get too conservative, you can snuff out the creativity. And it's not that everything we do should be a new paradigm, breaking, like we need the incremental research also, but as a field, I think having a mix is something that's healthy. So I think we very much agree. All right, let's stop there. We're going to go offline for about 20 minutes for our coffee break, and we'll be back for a few more papers at 3:30 Eastern time, European time. Okay, we're back for our last session in Lausanne before handing it back to Imperial for Michael Shapiro's keynote. We had selected by popular vote a bunch of talks, but we've had so much fun discussing today that we're running a little behind schedule as are others. So I think unless the room feels differently, one of the talks that had very high votes was the running distributed systems like clockwork paper. Shall we do that one? Okay, so we're going to do that and then we'll have a discussion and then we'll hand it over to Imperial for the close of our day. So without further ado, we are. Let me just actually reset the screen share to make sure. Oh boy. Let me just make sure I get the audio. Easy to forget that. Share sound. Okay. All right, second attempt.
Or SMR for short. Standard technique to achieve that.
Sorry, we'll try one more time because the sound did not go. Let's see. Okay. I think that should be it. We'll try rewinding one more time. Okay, I'm not quite sure what's going on with sound here. Let me try a different way. Third time, I hope will be the charm. We are cursed by.
Oh, maybe you can try sharing the application and stuff.
Yeah, I'll try that. I think that might be the difference. One more try. Share sound is clicked. Application window. NINeS video. And rewind to the start. All right, I'm not quite sure what to do because the share sound thing is checked, and we've tried several different ways. I think we're just going to proceed and watch this video. So folks following the live stream, you can watch the video also from the NINES webpage, and then we'll tune in for our discussion afterwards. Sorry for the AV woes, but we'll just go ahead like this.
On as soon as that machine fails, which could happen due to hardware faults, software issues, or misconfigurations. So the functionality of the service needs to be replicated. State machine replication, or SMR for short, is a standard technique to achieve replication. SMR is implemented using multiple servers for redundancy. Each server stores a copy of the state machine, which is deterministic and has the same initial state for all replicas. So even if some servers fail, the clients can send requests to the servers which are still alive. Therefore, the service as a whole will then remain available as long as not too many of the machines fail. There is an entire area of research dedicated to designing protocols for SMR. In the past 3 decades, there's been a lot of great work on SMR protocols, and there are dozens of solutions available for all sorts of different scenarios. But still, these protocols are not as fast to achieve as we would all like. They have to do a lot of coordination, which adds a significant overhead in terms of the throughput and tail latency, and they need a lot of machines to essentially do the work of one due to some impossibility results such as the FLP theorem. So we wanted to see whether this is truly inherent or whether there is something we can still do to improve things further. In our paper, we showed that the fundamental reason behind these SMR protocols having to do a lot of hard work is the underlying key assumption about the system model. In particular, these protocols assume the asynchronous model, which is very conservative. People want to build systems that are robust, and the asynchronous model results in a system that can work correctly under very difficult conditions. But as you can see here, the clocks on the train nodes are completely out of sync, packets are getting dropped and delayed, and this results in complete chaos. The key question is whether the asynchronous model is a good fit for modern data centers, where clocks are excellent, network jitter is bounded, physical layer packet corruptions almost never happen, the entire network topology is known, and we can know and control the entire workload too. Basically, we are trying to make systems robust by assuming a very challenging environment. But at least in single-tenant data centers, we do have a lot of control over both the workload and the hardware. And therefore, we should be able to ensure that the bad conditions do not happen. Let's see if we can use an alternative model instead of the asynchronous model, which is extremely pessimistic since it assumes the worst for the network. One possibility is the fully synchronous model. But the issue now is that the model is overly optimistic since it does not capture the limitations of real-world hardware. The system is in perfect harmony here, since there's no packet loss at all, and the clocks on all the nodes are perfectly synchronized. But in a real world, physical layer packet corruption can still happen, even if rarely, and clocks will not be perfectly synchronized. Can we make a model which can bridge the gap between the conservative assumptions used by the asynchronous model and the idealistic assumptions used in a fully synchronous model? There is a spectrum here, and neither of the two traditional models is in the right spot for modern single-tenant data centers. The asynchronous model, as shown on the left, is too pessimistic, and the fully synchronous model shown on the right is too optimistic. The key question here is whether we could design a model that is in the middle, a model which is closer to what the systems actually encounter. So we propose the quasi-synchronous model. Firstly, for clocks, we will assume that they're synchronized up to some known amount phi. This could be achieved by buying really good clocks, such as modern oven-controlled crystal oscillators, and or by using state-of-the-art clock-sync systems such as Firefly. Now, we don't want to just assume away packet drops altogether. Instead, we will assume no more than k physical layer losses such as corruptions. We'll do something else to get rid of few drops, and I'll talk about that in a moment. But given that Ethernet links are supposed to corrupt packets at a rate of at most 1 in 100 million, the odds of encountering more than, say, 3 corruptions in a row are so low that it no longer makes sense to design systems for that rare case. In our model, at least one of the k+1 consecutive transmissions sent in a row will be received after some time delta. Let's see how we can actually achieve that upper bound delta. Imagine two nodes A and B sending packets over the same link. In the asynchronous model as shown here, they might send the packets at the same time. So there's a lot of queuing in this case, and some packets are going to get dropped due to the lack of coordination. In the fully synchronous model, we assume a bound, but the bound cannot be achieved because there's too much data, and the packets just cannot get to the other end in time. This happens because this model does not take the limitations of real-world networking hardware into account. Now, in our quasi-synchronous model, we promise a delay bound that depends on the amount of data that is to be sent and the available link capacity. This bound is higher than it would be if only one node were sending packets. The nodes here can coordinate using the synchronized clocks to make sure that the packets they're sending do not collide in the queue, and that no more than a negligible amount of queuing happens. We can reason about amount of queuing using the clock sync bounds. If you're given enough information about the network, control over the workload, it's possible then to get a hard bound on queuing and thus avoid queue drops and any non-trivial delays. Therefore, delays are bounded and queue drops will not happen, and we only have to deal with the physical layer corruptions, which are extremely rare. Now, there's a few more assumptions that we need to consider in our model, but not too many, and the full details are in our paper. Overall, our model doesn't just assume some upper bound delta on the message delivery time. It assumes that the system actually has the means to guarantee such an upper bound delta. So far, I've talked about the motivation for our work and the quasi-asynchronous model. I will now describe the main high-level ideas of Watchmaker, an SMR protocol we developed for the quasi-asynchronous model. This is the model we use for Watchmaker specifically, and in the interest of incremental deployability, we wanted to assume quasi-synchrony only for the replicas, which is sufficient. Our algorithm gets full control of the quasi-synchronous replica network. To get the clock synchronized, we use a clock network. Importantly, this clock network is used for correctness in our case, as opposed to for just optimization as in prior work. Before I dive deep into the Watchmaker protocol, let me remind you that there are two key safety properties for SMR, agreement and ordering. To maintain agreement, each alive replica must receive every client request. And for ordering, each alive replica must process the request in the same relative order. The key reason that makes it difficult to provide the safety properties in the asynchronous model is that the network can be unreliable. For example, consider a setting with 2 replicas and 2 clients. When Alice sends a request to both the replicas, it's possible that one of her replicas packets got dropped, but not the other. This would violate the agreement property. Additionally, if both Alice and Bob send requests at roughly the same time, it's possible that the requests arrive in different orders. This would violate the ordering property unless this issue is fixed. We will now discuss the Watchmaker algorithm. I had mentioned earlier that the quasi-synchronous model enables us to prevent queuing delays within a replica network through careful coordination among the replicas. In Watchmaker, when a client has a request, it sends it to one of the replicas. And when a replica gets a request from a client, it'll then send it to all the other replicas. So basically, the replicas have to constantly broadcast data to each other. We can simply divide up the time into little slots, as you can see here in the illustration. Each replica gets to send in some of the slots, while all the other replicas remain silent in those slots. For Watchmaker, we'll use a simple round-robin network schedule. This ensures the agreement property, at least in the case where there's no failures. For the ordering property, whenever a replica sends a packet of the replica network, it'll also include the number of the time slot it is using. You can see that in this illustration. In a failure-free scenario, the replicas could basically just order everything by the timestamps. But we also need to take packet loss into account. So each replica will include the number of the highest slot such that it has received the contiguous sequence of all the packets up to that slot without gaps. We'll call this number the high watermark, or H for short. Replicas don't execute a request until they know that all the other replicas got in. So they'll only execute requests once they're covered by the high watermarks of all the alive replicas. Now, this would be a very horrible idea in an asynchronous network where packet losses can happen quite a bit. And if we trigger a recovery action each time this happens, that would be extremely disruptive. But for our quasi-synchronous model, we have taken care of all the queue drops, and the system runs essentially like clockwork. So all that we are left with are the incredibly rare physical layer packet losses. Doing recovery in this case, when a physical layer packet corruption happens once in a blue moon, seems fine. Let's see how to actually recover when a physical layer drop occurs. If the packet got dropped, the high watermark will stop increasing, as shown here for replica 1. When this happens, the other replicas can tell that a loss happened and which packet was lost using the high watermark. Then some other replica can just retransmit the lost request. Here, we will use our bounded packet loss assumption. Since packet losses are extremely rare, so is recovery. In this case, replica 2 will send k plus 1 copies of the retransmission to ensure that at least one copy reaches replica 1. So I've talked about the failure-free scenario and how to handle packet losses. There's a few other things that we need to consider. For instance, how can we recover if a replica fails? I'm not going to go into the details here, but I encourage you to read our paper if you're interested in learning more about the overall algorithm. Here I'm showing you the full watchmaker algorithm on this slide, not because I want you to read it now, but just to briefly tell you that you have to do some bookkeeping to handle the additional issues, and you have to be a bit careful in certain cases. But fundamentally, the algorithm is not that complicated. It basically does what we just sketched on the earlier slides. Now that I've shown you the watchmaker protocol, let's have a look at the evaluation to see how well watchmaker works in practice. The full evaluation of watchmaker is in our paper, but for the purposes of this talk, I'll focus on the throughput and latency aspects of watchmaker. Let's have a look at the throughput first. So usually people measure this by making a really simple state machine, say one that only echoes its inputs back to the sender. This makes sense because if the state machine itself is slow, then of course the throughput will be low too. But then this is not the SMR protocol's fault. So we set up an experiment with an echo state machine and we evaluated both open loop and closed loop workloads. We compared the throughput of watchmaker to a number of existing protocols, such as Measure and NoPaxos. If you haven't heard of these, all that you need to know is that these are state-of-the-art protocols. In both these graphs, you will see that as we increase the throughput, each protocol maxes out at some point, and the latencies go through that roof. That's the capacity of that protocol. Notice the logarithmic x-axis on the graphs. For watchmaker, the peak throughput at the saturation point is 100x higher than for the other protocols. The quasi-synchronous model enables watchmaker to leverage clock sync for ordering and the bounded packet loss assumption for agreement. Next, we'll have a closer look at the latencies. One of the key problems with existing SMR protocols is that the latency can vary quite a bit. This is because of the asynchronous uncoordinated network and all the messages that have to go back and forth among replicas for complex ad hoc coordination. Here, I'm showing the CDF of the latencies for watchmaker's main competitor, NINeS. You'll see here in this graph that NINeS has a really long latency tail. Sometimes it takes hundreds of milliseconds until we get a response. But with watchmaker, the latency is much shorter in terms of the tail, just a few hundred microseconds, or roughly 1000x less than with NINeS. That's because we carefully schedule a network for watchmaker, so there really isn't any queuing in the quasi-synchronous replica network. To summarize, distributed systems often assume that the underlying system is asynchronous. This assumption is extremely conservative, especially for a single-tenant data center. In our paper, we propose an alternative model that captures more of what modern hardware can actually do, and we call this model the quasi-synchronous model. As a case study, we presented Watchmaker, a quasi-synchronous protocol for state machine replication. The benefits of Watchmaker relative to asynchronous SMR protocols are quite substantial. In particular, we get 100x high throughput, 1000x lower tail latencies, and last but not least, we have to buy about 50% fewer servers. That's all I have for today. Thank you so much.
Okay.
Hello, I'm Charlie. And
The Vimeo autoplay kept going. I think our audio came back partway through that, so apologies for the technical snafus, but I hope it came through. We have a few minutes for questions before we turn it back to Imperial. Any questions or comments? I guess I'll start. I really like this quasi-synchronous model. It's one that sort of, if you rewind 15 or so years when eventual consistency was all the rage and people were sort of working with these more pessimistic system models, I think something like this was always the model that I thought, would be a nice thing to start from in building these kinds of, cloud-based systems. So it's nice to see someone kind of work it out and then
Inside the data center.
Yeah, inside a data center. Yes. Yeah. Yep.
That makes sense. So networks weren't as reliable or fast 20 years ago.
Yep.
It's cool. Very, very easy.
Other thoughts or questions? If not on this paper, we could use our remaining time to reflect on NINES and the distributed watch party pod experience.
So personally, I think it's an interesting try, and I think it would be interesting to collect different experiences in different locations, because I think we will all have like different perception depending on how people are organized, how many people are there, and trying to see what do people see as the most valuable in their experience throughout the day, being like the interaction with the people, being the watching some of the selected talks and so on. Because I have my own preferences, but I have no idea how other people feel. My own personal preference is, for today personally, has been to put aside some time to talk with people I would not have met otherwise. And I have to admit I have similar experience in watching talks recorded as I have when I go to a conference, meaning some I find interesting, some I don't. And those that I don't, I feel like I'm not really sure why I'm spending 15 minutes on the talk that I know after the first minute I will not enjoy. It's not the talk's for it's just this machine replication thing is not on my topic. I know nothing about it. I'm not interested. Right? With all the respect for the project, right, or the work. Which makes me really think about how challenging it is to have an in-person event where we present the work with among people with a wide variety of setting interests. I think this is one of the topics I struggle with CCOM, is that there are many different topics. I know only very few of them I would be interested in. And so an event where most of the program is about presenting those work is not something that I will be personally benefiting most. And there is no conclusion, like I don't know how to resolve this. I'm happy I've met people I could chat with. Whether traveling to watch some talks is the most useful to me, definitely not. Most useful in general. It's not feeling.
Yeah, I completely agree. I think this year of NINES has been a year of experimentation. So some watch parties and pods are very grassroots and sort of organic, and some are more kind of planned and official. I think one challenge that is worth thinking about is, our goals as the organizers for NINES was really to create a top tier venue for a paper, a different kind of paper than is what's being accepted at some of the mainstream conferences right now. And we want these papers to have as much visibility and, mind share and impact in the long run. And how do you create in, a worldwide set of people, the sort of hundreds of researchers who participate in the networking community, maybe it's a few thousand, how to get the same kind of, focus on a set of ideas when, we're all scattered and experiencing different things is maybe one challenge. I know one thing I plan to do is to spend some more time myself watching some of the talks. I think it's actually nice to have these polished presentations all, in one place to look at, as well as the papers, of course. Any other thoughts? We're right at time, but I don't know if I don't see Imperial here, so we can keep talking until they show up. And apologies for our camera. Again, our room has a very fancy camera that we can't access on my laptop. So we're dealing with just a MacBook camera.
I had a minor thought. I really like the podcast style discussion talks. I don't know if it's a thing, if it happens in other conferences, but I found it very interesting. And then I was wondering, can I find this on my podcast app? It would be very nice to listen to it while I'm driving to. And then I started thinking other things. But anyway, I found that very interesting. The discussion part, not just someone lecturing, but there's a discussion.
Yeah, so there are a few venues that do this. I think one that's quite nice, I don't know who exactly is behind it, but I know Jim Carosa is involved and Matt Caesar, and I think there's some EU folks involved, some SIGCOM folks involved. There's the networking channel, which organizes regular discussion with different groups of people. That covers some of the same territory. I also agree, I really like some of the interviews that were done. Those are quite nice.
But I'd just like to say that it was really nice hanging out already today. And although we spent a lot of time watching, but it was cool. And we should do it more often, regardless of NINES. And since you just came from Cornell, I was reminded of my time at Cornell many, many years ago, where we had systems lunch. Is that still a thing?
Mhm.
Amazing. 30 years later, right? That was awesome. I was actually an undergrad, and I would go to these things all the time and learn a lot. It'd be great if we had that group. On a weekly basis? Weekly basis.
Yep. Great. So I think Imperial's ready. So
Even you might learn something.
we'll sign off and hand over to Imperial. Thanks so much to anyone watching us from here. We've had a lot of fun, and we'll be tuning in to London for Michael's talk.
People online, do they hear us?
Yes.
Oh, perfect. Okay, great. Cool. So, let's do the same thing again, because this one. So now you can move around as well.
Oh, perfect. Hi, everyone. Can you hear me? Okay, cool. So thank you very much for inviting me. This has been a pleasure already. And I wanted to tell you a bit about my recent adventures in analog computing. And I should start by acknowledging that these were made possible because of this team at Microsoft Research in Cambridge, a very interdisciplinary team that's working on a very ambitious project, namely building an analog optical computer. And specifically, everything I'm going to talk about is based on close collaboration with these guys, Christos, Kirill, Buju, and Hitesh. And basically what the analog optical computer project is trying to do, and there's people from Microsoft Research here, so I'm going to delegate the harder questions to them. Be prepared, Paolo. And but basically, they're trying to build a new type of computational artifact, one based on a combination of analog optics and analog electronics, with the hope of achieving orders of magnitude improvement in terms of energy efficiency and speed. And just before diving into the specifics, I wanted to say that Marwan talked earlier about the two buckets that problems we work on fall into. So there's problems that are motivated by pressing need or by big money or by external pressure. And then there's things that are beautiful to think about, right? So from my perspective, at least, this is definitely in the second bucket. I'm not saying anything about the real world impact, but I'm saying that what drew me to this project, which is something, again, that was is done by Microsoft, was that it's truly high risk, high gain, right? It's very early to tell what will come out of it, but I think that we already know that there's something very conceptually fascinating about this thing. And there's potential, and there's a lot of open questions. A lot of them relate to actually building these things, which is physics and low-level hardware, and I certainly am not the man to solve any of these, but a lot of them are very abstract computer science questions, right? We don't often get the opportunity to look at a new computational artifact and ask, what can it do, right? What is it good for? And maybe on a more personal level, it also made me realize how fortunate I am, maybe we are, right? And to appreciate academic freedom, right? The fact that I have time to apply things I don't understand to things I don't understand, right? Analog hardware to problems in real world control, and the world is silent, right? I think that's wonderful, right? So just a brief recap on analog computing. So what is an analog computer? It's basically a physical system, right? Where we're used to data, digital data being represented digitally as binary variables, right? Whereas in analog computing, it's represented through continuous physical quantities. This might be liquid pressure, it might be voltage, it might be light intensity. And the computation is basically just letting physics do its thing, right? So we configure a physical system in a certain way, and then we let the physical dynamics of the system evolve towards a solution, right? Maybe we don't often think of it as such, but a thermometer, right, is a very simple analog computer, right? There's external temperature, there's the physics of the mercury moving around, and it computes some continuous quantity, which in our case is the measurement of the temperature. And in addition, it's the original form of computing, right? There's evidence of analog computers tracking the movement of celestial bodies in ancient Greece 2,000 years ago. But it's not just ancient history, but before modern computing, during the 40s and 50s and even 60s, right, this was the prevalent form of computing. And it had a lot of applications for process control, for bomb site control, differential analyzers like what we see in this picture. And by the way, I neglected to mention, but this is a conversation, so please, if you have any questions, don't hesitate. But we all know that this is a story with a sad ending, right? Because ultimately, analog computing, I don't know if it's a sad ending, but for the purpose of the slide, right, it's a sad ending. Ultimately, analog computers were replaced by digital computers, and rightly so, right? Because they have better precision, they're much more scalable, and it's all-purpose computing, right? They're programmable. An interesting thing, though, is that in recent years, we've seen a surge of renewed activity in this domain, both across corporates and across startups. And it's not hard to guess why. It's because of what's driving all activity, right? In the hardware space, or a lot of activity in the hardware space, which is the exponential rise in computational demands. And this is what we're seeing when it comes to unconventional hardware in the form of quantum computing, like quantum simulated annealers. And this is what we're also seeing when it comes to analog computing. And there's a catch, of course, and the catch is everything I said in the previous slide, right? There's a good reason why these things were eventually replaced. And in particular, this is not all-purpose computing. So for analog computers to succeed, we have to identify killer apps. And these killer apps are going to be certain types of computation that are amenable to this kind of computing and that are important enough, right, for people to actually pursue. And in designing analog computing solutions, we're going to have to also deal with the things that made them obsolete to begin with, right? To address scale, to address precision, to address programmability, right? Maybe within a more confined space, right? But we have to address them. So the way the way I think we should think about this is something Peter said to me once. The way I think we should think about this is really the way we think about hardware accelerators, right? That is, we are accelerating or we're improving the energy efficiency of specific types of operations. And the question is, which and why? And these are actually the two things that I've thought about the most during my interaction with folks at Microsoft. It's these two questions. What is the computational expressiveness of analog computing? So at an abstract level, what types of problems can we solve? And I would argue that we need to understand this abstractly to understand, right, what the limit of these things are and what falls within the boundaries of quantum computing. And the other one is where can they shine, right? Meaning not 10 years from now or 20 years from now if we address a lot of scalability challenges, but are there things that are happening now that could potentially benefit from changes and from analog computing? And as I said, I think these are important in the sense that the first question is one we need to answer if we want to guide next generation quantum computing and next generation analog computing and next generation analog algorithms, right? That is how, if we want to push the state of the art forward, in which direction do we need to do it? Yes?
Did you select the order of these two questions? And the reason I ask is actually, we want to know where it shine before we think about the expressiveness. That's the hardware and the algorithm. So I actually like that you selected it this way, peculiar and somehow.
Firstly, thanks. And secondly, historically speaking, I don't know that I have, but I think I may have because for me to figure out where it might be useful, I needed to somehow phrase to myself where it might be applicable first, right? I mean, I would love it to be useful for LLMs, right? But if I don't have an abstract understanding of the limitations, right, then maybe I'm missing on something. So I think that's probably the underlying reason for that specific order. But as I'll show later in the talk, these questions happen to be very closely related, even in terms of the answer. So I think we can show that. Let me get to that when I talk a bit about what I think might be first steps towards these answers. So regarding the second one, though, exactly what you said, right? What are we doing this for? Right? I mean, by the way, the first question in itself is, I think, intellectually fascinating, right? But it would be nice, right, to also have some kind of North Star, right, to guide this. So I want to ground this discussion, and a lot of this talk is going to be grounded in Microsoft-specific hardware, right? But I do want to step back and say that I think that there's general principles here, and that you could do the same type of analysis and the same type of a theoretical spiel in other contexts, right? So when Microsoft introduced their AOC, their analog optical computer, they also introduced this class of optimization problems that I will use to, again, make this discussion more concrete. And then the title is very indicative of what these are. That's a good thing about the title. It's quadratic minimization that's unconstrained. There's no constraints, right? And that's mixed in the sense that variables can be both continuous and binary. Okay, and the reason that they've introduced this specific class of problems is both because it's an extension of another specific class of problems that were coined in the context of quantum annealing. So that was a broader class, but also because it pretty much exactly captures the strength of the hardware in terms of from an optimization perspective. And I will note, because later this might make an appearance, that you can incorporate linear constraints as penalties into the objective, right? Later on, you might be curious about how I hand waved my way around linear constraints, so it's right here. And to address this and other types of problems, Microsoft introduced AOC, right? Where AOC is not that big. This is the second generation of AOC, and it was specifically designed to fit inside a rack. Right? And now, here's how it works, and this is still mind-blowing to me. And I feel free to say this because I have nothing to do with any of this, right? This is just the way that AOC works, but it's sort of like watching a magic trick. Sort of, you have a vector, these are your variables, where the values are represented as light intensities. And then what you do is you take you take these light intensities, you take this light and you project it onto a matrix of programmable filters. And what happens is you can sort of think of it as multiplying the values of the vector by constants. This is what's really going on. And then, so this was a fan-in step. Sorry, the opposite. This was a fan-out step. And then there's a fan-in step. Right? So we're fanning out across the row, then we're fanning in across the column. Can you guess what this is? What mathematical operation looks exactly like this? Matrix vector product. Right? Cool, right? So this is a very well-known this is a very well-known trick from optical computing, right? But it's nice to see it at work. And basically what's going on here is that you can multiply, right, a given matrix, W, think of this as fixed, right, by variables, by a vector of variables. And then the next thing you can do is this was all in the optical domain, you can use analog electronics to apply nonlinearity to the specific coordinates. Why is this useful? Firstly, because some of these we see, for example, in applications in machine learning, right? But even a simpler answer is, if we want to emulate discreteness in a continuous world, these are good ways of approximating it, right? I might not be able to project on 0, 1 exactly, but I can sort of make the variables closely approximate a binary assignment. And the cool thing is that this goes on in the analog domain until we decide to stop and look at the result. Right? So basically, what is it that we've done here? Gradient descent. Right? Because the gradient of a quadratic problem is a matrix vector product. Right? So this is gradient descent at the speed of light. And at some point, you can measure and see what the answer is. Yes?
The lines, they are final, right? Like, so
Yes, yes.
But the analog electronics is with domain switch.
Exactly, yes. So there's photodetectors here, right? There's a transition to the electronic domain, right? And then a transition back. But this is not digital to analog, right? These are transitions within the analog. That's right.
Is that some sort of bottleneck between the domain switch every time?
That is a good question. And I am told that not so much, but I won't defend it, right? Paolo, do you want to defend it?
You don't even need to digitize this, but you can keep in the analog domain. This is where things can be really efficient. And this is different because, there have been, other approaches looking at optical compute, but where they were all falling short is that every time you need to go back to the digital domain and you need like, ADC and DAC, suddenly you have a massive, hit in power. And then to some extent you were losing all the benefit coming from this. But if you can crack this OEO conversion in a cheap way, this may have a good chance.
So keep this in mind, right? What we're doing is we're doing a gradient step, right, in the analog domain, in the analog domain. And actually, when you look at the actual algorithm running here, it has more components because we don't want to get stuck at local minima, right? There's momentum, there's simulated annealing. You might start at multiple different places. But I think the takeaway is you can explore extremely quickly. And because you can explore extremely quickly, you have hope of reaching a global optimum, even where digital systems might fail. Yes? Okay, yeah. So let me get to this. No. So this is the picture, right? but it's scaled larger. How large? That's the next thing. I have a slide for that. Okay. So, but following up on what Paolo said, one of the key points that Microsoft was emphasizing was using consumer sector technologies, things that we have in projectors, things that we have on our phones, things that we have in like micro LEDs, right, to make this thing happen. And going back to your question, we are here, right? And you can see the number of weights, but from our perspective, you should really take the square root of what you're seeing there, because when they talk about weights, they talk about the matrix, right? But the size of the vector is what you'd care about in this context, right? But as you can tell, right, this is impressive, and these are problems with thousands of variables, right? Actually, Francesca, who's one of the leading figures in this project, at some point, this is generation 3 that they're working on. At some point, she gave me a present, which was this model of the next generation of AOC. And the mind-blowing thing was that it was to scale. So it was literally this big. You have these micro LEDs sending across the... So going back to our 2 questions, here are the best answers I came up with so far. One is trying to abstract away from the analog device and trying to characterize the types of problems that it can solve and trying to push the boundaries a bit from the current hardware. And the other is real-time control. And going back to your question, Marwan, the interesting thing is that the two are, there's a lot of synergy between the two. And I will try to do that in this talk, actually, to explain why you need more expressiveness if you want to address more sophisticated problems in real-time control, and the opposite, to motivate the hierarchy through real-time control in different applications. Yes? Yeah. So, I'm sorry? Yes, so I was asked about the accuracy of the result, and what was shown in that Nature paper is that they get remarkably high accuracy, I think, compared to what you'd expect. And one thing I should say about the process itself is that it sort of addresses a lot of I think it implicitly, because of the hardware algorithm co-design, it addressed a lot of the known limitations of analog computing. So, for example, the fact that gradient descent is very robust to asynchrony, right? So I think the algorithm was sort of tailored to that context, right? As long as there is some descent direction, right? Don't necessarily have to optimize for it. And then there's the question of, reading out the outcome, where measurement errors might occur, but they show empirically that they get good results. Yes. Yes. You are me 2 years ago. 2.0.
Maybe it will take me a little bit longer for me to catch up. But I was wondering, does this have any advantages when it comes to our environment introducing errors to these computations? Because in the digital domain, we have lots of error correction. We were earlier talking
Yes.
about sending things out to space and how bad it is because of bit flips.
That's
And what
a-
happens here?
That's a very good question. I will try to address it in this talk through two different things that I will get to. One is the scale. It's a different scale, right? So when Mark was talking about the huge scales, right, an error is a fact of life. Multiple errors are a fact of life, right? So here we're talking about very different scales. Also, not exactly the bit errors that you mentioned, but say perturbations to the input, this actually can help with. I'll try to linger on that. So what is the expressive power of analog computing? There's two very vaguely defined terms here. One is what's analog computing, the other is what's expressive power, right? So when I talk about analog computing, there's two possible characterizations. One is single pass feed-forward operators. There's been work on optical neural networks. I'm not talking about that at all in this talk. The other are systems like AOC, right, that try to exist in the analog domain and do a lot of fully analog iterations, where the idea is to avoid the costly analog to digital conversions, right? Basically, it happens twice: when you formulate the instance for the analog computer to solve and when you turn it back into digital, right? And there's a lot of examples other than AOC that you can categorize inside this class. Now, what's expressive power? That's a harder question, actually. And I'm going to hand wave around it, but I will say that, and I think you will see this when we talk about what types of problems we solve, that we will basically be reverse engineering from the hardware primitives, right? Trying to ask what puzzles can we construct using the same hardware primitives. So what is it that we've just seen? Let's step away from AOC, right? We actually saw fixed point iterations, right? So what AOC did was it applied a linear mapping by multiplying by a matrix. Then it applied a nonlinear mapping in the, it must have this form, right? It must be such that you're stuck. Why are you stuck? Because applying the linear mapping and the nonlinear mapping puts you back in the same place. And AOC is just an instantiation of a generic solver, right? For this problem, which is just continue these fixed point iterations until hopefully eventually you stop. What could this F be? So we have a matrix W and the nonlinear function. It could be, for example, the gradient update step. It could be neural layer activations. It varies across applications, but this is basically the abstraction. Yes?
For example, the analog step. So not to detract from the abstraction, but
yes,
in a practical, like an implementation, presumably the perturbation step, the analog step, could take you 2 iterations away from the solution, in which case that would not be true. Like, how does that happen? Do we worry about that? Does it?
I think, well, for sure we worry about non-converging, right? As we do with any gradient descent process, any fixed point iteration process. Another gradient step won't take you further. I won't go deeply into this. I'll touch on it later. There's also various types of neural networks, right, that sort of smoothly fit into this framework. So what I'm going to do in the remainder of this talk is I'm going to walk you through this set of abstractions, and I'm going to do this through the story of real-time control. And the reason I'm doing this is because I think real-time control is interesting in itself and can benefit from these abstractions. So we are starting out here, right, with model predictive control. How many of you know what model predictive control is? Okay, the rest of you are in for a world of excitement. Okay, so I will talk about that in a bit, but then I will show you how I think with the advent of analog computing, we might actually be able to perform more sophisticated vehicle control strategies that are today limited by the online speed. So I should say, as a networking person, the most exciting thing, graphics I show is a CDF of something, right? So this is, I've always envied the computer graphics people, and this is, it doesn't actually compete with them, but it's a, but it's a big step for me. So show your appreciation. And so what is model predictive control? So let's look at a simple example. We have two dots, the white dot and the green dot. This is a two-dimensional plane. The white dot is us. The green dot is moving according to some fixed trajectory, right? What do we want to do? We want to closely track the green dot. How do we do it? Our actions are exerting forces on the white dot. So we can exert a force on the x-axis and on the y-axis. And there's a model, there's a physical model of the system that says if you exert this much force here and this much force in that direction, this is where the dot will be next, right? And so this is basically a very simple control task. And I will illustrate everything through extremely simple control tasks. And the way we're going to do this is model predictive control. Model predictive control is the go-to strategy in control theory for when you're handling a sophisticated sequential decision-making problem, right? But it's actually remarkably simple intuitively. It's just look at the current environment state. In this case, it might be where I am, right? My velocity, right? And then look at a bounded time horizon. Maybe I make a decision every 1 millisecond, and so I look 10 milliseconds into the future. I have an explicit physical model of the environment, so I can actually optimize for the best sequence of actions. So I'm trying to actually optimize and find my next trajectory of 10 actions to be the best based on some cost model that I have. Once I do that, I apply the next action, which was the first action in my computation. I see what happens, and then I repeat this process. Right? So basically, all I'm doing is I'm looking ahead into the future. I know everything about the world, right? This is why this is for a very specific class of problems, right? Where robotic arms, factories, et cetera, where you actually have an explicit model of the world. I optimize, and then I take the first action and re-optimize. And model predictive control is very much a real world thing, right? So I don't know if you've seen the Boston Dynamics robot backflipping. It's solving model predictive control online. Isn't that amazing? So fundamental to the theory of practice of real-time control, a lot of real-world applications. And I would argue that all the stars are aligned for analog computing here. Why is that? Because there's frequent and very intensive online computation, right? That's the first requirement. We have to care about computing time. There's a natural combination of continuous and discrete variables. I was talking to this robotics guy, and he said that when humans are lifting a cup, they're implicitly deciding on how many fingers, right, to use. Or think of process control, where some of the machines can be switched on or off. Right? So some of the variables, temperature, for instance, are continuous, others are discrete. Non-convex objectives, what people do in practice is they massage the objectives to become convex, but obviously, right, they might miss out on important details. And maybe most importantly, or second most importantly, it's very compatible with the formulation of problems we can solve even with existing analog hardware. Whereas if you look at a control theoretic book, what you would see is quadratic optimization with linear constraints when they discuss model predictive control, right? So it's we don't have to actually tweak the problem to make it fit. And lastly, the scales, right? That is, again, I don't know if we'll ever see analog LLMs or even analog ML models that are orders of magnitude smaller, but here, thousands of variables is a lot, right? These online problems, right? You have state, you're looking into the future, you have your actions, but thousands of variables for a 1 millisecond operation is a lot. So just to give you some intuition, if you look at our specific example with the white dot and the green dot, what would it look like mathematically? You have some cost function. The cost function is there's a bounded time horizon, capital T, and you are trying to stay close to the green point. S is the state. I want my state, think of my location, to be close to that of the green point. And I also want to minimize, U is the control action. I want to minimize the control, right? I don't want to exert a lot of force, right? This is a very standard cost objective. Are you with me or just dazzled? Okay, okay, thank you. That was very kind, not true, but kind. Thank you. And in addition, we have a linear approximation of the system dynamics. So what my student did at an internship at Microsoft Research is he actually implemented a prototype for analog MPC. And what that involved was basically taking the simulator of the analog optical computer and having it interface with MuJoCo. MuJoCo is one of the canonical, or maybe the canonical platform for evaluating control tasks in simulation. And if you look at a lot of robotic papers, they actually have experiments in that framework. And what you just saw actually was that, right? The simple control task implemented in MuJoCo with an AOC simulation in the background. And we try to identify tasks for which analog control is natural. And I want to say that there's two possible ways to win here. One is to be faster than existing solvers, but the other one is to have a better policy. Why would you be able to make better decisions? Because maybe you can solve for a longer time horizon, right, at the same time frame, right? Maybe I could just look ahead more, and I will know that I shouldn't move in that direction because there's a wall ahead, right? Whereas someone that optimizes in a more myopic way will take one step after the other until that wall is right in front of it. So I will give you two very simple examples, but I think they're cute. One is discrete actions. So on the top, you see the analog MPC planner. Here you see a gradient descent planner. That's an MPC planner implemented into MuJoCo. It's myopic. That's what you should remember about it, but it's also continuous. So how does it actually work? It optimizes something continuous, and then it binarizes after the fact, right? In contrast, what the AOC planner is going to do is it's going to optimize while making the variables discrete. And this is the consequence, right? So what you see here, it's actually solving the right continuous problem, but then this binarization after the fact leads to so there are different forms of dancing, right, of the white and the green dot. But this is obviously a better policy in terms of the cost function that we're optimizing for because you're almost on the green dot all the time. Now, here's a more interesting example that I think reflects why you might need the speed and computational power of analog. Here's a very simple example. We define this class of problems that we call track and avoid. So far, we wanted to be close to the green point. But what if we also want to be far from the red point? Right? There's a risky area. There's an area with high wind, right? So now, what would my cost function look like? Maybe something like this, right? Ideally, I would be on the other end of the green point and far from the red point. But as I get closer and closer to the red point, I suffer increasingly, right? And for the suffering to end, I need to do something very non-myopic, right? I have to get through it, suffering more and more in the process until eventually things get better, right? And all of these myopic MPC planners are going to get stuck here, basically. Whereas if you were to optimize globally, you could arrive at the correct point. And let me show you a very simple 2D example. I think it's actually cute, where this is a 2D version of what we've just seen. I want to be here. I don't want to be close to this guy, right? And I'm that white dot. So the optimal policy here is counterintuitive. It's going through the red dot, right? And going all the way to the end because I'm going to stay there and benefit from that in the long term. What you see at the top is this effectively happening in a very non-convex landscape. What you see at the bottom is convergence to the local equilibrium, right? Where basically I'm further away from the red dot. I can't get any further because that's the boundary, right? And I won't get any closer also. So, so basically, what have we learned from this? We've learned that model predictive control very naturally fits in this fixed point optimization framework. And if we extend this framework, suddenly we have more possibilities, right? Possibilities that today are fairly far-fetched to do online. So, and I will talk about two of these, robust MPC and MPC with learned world models. So going back to our simple example, let's imagine that there's also an adversary that's slightly pushing us, right? So we make decisions, we exert force, and there's some devil, right, that slightly nudges us in different directions. So this is a minimax problem. I am trying to minimize the cost, but there's someone working against me. There's someone who controls part of the variables and is trying to maximize, right? In this case, he controls what's known as the disturbances. The disturbances are shifts to my model, right? Like, why does that make sense? Not because I'm actually concerned of an adversary in the 2D board, but because it's a very good way to model inaccuracies in the model, for example, right? Or things I couldn't model for, right? So if I don't fully trust the model to be perfect, right? I may want to be robust in the sense that I perform well even for adversarial perturbations within a certain region. Yeah. So it is important, and this is robust MPC in the control theory literature. There's many manifestations of it. This is a sort of minimax manifestation, but it is important because eventually all of these things need to be sucked into the objective function, right? The problem is unconstrained. So there are some structural properties that you need. Luckily for us, this is very faithful to the way things are modeled in robust MPC, but that also explains why some things are impossible, right? You may not get something quadratic if you start absorbing these terms, right? So in general, minimax optimization is a very broad class of problems, right? Where, again, someone holds part of the decision vector, someone else holds another part of the decision vector, and they have conflicting goals. Or in more vividly, someone is trying to harm the other. And what is this useful? Because these problems arise all the time, right? I want to optimize performance subject to failure scenarios, subject to unanticipated user demands, right? Or in our case, subject to adversarial modeling errors. And you can capture these things by thinking about the problems we've looked at so far and turning them into minimax problems. And let me now sort of give you intuition for why this is helpful, because what's a very standard approach for solving such problems? It's just an extension of gradient descent. It's called gradient descent ascent, where I improve my variables and you improve your variables, right? For me, that means minimizing. For you, that means maximizing, right? This can basically be implemented using almost the exact same machinery we've been using so far, right? There's a lot of literature in game theory and optimization from which we can borrow ideas to make convergence better, right? But the point is, all of the core elements are there. Yes?
AOC, we would need to express more traditional systems optimizations problems. Such
So when you say more traditional systems,
I'm thinking of some global scheduling policy that you want to apply on a machine, or a distributed system.
So I think if you look at the like projected hardware efforts, the numbers that they mention are in the orders of thousands of or tens of thousands of variables that they want to reach in the next generation. So this is why when I was searching for problems that might be appealing, real-time control was appealing to me. But if your problem has 200,000 variables, that means you will have to wait, right, for the analog hardware to catch up.
All right. I was just wondering if there's a realistic system scale that would, where an existing AOC would fit.
So I think that for these problems, right, if you talk about, again, we've talked to practitioners doing process control in various contexts or doing robotics, and for these problems, at least on paper, the next generation of AOC could be applicable, right? These are the scales, right? Once you go beyond that, you need to check that you can actually represent that. So I don't want to linger on this for too long, but we can, but basically this is an instance of a broader class of problems where you have two players. You have two players and they're working against each other. And just to give you a taste of what this could accomplish, so you've seen one, right? One is robust MPC. I'm trying to optimize my control strategy, but I want to be robust to perturbations in the model. But the other one that I think is super interesting, and this has recently been popularized by Jan LeCun, right, who objects to everything LLM and is in love with MPC with learned world models. But basically, this is of course a very different context, but one of the things that you can show actually can fit in this framework is, so far we've been talking about linear models. That is very common because people actually typically do linearize the model because they want to be able to solve simple online problems. But it has two problems. One is that linear models can be inaccurate, and they're more inaccurate the further away you look, right? The longer the look ahead horizon. The other is that linearization happens digitally, right? So you still spend time linearizing the model. What if instead you had an analog model, an ML model that was implemented in the analog domain? Doesn't have to be extremely big. It just needs to be more expressive than a linear model. And that you could actually just stay in the analog domain throughout and use. Right? So this is one other thing you can implement in this more abstract framework. And there's more things, right? There's more things. We can generalize this to multiple player games. All of these abstractions, pretty much all of these ideas extend. I'll just give you intuition for why this might be important. If you think of cars at an intersection, if you think of multiple robots in a shared space, it's not just me optimizing my trajectory. I also need to sort of anticipate what you're going to do. Right? So even if I'm only optimizing for myself, I need to know that if I accelerate my speed, you're not just going to continue at your current speed. Right? And that there's several recent work showing how this boils down to computing an equilibrium over a finite time horizon. Once again, very amenable to the exact same hardware primitives. So bottom line, this is an abstract perspective on the power of analog computing. I think that there's a lot of interesting research questions there, both in terms of extending the hardware and in terms of identifying the killer apps within and without real-time control. That's it. Thank you very much. Yes.
Yeah, it's really cool, this stuff. I'm just going to say, if you're in Cambridge, you should go look at the Moniac, which is a 1949.
I was not allowed to.
Oh, no.
Oh,
Oh, that's
close to
really-
the public.
It used to be in the front entrance of economics. It's a hydraulic analog computer that models the entire economy of the UK. It was originally built in New Zealand. Oh, they got one here? Okay. I mean,
So
there's more
I
than
should
one of
try
them,
that
but the
then. Yeah.
one in Cambridge used to be public. The other thing I'd mention, as Mark will know, is Carl Jameson, who used to be at UCL's at Princeton, has done analog quantum computes. So this is not fake quantum compute, it's real but analog, to model radio propagation in 3D spaces. And I was just looking at probably the most relevant paper to look at is quantum annealing for large MIMO processing. It's on archive, and it's very cool. So it's another supporting case for what you're talking about, which I think is like is super fun. I think also the way you're heading with this, I was thinking with the multiplayer game, you might want to build a Bayesian model of the other player combined with an analog, so that you actually model complex movements in the future, not just
Interesting.
tracking.
I need to think about that.
Yeah, I know, no. Okay, this is, I mean, it's just like millions of things come up anyway. It's very cool.
Oh, sure.
Okay.
Say thank you.
Thank you very much.
Perfect. Yes. So we're gonna stop the streaming now. We can continue with the Q&A for a few more minutes. If that's okay with you.
I'm here. Yeah.
Perfect. So, yep. Right. Yes.
All right. My question is, so quantum computing is another example of a technology that's good at solving certain types of problems. So how should we think about quantum computing now?
So it's interesting. I was at first really confused by that question, because when you learn quantum computing, right, you learn about Shor's algorithm and this amazing expressiveness. But then when you look at the models that are inspired by quantum simulation and simulated annealing, right, they're in fact, sorry.
Another thing we don't teach about in computer science classes is system modularity as a strategy for managing power. No, I mean power as a sociologist or a political scientist talks about it. And I think maybe we should teach that too. Sociologists and political science do think about power, but they don't understand system modularity. So I've been trying to talk to sociologists, and I found the conversation difficult. We look at an example. I mentioned the web, build and keep. Let me talk about a decentralized social media app that's called Blue Sky. On Blue Sky, there are lots of things around the edge called personal data stores, okay? And you pay for yours and I pay for mine, or maybe they give you one for free because they're generous, but it's sort of build and keep-ish. But in the center, there are two big components. There's something called the relay, which crawls all of the personal data stores and pulls off all the new stuff and produces a feed they call the fire hose. And then the fire hose feeds into something that's called the app view. And the app view is where they build a unified model of each post, and then you do that's where, and then they feed, and people get feeds out of that. How are the relay and the app view paid for? Well, Blue Sky started with a charitable donation from the founder, whose name escapes me at the moment, but I'll think of it. And then they didn't quite have enough money, so they took some venture capital money. And now the venture capitalists are coming in and say, by the way, how are you going to pay me back? This is being recorded, isn't it?
We don't have to put it up live.
That's all right. No, I can say this. The Blue Sky people are actually worried that the board of directors is going to make them be evil in order to make some money. Now, every component in Blue Sky is open source. Okay, there's an open source for the relay and so forth. So they've been trying to persuade somebody to bring up a second one, so that if the board of directors pushes them to be evil, they say, well, if I'm evil, then just go use this other one over here. Then how would the second one be paid for? Well, I'll come back to that. Let me look at another system, which is interesting in terms of money routing, and that's Signal. Signal is not a decentralized system. The creator of Signal, Moxie Marlinspike, has a very interesting blog in which he said decentralized systems cannot survive in the real world. He's just very cynical about it. He said, so I have to make a strong commitment to you because here is my promise. I will never charge you money, and I will never profile you and show you ads. Well, they can't profile you because it's all encrypted. So how does Signal make money? It's a 501c3 and they live on charity. It's cheap. Costs 10 cents a month to use Signal. But they have 50 million users, so the president of Signal, a woman named Meredith Whitaker, has to raise $50 million a year in philanthropy. It doesn't scale. When the head of Blue Sky tried to persuade people to bring up a competitive relay box, there was an activity on the web. It was called Free Our Feeds. How are they trying to raise the money? Philanthropy. It doesn't scale. Okay? So we got some problems there. Now, if philanthropy doesn't scale, where can the money come from? Well, one answer is advertising. Oh, that's what makes us evil. By the way, if you go look at how much money there is in the advertising ecosystem, there isn't enough to pay for everything we want to do. And if you want to see what's really going to be bad, figure out how much advertising money it would take to pay for AI. And the answer is no. There's only one place the money is going to come from, and that's us, the users at the edge. But then how do we support people who can't afford to pay? Okay, Signal is free. If you use Signal and you have money, you should make a little charitable donation so that the people who can't afford to pay can be covered. Okay, doesn't scale. Okay, but the source of money, in some sense, unless, of course, the government pays for it. Oh my God, what a terrible idea. Okay, so let me ask the next question. Where do money routing protocols come from? The IETF designed all of the protocols for building the DNS. They didn't design the money routing protocols. They are very clear, at least of a few years ago, they will not design industry structure. They will not design business models. That's not their business. No. Okay. If a bunch of companies get together in a room and try to figure out how to route money, that's antitrust in the Sherman Act, and they'll come get you. Okay. So who's designing the money routing protocols? If there aren't any money routing protocols, the decentralized system isn't going to succeed. End of discussion. Okay. Next question. Suppose the money routing protocol, why would people agree? There's only two answers. One, it's imposed from above like ICANN. It says, you will do this, it's in the contract. Or it's incentive compatible. And now that takes us into a very interesting theory space having to do with how to design protocols that are incentive compatible. There is one area of economics which looks at issues of incentive compatibility. It's called AMD, or there's even more complicated version called distributed application. And just to throw out a few buzzwords in case you want to go look about this, there's a fundamental theorem by Arrow. There's a there's something called a Vickery auction. If you've ever heard of that, it's a second price auction. And there's a mechanism called a Vickery-Clark-Grove mechanism. And if you want to go look some theory, you can go find this stuff. I'm just telling you the name so you can do it. Shanker wrote a very interesting paper. Design. We can go find out about this. In fact, they actually used it to look at multicast and routing, which was sort of, ooh, that's cool. But I'm not sure how much this generalizes. And so I guess the other thing I would say is it's clear that some systems, like systems that don't have a centralized component, it's easier to understand the money routing. There is a decentralized equivalent to Signal called Matrix, and there is no centralized component. There are just things they call rooms, okay? But the synchronizing protocol between the rooms is incredibly complicated because they didn't want to have something called a relay or an app view. But it is a bill and keep system, So I understand how the money flows, but it made it much harder to design a theory. I don't know how Matrix is surviving in the real world. I have one further thought about economics here, which is blockchain is not the answer. Blockchain is a mechanism. It doesn't tell you how the money should flow. It just explains how it might flow. And the blockchain people say, oh, this is the foundation of, Internet 3 or Web 3 or whatever you want to do. No, it's just a mechanism. You still have to solve the money routing protocol. Okay. Now, I know I've gone rather far away from packet routing and queuing and latency, and I like that stuff. I measure latency and that kind of thing. And Scott, what's this conference? Because if you want the scope of this conference to be new ideas in queuing theory and latency and so forth, I'm way out of scope. And he said, no. Why don't you do something that shakes people up? So that's fine. So I've taken us out of the packet routing area, and I'm going to make it much worse. So here's my second topic. If you think about what we do, we built this packet carriage layer, and then these things on top of it that we knew would happen called apps. But if you look at the internet from the user's experience, they don't know about packet carriage. They did a survey about 10 years ago in Indonesia. They asked people, do you use the internet? And they said, no. They said, how many hours a day are you on Facebook? 5. And to them, the internet experience is the apps. And so that layer, that way of thinking about the internet is it's apps with people on top. And so part of what we should think about is people. Some cynical person said to me, not a computer scientist, said, it's not clear to me computer scientists by personality the best ones to understand people. And I said, well, let's be careful about that. But I was talking to a vice president of security from Microsoft who said, well, we just have to teach everybody in the world how to look at a URL and tell whether it's bogus. I said, what? What? Us ain't them. Okay. My current research, I'm collaborating with a behavioral psychologist, woman named Sarah Wiedemann, who spent her career consulting in industry trying to help companies understand why people do the damn stupid things they do. The experience of human interaction, we grew up in tribes. And, now we're talking to 100,000 people, we're talking to the world. Our experience has evolved. We have not evolved. We still have our human tribal brain. And that comes out in lots of ways. There's some wonderful research by a man named Robin Dunbar, who's there are a series of Dunbar numbers, but the one that everybody quotes is you can keep track of about 150 people. And that's the size of your tribe. Okay. We were not evolutionarily designed to shout at the world or have 100,000 followers. Now, of course, we can think about that. We know how to do it. We're smart people. But interesting brain science research that bears here. About 2011, there was a book by a guy named Kahneman. It's called Thinking Fast and Slow. And there's been a lot of subsequent research, and people have evolved his model and all that stuff. So maybe his model's a little out of date. But I sort of like his language worked out by doing a whole bunch of experiments on people. He doesn't measure packets, he measures people. Is that there are certain aspects of human behavior that are not necessarily what you call rational. There's a part of the brain he calls System 1, which makes fast decisions. And System 1 is the part of the brain that we share with lesser mammals. It's sort of back here, and it's sort of like your rat brain. And what it's focused on is survival. That's where fight or flight lives. And it makes really fast decisions. Okay. If I'd known I was going to give this talk, I would have brought a large mallet, because I've discovered occasionally you can surprise people by suddenly getting the table and there's and that's System 1. Say, oh my God, what's going on? Do I have to run away? Now there's a System 2, that's up here, and that's where we think about wonderful things like morality and law, and we make carefully reasoned decisions, and System 2 runs slow. Sometimes it can kick in a second or two. Sometimes you have to think about something for a half hour or 5 years. System 2 can override System 1. It may take it a second or two to do that. But what Kahneman figured out is System 2 is sometimes sort of lazy, and so it just lets the System 1 decision go. Now, if you talk to people in HCI, human-computer interaction, they try to make everything easy, fast. So, one click. I liked that message. One click, I forwarded it. Was that perhaps incorrect? Oh, well, it's gone. One click, I followed the, oh, damn, where am I now? Okay. We try to make everything fast. Maybe that's a mistake. Maybe we should add some friction to certain things. There was a paper by what's co-author? They wrote a paper in 2023 about friction. Actually, it was a very interesting paper because it argued that adding friction to the system was consistent with the Supreme Court's interpretation of restriction on the First Amendment free speech. Well, they're lawyers, that's all right. But what they pointed out is if you slow things down, what they said, it's good to slow things down, but the point is we're actually slowing things down for a particular reason having to do with brain science, which is we're trying to give system 2 a time to kick in and tell system 1, do not forward that message. Do not click that link. Now, you could say, have anything to do with us? I just forward packets. Well, we can think about that. Let me give you another lesson. I've been learning a lot. The need to belong is fundamental, to be part of a group, to be accepted. Loneliness is an illness, it's pathological. Joining a group is more important than, for example, being truthful. Talk to the flat earthers. Some of them will say, I know it's round, but it's so much fun. I want this group to hang out to this group, so I'll believe it's flat. They say, what? What? That's how humans behave. And group formation, and you can say, boy, am I far away from packet forwarding. I am, I know that. I'll come back there with a totally heretical statement. But the issue of group formation and how it happens in things like social networking, so forth, is a critical issue for us to watch. Little groups aren't terribly dangerous. You get 10 people together and they all decide that, some weird idea is true, like, they're lizard people in Washington. I thought that was true. And, but the one that have 10,000, 100,000, that's where really weird pathological things can happen. Notice Signal does not have large open groups, but Telegram does. And the question is then, how do you moderate them? How do you moderate those large groups? And they were doing a sort of lazy job of moderation. And that's why the French arrested the president of Telegram. Okay. They will come and get you. Okay. Signal has no large groups. Meredith moved to Paris to avoid Mr. Trump. And I could wonder if they're going to go arrest her, but they don't have large groups. That's all right. I think Meredith is okay. Now, maybe group formation or large groups somehow have some friction in it. And I've sort of been thinking about what that friction would look like. We were techno-optimists when we built the internet. We wanted this global platform, and we said, now everybody can talk to everybody, and it'll be just wonderful. A lot of wonderful things have happened, but horrible things are happening too. State-sponsored disinformation, and I mean, the list goes on and on and on. Maybe when we form groups that involve people that are far enough away that we don't have any idea who they are, maybe there should be some friction. And what should that friction look like? And should there be service layers in the internet that contribute to that friction? I don't think that's a slowing down friction. I think it's a take extra steps friction. I'm not saying that your packets should show a passport when they cross the border, but that analogy is not totally wrong. We fought putting identity mechanisms into the packet layer of the internet, and I will explain why if you want to know. But a Senate staffer a while back asked me a question that is nonsense, but you know exactly what he meant. He said, why don't packets have license plates? Why can't you tell where they came from? Okay. Well, there's several reasons why we wouldn't do that. I'll ask me a question and I'll tell you the answer. But maybe identity is actually something that's going to really matter in the future of the internet. And I think identity is going to really matter when we start talking to AI agents and say, by the way, what are you and who's responsible for you and so forth. So maybe we need identity tools, and maybe there are places in the internet where we actually ought to be looking at them, which of course probably involves crypto goo, and so it's going to slow things down and so forth. Well, that's friction. Maybe that's a good kind of friction. Maybe there's a place. So this is I'm advocating a conversation about it. Okay? And I understand if you came here thinking you're going to talk about packet optimization, I am a long way away. And well, that's fine. What should our field to do if we really want to change the world? I'm going to say something a little harsh here. Should we still be aspiring to, I mean, look, I started work on the internet in 1975. Right? Blue sky, you know, unfenced west and so forth. And now everything's mature. Should we still try to find ways that we can change the world, or are we just doing performance optimization for the richest companies in the world? You know, why do we do data center optimization? You know, look how much money Facebook and Google and Amazon have, you know. Okay, that's a little harsh. I know that. But they are the wealthiest firms in the world. And of course, there's another question. If you start doing fantastical things of the sort I'm talking about, will I get a job? Will I get tenure? It's very scary. Okay. But when we change the world, and our dreams about change, you know, from I'm still living in 1975. I don't know the answer to that. But I think we ought to have at least have the courage to talk about it. So let's talk about it. I'm done. That was it.
Thanks. That was entertaining.
Questions, Paul?
Hi, Dave. Paul Barber.
Yeah. Hi.
I think across multiple disciplines, but one that I found curiously omitted, and is the fact that I think that we have an opportunity as computer scientists to actually make a huge impact on the future, not from the perspective necessarily of the technology that we develop, but by training our students to think about things like ethics. And I would urge, if you haven't done it already in the context of the things that you presented, to reach out to our friends in philosophy departments who have been studying things like writings of the ancient Greeks all the way through the ethical writings of Kant, that I think can, if we train our students correctly, can potentially move things in a different direction.
Yes, but I'm to philosophers, and I've actually had more luck talking to philosophers than I had sociologists who are terrified by the idea that I want them to predict something about society. I think ethics is sort of a narrow, we ought to teach ethics, but we also need to understand incentive compatibility. And, you know, Google has stopped saying, don't be evil, or at least I think they have. So I think understanding incentives and so forth, this is going to just go up by a factor of 10 in the AI space. So I thought I was going to give AI a miss, but it didn't work. I'm just a packet guy, what the hell. But yes, I agree with you. And I think talking to people across discipline boundaries in philosophy is a good one to try crossing, is an excellent idea.
Let's take a question from Zoom. Brian.
Yes, thank you. Great talk, David. Really nice to hear it. I guess my question, though, is another thing that seemed a little bit absent, missing from your talk was what are the mechanisms concrete mechanisms you can envision that could counteract the natural centralization, re-centralization, winner-take-all type tendencies that you brought up. And in particular, is there a place for governance mechanisms and democracy in this?
Well, in the sense that I think in the long run, the money has to flow in from the edges, because I don't want it coming from advertising, and I don't think philanthropy scales, and I don't want governments paying for the internet or the apps. And that raises some questions. What about people who cannot pay, and how do we deal with equity? I think that, of course, democracy is a minority opinion in the rest of the world. And so the question of how you build something that scales across countries that have very different governance models is a complicated one, especially if you want a global experience. Clearly, China has an entirely different model of how they're going to shape their online experience. So I do think there's a question of equity, and I'm concerned about that. As I said, Signal costs about 10 cents a month to operate. I use it. I think that I can afford. I give them $5 a month. I'm trying to pay for somebody who can't pay for it because maybe they're in some part of the world where paying for it would be dangerous. But I do think that the question of incentive in terms of how the money flows is critical to the success of decentralized systems. And that's slightly different than appealing to something like democracy. I don't know whether that's an adequate answer to your question, but you want to follow that up?
I would love to go much deeper, but I'll respect the other people who probably want to discuss. Thank you.
Hi, Ariam Clemente, Northwestern. As much as I love decentralized systems, and I made my career in that, I don't think that you can use them to take over. It will not replace centralized systems. Centralization seems to be an unavoidable trend in many ways, being particularly that there is no supranational entity that will protect us from that. So what do we do as network researchers to provide the right incentive, if you want, for the correct behavior of decentralized entities?
Of the centralized entities?
Yeah.
No, I mean, what we have seen right now is that with respect to social media or social networking in particular, there is a very powerful force in there, which is the tippy market, winner take all network effect. So I'm on Facebook because you're on Facebook. I'm on X because I'm not on X. I'm on Signal because you're on Signal. If you look at other areas like the teleconferencing apps, well, I have them all on my device. You want to use Zoom? I'll use Zoom. You want to use Microsoft? I'll use Microsoft. You want to use Google? I'll use Google. There isn't quite as much market concentration there. So one question is social networking a special case because it has a very powerful tippy effect? And I think when we looked at AI, for example, we're now having this idea that now I can have my agent and then all our agents, so the latest fad is OpenClaw, and now this thing's called Moltbook, where all your OpenClaw agents should talk to each other. It's not clear that there's a powerful tipping force there. And so maybe there are opportunities for a market where there are powerful players, but they're competing with each other. So what do you do about social networking? I don't know, turn it off. Let's go to small groups. Let's go to Dunbar groups, 150 people, 200 people, groups like that. Maybe giving us a tool to shout at the world, absent some other constraints. I think Europe's trying to figure out how to regulate big tech. I think that our country's captured. I don't know. That's a pretty weak set of answers. There's somebody got his hand up there.
Yeah, go ahead, Alex.
Alex, undergrad, Brown University. Thanks for the talk. I'm curious. So there's this kind of like mentality, I think, in the tech industry often, which is that we kind of like burn this torch of capital in order to advance technology as a whole, but we don't really control where capital decides to put its development. Like by capital I mean like large corporations. Like, there's this thing of like it's a great thing that it's a lot of these technologies that companies like like Amazon, Google are developing all these technologies are very useful in that like you end up having faster Wi-Fi, you end up having better better distributed connectivity or better scheduling algorithms, all these things. But we can't necessarily control where they decide to put their money. They will always put it in where there's a capital incentive. I guess the question is, do you take the approach of like do we just let these companies burn money in the hopes that some of this will trickle into the public sector in a way that will benefit us, or do you think that there needs to be strong regulation to make sure that these companies' incentives are aligned with user incentives? Because I think honestly, with the advent of AI data centers and all these things, I think they're becoming more divorced as time goes on, because there's kind of this circularity of making products that generate hype and generate the idea or the perspective of potential gains in the future, but I think the average consumer really isn't seeing much of that. But I guess the question is like, do you think we need to steer capital incentives?
We can't. We do not have direct tools to steer capital, okay? People who own capital, unless you run afoul of the Sherman Act or something like that. We can try steering it indirectly. One answer, of course, is if you think there are decentralized opportunities like the internet itself, stable standards are critical. You have to know how to enter the market. If the constraints, I mean, one of the problems with Trump's trade tariffs and, oh, let's start building all this stuff in the United States is it's unstable. Who knows what the Democrats would do if they came? No businessman's going to invest in something if they think the rules are going to flip in 2 years or something like that. You need stability. So standards give stability, and standards for money routing are part of the stability. I think that advertising is a particularly pernicious way to pay for the internet or the internet experience. And if we could get beyond that and get people to understand that they should pay for the experience, I think it would align people's interests better. And we can see this happening around the edges. If you look at Spotify, which I know is not a social media app, 40% of the, I haven't looked for a year. I looked at their annual report 2 years ago. 2 years ago, 40% paid and 60% were living on ads. For those who paid, the actual take rate, because they have bulk plans and family plans, we work it out per person, it was about $4.70 a month, 70% of which flowed to the rights holders. For those who lived on advertising, the monthly income per user was 40 cents. Peanuts. We cannot live on advertising, and it's becoming more and more brutal in that space, more and more manipulative, more and more perverted. You know, I find this deeply. But if we could just get people to pay, notice Signal costs 10 cents a month. If you read Facebook's annual report, it costs them about $2 a month. Okay. Of course, what they bring in per use for it, because they look at their profit margins are like disgusting. You know, let's go launch some rockets or something like that. But if you took all the advertising mechanism out of Facebook, and you probably could provide Facebook for $1 a month, it's almost too little to charge. Okay, so I think that is one of the ways to align incentive. But that's, you know, make it easy for money to go in the right way by having standards and change people's expectation. I blame all this on the music industry. They're the ones who perverted people into thinking that free was good, and that's why we have music piracy, and then blah, blah, blah. You've got your hand up.
Going back to the money routing and the beginning of the talk, one question I have is, it's often hard to solve one problem really well. Having, you know, two different groups come up and solve and revolutionize their own areas independently, I imagine is even more difficult to get a successful system. So we often think about problems like economics, security, after our systems get popular, right? And one question is that so bad in a way? If you had gone to those economists and said, oh yes, we didn't have a money routing protocol, let's do it now, would you have ended up with like the phone system instead? And we would be talking about internet in the history books as, oh yeah, that was a nice try in the 80s and 70s, but no, didn't work out because it was so heavyweight, and now we're using telephones still. So
I don't think there is an answer to that question. I mean, that question was really a damned if you do, damned if you don't gamble sort of a, yes, that's like security. It's the same thing about security. People say, oh, the security people say, oh, I got to bake the security and you can bolt it on afterwards. And so you go to extra trouble to bake it in and you're late to the market and so your product fails. And so you say, I'll put the security in later. And then everybody says, oh, you're screwed, you idiot. Why didn't you put the security in up front? And the answer is because then I would have been late to market and failed.
Or it adds too much friction.
Or it adds too much friction. Well, that's
Don't use it.
don't use it because of the friction, right? I think we ought to think more about economics than we do because it is so fundamental. That's all I can say at a very high level.
Lindsay Jukavich, professor at UCLA, also a research scientist at Netflix. So sorry. I was wondering if you were keeping tabs on the low Earth orbit satellite network monopoly that we have. So Starlink has completely monopolized that, and mostly because they're the only ones with a rocket to shoot satellites up. I was curious what your perspective on that is.
I haven't thought about it a lot. What you said is true. I don't know whether people heard that. Basically, Starlink has an effective monopoly because they're the only ones who could put satellites in orbit. And other countries are talking about putting up some because they don't trust Starlink, and there's all kinds of stuff around the edges. But yeah, the guy who has a lot of capital, and where'd the capital come from? And, the capital came from, well, yes, we know what happened there. So I'm not sure I have something wise to say about that, other than to observe that your statement is true and it is potentially problematic. But it would be nice if there was somebody else who had enough money to put that many satellites in orbit. Maybe yeah.
Thank you so much for this talk. This was very interesting. So I was thinking about your part where you were talking about large group formation through social media and this concept of adding friction. I wanted to ask you what you think are potential avenues for computer networkers to sort of add friction to large group formation.
Comment is mostly at a higher level than packet forwarding. And so the question is, what are you when you're a network person? I think the issues of, well, let me give you one example of adding friction. This is heretical, but if you have more than I'm going to pull a number out of the air. If you have more than 150 followers, that's probably too low. If you have more than 1,000 followers, the system should prevent you from reposting. Take the amplification out of the system. If I want to post followers, that's fine. And if they send it to 3 of their friends, but there's been some research about the propagation of disinformation on networks where they've discovered there's a group of women in some southern states that basically sit and just do nothing all day but repost and amplify what are clearly pieces of disinformation. Why should we give people that kind of amplification? That was a design decision. You don't necessarily need that kind of amplification. If you have 10,000 followers and you want to post something to your followers, that's fine. Maybe they pay you back. Maybe you're an influencer. That's a different issue. But reposting, forwarding things somebody else sent, maybe take the amplification out of the system. That's an example of limitation or friction.
I think there have been examples where, for example, I think in India, WhatsApp forwarding was disabled for a period of time, for example, during elections.
Yeah.
And you just prevent people from forwarding to avoid issues.
Yeah. Turn it off.
All right. We have time for one last question. Yeah.
Hi, thank you for your talk. Really wonderful. So I had a question about this idea of money flowing from the edge. So a lot of large scale system deployment is extremely capital intensive, and you require very large upfront commitment of resources. And the nice thing about venture capital is they have a lot of capital and they're willing to put it on the line. They do some amount of research and they decide whether it's worth the risk or fail. So it seems a bit of a difficult idea to imagine end users willing to take large amounts of capital risk for the idea that they might have an application that they could use. And so I'm struggling to see what the vision is for enabling money to flow from the edge in a way that allows you to set up a workable service before continuing to use edge payments to maintain it and so on.
Well, one possible answer is that infrastructure is really expensive, but a startup that's building an app doesn't have to be that expensive because the app can actually just run in the cloud. So somebody once said, it's easy to do a startup these days because everything you need is in the cloud. So there's a question of at what layers are capital intensive, at what layer is the innovation occurring? And, it's, as they said in the gold rush, the guys who made money were the ones who sold shovels. And so maybe we understand that there is competition in cloud today. There's more than Amazon. And that's a lot of capital intensive stuff. The apps that run on top of it may be fairly easy to build. Now, you still need some money to get started. I understand that, but it doesn't necessarily have to be massively capital intensive. So, how long until users begin to see the value of paying for something? So I understand your issue. It's a concern, but maybe we can look at this and say that the really capital intensive stuff is occurring at the infrastructure level. And again, this is going to come up at the AI level. If I have this massive data center the size of Oregon, am I the only one that's running my AI on it? Or in fact, am I renting out space to other agents that are doing various kind of things, and they can just requisition space in my data center and try very quickly to see if something works? Interesting business question.
Great. On that note, thank you, Dave.
Yu. He is a third-year PhD student from the University of Maryland, advised by Professor Alan Liu. His research focus is efficient and observable LM inference system. Today, he's going to talk about their talk title, which is for the APT detection.
Thanks for the introduction. Hi, this is Yu. Being the first presenter after the great discussion just finished is actually killing me. But yeah, so today I'm just gonna share a work that is done with my colleague. We are solving the concept drift in problem-based advanced persistent threat detection. This is a joint work between University of Maryland and Georgia Tech. So first of all, what problem we are facing? So what are APTs? So APTs is not a specific attack technique. It's a certain type of attack that often involves attackers who are highly skilled with a lot of resource. But according to the news, there are always national or state government forces behind it, and they are always planned with multiple steps. They will initialize multi-dimension attack vectors, and they will also hide in a system or environment for a long time to achieve their specific predefined goals. So, which means APT, they are humanly guided, then they are long horizon and with very insignificant attack signals. So to counter this very hard type of attack, the security community actually come up with a provenance-based intrusion detection system, which we call PIDS. So the input of the PIDS is normally streaming system logs, and the output will be some flags for suspicious log, and they will project this semantic log back to the causal relations graph for provenance recovery, so that they can know they can learn the whole story of the attack. Existing PIDS for APT detection, the first one is obviously the rule-based. By literal means, it requires a lot of researchers and experts to analysis a huge amount of attack stories, so they can predefine some rules to prevent the attack behavior. However, it's obviously very human and time consuming. So the next idea, easy to come up with, is we use machine learning as approach, since we are learning stories from the data. So the machine learning approach often comes with two categories. The first one is anomaly based. We learned a huge amount of benign activities. So the next time we saw unseen behaviors, we can classify it as a malicious activity. Oh, the second one is signature based. It wants to be more precise about the attack signals, so they will learn the attack signals. However, all these learning-based approaches, they overlook one particular aspect of the APT attacks. These attackers, as we mentioned, they are highly skilled. They want to do whatever to achieve their goals. So they will adapt. If their certain attack models got detected and blocked, they will try to, they can either mimic more benign behaviors, so the anomaly detector's false positive will raise, or they can just develop new attack patterns. So the already learned signature-based detectors, they will have a more false negative rates. And all this, they will do whatever to bypass this kind of learning-based system, and they are pretty dangerous. So here is the example. So DARPA transparent computing is a APT simulated engagement. There are Team Red, which will simulate the APT attack from the past, and there is a Team Blue, who use different system observation tools to uncover the attack stories from different angle of the system. So the subsets above on the x-axis, there are different attack stories that cover that are uncovered by different tools, and the E3 or E5, there are two engagements happen 13 months apart. And from the table, we can see the graph embedding similarity is varied, which means their attack graph changes throughout the time, and also even from some version of the system, you can see the attack story actually change. This is the example of APT is actually evolving throughout the time, and this also beyond the DARPA datasets, other APTs like IPT42 are known to evolve from APT35, and also some recent work that shows that attackers can actually manipulate the attack graph to mimic blind activities at the graph embedding level, so the model can be even harder to detect. So which means this is especially dangerous for those learning-based that they just train once and deploy forever. They need to have, this demands once you have a new data variant, you have to keep training, keep fine-tuning to adapt to a new data. So obviously the question is, can we just simply use existing PIDS systems and we keep fine-tuning them to solve this problem? The answer is no. So let's consider a successful PIDS system that can handle this concept-driven problem. It has to be good at adapting to the new attacks, but also it has to preserve the prior memory from the already learned attacks. So here is the example with the Atlas signature-based detection system, and we can see if we do not do any fine-tuning and we direct test on the E5 system, which we consider is involved from the E3, the accuracy is pretty low. And if we do the fine-tuning and test on fine-tuning, the accuracy actually raises. But if we test the fine-tuned model back on the E3, the accuracy drops a lot, which means simply adding fine-tuning on those existing PIDS systems that didn't count the concept drifting in their mind doesn't solve the problem. So what do we need for what's the design requirement for a learning-based PID system actually practical under the APT concept drift scenario? Minimum we have to be the model have to be powerful enough to solve the needle in a haystack problem, and it has to good at defending under attack drifting, which means we both adapting to the new attack, also prior preserve the old knowledge. And it also have to train and deploy in timely manners, which means you can retrain the whole model. Let's say your model is huge, and retrain the whole model once the new data comes in. So here is our proposed solution. We propose TDO. We can mainly split it into two timestamps. So the prior drift, which means we are trying to learn a pre-trained base model that have the shared shareable knowledge while maintaining the transferable capability for future use. We combine both the semantic data and the graph data into the input and feed into our specific design multi-task transformer model. So here is our architecture. We specifically designed it to maximize the learning of general knowledge while using different attack task paths to explicitly separate the decision boundary for each specific attack. First, for the shared backbone, we use transformer architecture for the semantic system audit log data, which is known is highly effective with the long context and causal relationship. And we also put the graphic data into representation and add to the input. Then we assign dedicated task path for each specific attack. This ensures that every attack has its own decision boundaries. Therefore, it can prevent interference during the future fine-tuning learning, transfer learning process. So after the train, we have a shared transformer backbone, which learns the maximize of shared knowledge and pair with several isolated attack-specific output projection layers, which is the task path. And also this separate task path design enable us for flexibility to just changing the loss function and the training objective, so we can switch between the signature-based and knowledge-based detection modes. So we don't need to debate whether which one is better for this task. Then there is the second timestamp, which we have new data values come in, and instead of retrain the whole model, we actually use a transfer learning process. We simply freeze the first half of the shared backbone layers and reduce the learning rate. Then we attach a new test head specific to this attack. By doing this, we give the new data its own decision boundary. It's very important because it protects all the shared and specific knowledge we built up earlier, but can still allow the model to learn the new attack patterns effectively. So here we're just gonna show two key results from the evaluation. So again, if we consider a good system under the concept drift, we have to make it adapt well on the new data. So here we can see we are using the anomaly-based mode, and we are comparing the existing works. We can see both precision and recall are higher than existing approaches. This is especially significant when the after drift available data is very limited, which is more useful to think about if you have a new data coming in, the data will be more scarce than the prior URL learned data. And also, we have to guarantee the knowledge we already learned have to not be forgotten. So here is the result. We are the only system that can still maintain a relatively high precision and recall if we use fine-tuned model test back on the previous already trained data set. So which means theta forgets the list, remaining effective after fine-tuning. So conclusion, we introduced theta, normal framework that enhance APT knowledge sharing while preserving the attack-specific patterns. We show that a learning-based APT detection can work under data scarcity and concept drift while transfer learning. And the discussion is, even after we design so many architectures and training workflows, the lack of data, especially the real data, is still a significant fundamental bottleneck in the APT attack. And the next problem is machine learning a generally good solution for this APT test? Thanks, everyone.
So, okay, so concept drift has been discussed pretty widely outside of this.
Yes.
Here's my question. Transfer learning cannot necessarily prevent you, why does transfer learning count here? Like, if I have a 0 day, and the point of the 0 day is no one has ever seen this type of thing. So, for example, something like Spectre, how does transfer learning what is the logical hypothesis that allows transfer learning?
Okay, so I think we have a hypothesis. We investigate all those APT attacks, even though they are evolving throughout the time, but we can still see some like shared patterns.
Isn't that a problem with your data set? Like, isn't your data set essentially causing it so that your data set is curated to have APTs from a single? Because concept drift actually means that you're out of distribution.
Yes, yes.
So how do you know that transfer learning works for our distribution?
Okay, so I think one problem about the APT area is we don't have too much real comprehensive data set. So here in this work, we only use the DARPA data. We use the DARPA data set E3 and E5, and we are using the assumption that even though you evolve throughout the time, you still have some shared patterns that your shared backbone can learn. However, yeah, we also raise this discussion in our paper that if we see some like 0 days with exactly zero similarity compared to the prior attacks, it will be a problem. But transfer learning is still useful in this scenario is because APT, they do evolve throughout the time. And this is the design principle you should keep in mind. You shouldn't just think about training a one big model using all the data that you can get and deploy forever. You still need to think maybe we should use some training workflow to keep involving even though the data might be absolutely 0 days, but we still transfer learning can be useful in this case.
Thank our speakers. Our next speaker is he is a PhD student from CMU. He's going to give us a talk about the Tor network, which is an interesting way to enhance the privacy.
Okay, yeah. So this isn't literally about putting vegetables in metal containers, but it's similar. So I'll speed run through the intro, but basically, if you want to access a website, you ask a DNS and they just give you back an IP address. And that's fine and all, but someone in the middle can monitor your packets and they can figure out, hey, this was going to a particular IP address and it was coming from this source. So they can tell an adversary or they can be an adversary themselves. And the adversary can then basically go to the source IP and stop you. This is a problem that we want to stop this from happening. We want you to be anonymous when you're trying to access content. Tor already does this. Tor was designed to do this. It adds intermediaries. It basically adds 3 nodes in the middle, a guard node, a middle node, and an exit node. And the idea is that the guard node knows who is sending the packet, but it doesn't know where it's going. The middle node knows nothing, and the exit node knows where the packet is going, but not who sent it. And with their powers combined, they form a unidirectional Tor circuit. It's unidirectional because only the client anonymity is protected. If the guard and exit nodes are compromised, then this can be a problem, but we'll get into that later. Establishing a circuit is also a protocol, which I'm just going to speed run through. But basically, the idea is you have a bunch of volunteer nodes and you pick 3 nodes. You can be picky. You can be more picky about the guard node, for example. But ultimately, you pick 3 random nodes and you decide, hey, I'm going to use these as the guard, middle, and exit node. And only the guard node knows your IP, but it doesn't know where you're trying to go to. And that's great. Now, an adversary, even if they're examining the traffic in the middle, they can't link you to what content you're trying to access. But what they can do is try to stop the content at its source. And Tor also has a way to stop this. So they have something called onion services. And the idea is that you basically advertise yourself as an onion service by talking to something called an HSTR, which is a fancy way to say it's a bit like a DNS for the Tor network. It doesn't know anyone's IP, but it lets you connect to an onion service. This on a high level, what basically happens is you talk to an HSTer and you say, hey, I want to reach this particular onion URL. And the HSTer says, oh, I don't know where it is, but you can talk to this particular node and they will tell you where to go. And you use that to basically create a bidirectional Tor circuit. So as you can see here, the client has one unidirectional Tor circuit, so its anonymity is protected, and the content provider who's on the other side has another unidirectional Tor circuit. This is just a bit of background on Tor, which I've gotten through. But the idea is that Tor does allow you to protect the IP of both the client and the content provider. And that's great. You can route traffic through a 6-hop connection. But there is a problem. Now, someone might try to de-anonymize the content provider. And to do that, what they can do is basically make a bunch of different circuits. They can ask, hey, can I connect to you? And of course, the content provider doesn't know better. So they'll make a bunch of different connections. And if it turns out that the guard node happened to belong to an adversary, then they can just try to correlate traffic, or they can launch some other attack. Correlating traffic is probably the easiest. And they can say, hey, I've sent a bunch of traffic to abc.onion and I saw it coming out of this guard node. This means that this guard node is probably connected to this abc.onion. If abc.onion's IP address is this. And this problem, all these attacks basically happen because an adversary can always interact with the content provider in some way. And we want to stop that. So in short, the two small problems we have, are that a malicious client can always connect to a server at will. And secondly, the server must always remain online to provide content. And to stop this, we say we add an intermediary vault of the title. We add a vault in the middle, and the content provider is not directly serving content. The vault is. And that's what we say, putting your onion in a vault. So yeah, if you add a vault and intermediate in the middle, the server, the content provider doesn't need to be online forever. That has benefits. They can leave, they can geographically change their location if they want. And the client can connect to the server at will. But there are a few requirements. The first thing that the content provider should be able to do is you are giving away your content to someone in the middle. And how do you trust that someone in the middle to actually serve your content correctly and not spoof it or read private content or something? And similarly, how does the client know that they are accessing the right content provided by the content provider and not something else that a malicious vault, for example, is trying to champion? We also, since we are trying to build it on top of Tor, we don't want to change the Tor architecture. If we change something, it might break, and then no one's going to use it. Or worse, they will use it. Or you could have a malicious vault, like we are introducing something new, and we don't want the new thing we introduced to become a new attack surface. So out of these, we're going to try to start with this, and you see how it kind of leads to the rest. So that's where T entered, and this was an alternate title. I think it's our moral responsibility to always use a pun if you can. But trusted execution environments are a fancy hardware mechanism in which you can basically trust another entity which owns a piece of a machine that you haven't even seen to run your code, to run your arbitrary code. And you can trust them with two things. One, that they can run it without modification. They're not, inserting their own backends or something into it. And two, that its state is private. They can't just snoop the memory and they read your password or something. I don't know why we stored it, but yeah, they can't read your memory. Trusted execution environments are designed to do this. So you just send over your code and they run it inside this fancy schmancy thing called an enclave. And it's basically a region of memory that is protected by hardware. And because it's protected by the hardware, even the machine owner who has control over the OS and the hypervisor and can change the Linux kernel if they want, they can't read the memory of stuff running inside an enclave. The second interesting thing that trusted execution environments let you do is you can basically hash everything inside an enclave, which in short lets you look at everything running inside an enclave, and it gives you a string, a hash, and you can just say, hey, is this hash matching the code that I sent over? They sign it using a private key. That's the fun part. So when you're sending it over, it's signed using a private key that's burnt into the CPU. So even the um, machine owner can't replicate it because it can only be accessed via hardware primitives. And using both of these, you can meet the two requirements. You can send over, I would trust that it's your code and it's running without its state being accessed. Keys are a work in progress probably. They have side channels that people are working on. It's not in our scope. We are going to assume they work fine. Okay. But yeah, you can prove that code is unmodified and the program state is private. That's just what keys do. So we are going to look at it in our architecture. In our architecture, you have a vault which just says, hey, if you want me to host your content, go to this onion URL, which they can just make. It's advertised in the same way as any onion URL is advertised. And a content provider can use that to upload server code and some authentication secret, like they can upload a password hash or a public key or something better if they want. And the vault can then run the code they sent over, the arbitrary code they sent over inside an enclave. Afterwards, it can make an onion URL and just publish it to the DNS equivalent, the hidden service directory. And afterwards, the measurement, the proof that, hey, it's the right code that I'm running, they send it back over to the content provider. The content provider can then verify it. And if they trust it, instead of saying, oh, come to me, they can just say, oh, go to this vlt.onion. And as far as a client is concerned, when they want to access the content, they will connect to vlt.onion. And they won't ever reach the content provider directly. So the big thing is there's no way for them to reach the content provider. Yeah. So as far as proving the content is correct to the server, that's what T's do. You got the measurement. You're running their code, so the content is correct. How about proving it to the client? Well, as far as the client is concerned, it's not their headache at all. For them, it's just a change in the onion URL. Before they were trying to access the content provider directly, now they will access a vault. And since the content provider trusts the vault, they can probably trust just the onion URL the content provider distributed. As far as changing the Tor architecture, we use the same 6-hop connections and everything. You do need to publish a self-signed certificate, but you can publish it in the same way you publish your onion URL. So if you know about an onion URL, you can just append it to that, and that's just a minor extension to your browser. But you don't need to change the Tor architecture for this. And so about adding a malicious vault, like if potentially adding a malicious vault, we have to be careful. But I can argue about it that if you have a vault that's connected to a content provider, that's a bit of a mirror to a scenario in which you had a adversary that was connected to a content provider right now in Tor. And they're both connected using a 6-hop bidirectional Tor circuit. And the only way the anonymity is compromised is if these connections are frequent, and then you can do some long-running attack. So if the content provider is accessing the vault infrequently, which they should, otherwise you might as well host it yourself. I believe that it should be secure. It's a mirror of the current Tor. But better is that the vault cannot initiate any connections with the content provider. So it might be even better than current Tor. Yeah, so since we met the requirements, we can have the benefits. I'll just skip over the slide. You can look at it in the paper, but essentially the idea is that we actually implemented this, and we found that if you try to run it inside a T, we were worried. We are running it inside a T, it might be slow. But the overhead of those 6-hop, which is happening all around the world in Tor, that overhead is so high that running it inside a T is not that bad at all. So just look at the paper for more details if you want. We have a discussion on that. But this does raise some interesting questions about why someone would want to take on all the attack risks that would normally happen to the content provider. And well, Tor is built on volunteers. Like there are nearly 10,000 relays right now that are all volunteer run. And you could also try to bake in some crypto contract, for example, in the enclave code, that as long as you're getting paid, it can release some crypto, for example. But essentially, it's going to be for some sort of ethical or financial reason. It is shifting the risk. We are shifting the risk from the content provider to the vault owner. But it's for them to measure that. There's some fun questions that also pop up. So currently, if someone is hosting content and they get de-anonymized, they don't have much of plausible deniability. So they can, because they know exactly what content they're serving. But if you have something running inside a vault and they get de-anonymized, like they're just running some code inside an enclave. They would have to launch an attack on themselves to figure out, hey, what was I even serving? And it can perhaps be argued that they're similar to a current or relay in which they're just passing content along. They're not really privy to the contents themselves. It's something to think about, I guess. There's some other interesting things that can be thought of. Like if every onion service in the world ever was inside a vault, then could you just make a vault yourself and then upload your content to yourself? And then if you get de-anonymized, you can just say, hey, I don't know who sent this content to me. So yeah. Or you can have some scenario in which the code running inside is publicly verifiable, or the code itself can be crowdsourced. Some future work includes trying to load balance all the work in the vaults. But yeah, questions?
Any questions?
So I'm wondering, is there a way to verify someone else is running that hardware? Like if they say I volunteered at host a vault code, then I guess how do I know that they have those hardware guarantees and then I can trust to send it to them or something?
If you get a signed measurement later, then you know it's running inside an enclave.
Sorry, could you repeat that?
Yeah, if you get a signed measurement later, you know it's running inside an enclave. The original code you sent over should not have any information you don't want to lose. So you basically send code over and you expect them to run it inside an enclave. Then you can verify if it's running inside an enclave.
Yes, I'm not sure. Are you assuming that they cannot modify their hardware to, I don't know about the cryptographic guarantees or anything like that. Like, could I just change, the code that's in the chip or something like that?
No, that's messing with the silicon, probably difficult. I would assume it's difficult to mess with the silicon and break open a CPU or something. Like you would need to do something like that, probably.
Any other questions? I have a quick question. I think about that is the fact we have to consider if Intel LD is about
That's a good question. So as far as the software is concerned, it's currently easier to run it on Intel because people have worked on it. But in as far as actual implementation goes, you could implement it on any T that can be remote tested. Like it doesn't need anything else.
Thank you, Alice.
So we have sat back and we will starting it at 1 o'clock with people on cooking research.
For the live stream, we will be taking a break. We will be taking a break until the beginning of the hour. So we'll see you all back here at 1 p.m. Eastern. Thanks.
Test 1, 2.
Test, test.
Test.
Okay, there's a switch on your microphone. So when you speak, just turn it on. There's a green light that'll go off on recordings. Okay. All right. Welcome back. So we're now going to have our panel on network systems research in the AI age. We have 4 illustrious panelists, Mohammad Alizadeh, Minlan, you, Rachi Singh, and Jinchen Jiang, who have done a lot of work on these topics. And I'm going to tee it off with a couple of questions, split into both AI for network systems and network systems for AI. And I have 6 questions. I made 3 of them. I got 3 of them from ChatGPT. I asked Mohammad and Akshay to determine which came from ChatGPT and which came from me, and they were, as good as basically a coin flip in terms of figuring which ones came from ChatGPT, which ones came from me. So on that note, we're going to get started here. So I'm really start with this question for the group on kind of AI for network systems, where the first question I'm going to ask is, which problems in our field are genuinely improved by AI? What are better left to classical algorithms? Field papers on things like congestion control, routing, scheduling, there's a failure detection. These all seem like good targets. But it also seems like many AI-generated methods are pretty brittle and fragile when you see distribution shifts. So where has it actually been working so far, and what do we see the future to be? So why don't I just start with Mohammad, and then we'll just go to and we'll see if we get to our second question.
Right. Thanks. Sorry. So I think, yeah, I think so. So what? I think you kind of, you mentioned the key point here that the learning-based methods are trained on some data. So it's really how good that solution is. It's all about how well you've been able to train it. What is that data that went into the process, and how representative is it going to be? So you think about like where these things have actually been used and succeeded. It's in some setting where you can kind of control distribution shifts and control this train test differences. So some examples that come to my mind are essentially anytime you sort of have like something you can kind of turn into like an offline optimization problem. There's been a lot of success. So one example of this that I remember from some of our earlier work on video and was in this video encoding problem, where you have like for offline video encoding, you have a lot of like decisions you need to make. It's called like rate control for video encoding. It's really about like how many bits you allocate to the encoding of any given frame. And you can go far beyond these like generic sort of universal heuristics and do more data-driven optimization of a policy for setting something like that. And because it's a very offline task, like it's sort of, say like this was a project that was done at Google, and say you want to take like all the YouTube videos in the world and you want to just figure out what's the most efficient compression of these that you can do. There's no like really like risk of distribution shift hurting you. Once you figure out like an offline representative set of videos, a good policy for that, you can, run it across everything, and then you'll get like some 10% better compression than current state of the art. And so that stuff like that is actually used. I mean, that is one example. There's a lot of sort of examples of not very sort of general like learning methods, like deep RL or putting neural nets in place, but methods that are about taking some existing algorithms and like, tuning their parameters in a data-driven way. And again, I think, so there are things like that that are used. For example, I know in video, this tuning of playback settings based on data, and probably like Junshen might be able to also speak to that. Like that's something that people do. But before I sort of, I've been talking for a long time. Like one thing I want to say though, there is now this new regime with language models and new ways of actually doing like AI-driven system design or networks that might make some of these questions a bit moot, because now you have these agents that can essentially like optimize and work on these systems the way that humans do. So some of these limitations of previous kind of learning-based approaches structurally is just not there anymore in the same way. You have new challenges, but it might this is kind of very new area, but it might really make these methods applicable, make AI applicable to a much broader range of problems.
Yeah, I want to follow up on what Mohammed just started. There are much richer AI tools and also much richer networking problems. Networking is a field not only about algorithms, but if we look at network management in practice, it's such a complex problem. So we actually had some experience helping Meta to build their multi-agent kind of LLM-driven network management system. So there is not only about traffic engineering, congestion control, this algorithm, but taking maybe topology design as an example, you would have to first get the intents, right? What type of topology you want to design? Say you want to expand your backbone, add some cables to increase the capacity. Then you need to maybe first figure out the physical constraint of where the capacity, additional ways to add capacity. And you may want to then think of a blueprint of what topology you want to change. You may want to next find a forecast of your traffic. So in the next 2 or 5 years, what my traffic may look like. You may want to understand under different failure scenarios, like what kind of failure is critical to us? How do I simulate different types of failures? And finally, feed everything into a simulation, like taking the traffic, different scenarios, understand like throughputs, like latency, all these metrics. So this is a typical like real network management task that involves many subtasks, and all of them are complex. Today, it's all be done manually, and that's where AI really shines. It helps you plan and group all these different steps of the task, so together achieve some end-to-end complex tasks. And this procedure is actually not easy, because it involves many of the existing tools, not new algorithms. Say in traffic engineering, topology planning, but there are a lot of existing tools, and AI is a brain kind of help you to decide how to use these tools. There's a lot of data that people already collect, say the traffic data, the topology data to feed into the problem. So we also need new ways to have more efficient way to feed this data into AI. So there are a lot of such type of research that makes AI really practical to use in practice. Another comment I would like to say is AI is not only there to improve accuracy of a lot of these tasks, whether it's algorithm task or the complex management task. It's also there to help us speed up the procedure. So from algorithm perspective, naturally GPU is a parallelized system. So if there any way to have fast solutions of the algorithm, so you can react fast to these distribution changes, there's also gains to the efficiency in addition to the accuracy or efficiency. And take it broadly as a complex network management task, I think AI is there, the real value is saving engineering hours in dealing with these many complex tasks.
I think these are great points. I think when I think about a problem, all of the problems we're talking about, video bit rate, traffic engineering, topology engineering, it's clear these are, if we had enough time and if we could run Gurobi long enough, we could solve these and get the optimal, right? Like, and there is nothing better you could do than getting the optimal. So that would be great for most of the problems that we're talking about. But I think one of the things that makes it compelling to want to use AI is, the reason that I mentioned, sometimes it can accelerate the decision process instead of spending a long time to solve an optimization. But the thing that I think about when I say, is this actually a problem that I want to apply AI on, I want to think about the following, which is, does this problem have some tolerance for suboptimal? And what I mean by that is, network operators in general are relatively conservative people, and I think that's justified. We don't want networks that fail all the time. So when the AI does make a mistake, when you've solved the optimal, this is the right solution. There's a lot of confidence associated with that. But if you're using a model that may be making assumptions, I don't know about you, but I often see Claude mess up some citations for me. You may have heard of, hallucinations of author names and so on. So, while this is amazing technology, we're still discovering all the different issues that it has. And I would like to use it in situations where there is some tolerance for suboptimality. And you might think that I'm imagining such a problem space, but take, for example, traffic engineering in the software-defined networking world. If you say 2 data centers are only allowed to send 200 gigs of data right now, but actually the optimal solution was 250, that's actually not the end of the world, right? Like, you could, in fact, hold back 50 gigs of traffic for the next 5 minutes, and it would be okay. It wouldn't be the end of the world. So there is some tolerance to suboptimality that I think makes some problems a little better to test with AI or to deploy AI in. And I think an example of that is traffic engineering.
Well, it's very hard to add more points after those arguments now, but just to expand what Rachi said earlier, and probably as a lengthy expansion, but one thing Rachi said, I totally agree. And I think if Keith Winston is here, he's going to have a lengthy argument about what kind of problems are not good for AI. And there are a lot of problems out there that are not good for AI. But I want to, and the key argument here is not every problem in networking are complex enough for AI to have enough room for improvement. But my feeling over the last decade applying ML in networking was I was constantly surprised by what the ML community could produce. When I graduated, it was basically classic ML models, and I applied classic ML models in networking, big data for networking. And then I was surprised by Muhammad's paper on deep RL for networking. And then I was surprised by all these generative AI models for video generation to improve video streaming. And then one of the students just gave a talk earlier about using transformer to predict network delay, because transformers are so expressive about all these complex time series relationship between packet delays. And then some of you probably realize that one line of work from Berkeley these days are arguing, you can use ML to really replace researchers to design systems, not just system algorithms, but also system programs, right? Really programs. So basically, it's not just hill climbing anymore. It's not just optimizing performance anymore. It's applying human knowledge to say which policies, which algorithms make sense, and then choose from these reasonable algorithms which one can improve. So it's more like human. So just my point is, I'm constantly surprised by what the ML community can produce over the decades.
Okay, that's good. So I'm going to maybe pick up on that point. It still feels like almost everything that's been done, to the extent they're successful, are offline problems. So we think that there is really room for true AI to be used in an online sense. And is the issue that the way in which we've architected our systems today are just kind of intended for more or less static policies? Or is the issue that we really actually don't know how to do online AI? I sort of draw this analogy with, if you think about human beings in some very crowded area navigating the space, we sort of figure it out, or animals for that matter. They figure it out. There's no one who, as far as I can tell, unless it's in our brains, there's no clear policy that at least I'm aware of in my brain. It just sort of happens. And if the situation changes, we just adapt. And I would think intelligence is something like that. So again, I think all of this work, including this work with LLMs on design, just seems to be offline heuristic optimization. So that's good, but that's not What do you think about online? So I'll start with you.
I would say just to follow up on the recent line of work on using LLM to design now or systems optimization algorithms. That is offline, of course. I think that's actually good, and even that offline optimization is good because fundamentally human need to sleep, right? Humans need to sleep. You can't optimize the system 24/7, and the algorithms can do this all the time. So whether they can make it fast enough to do it online in real time, um, I think that probably is the system for AI problem. How to make it run fast enough to run it in real time. But that probably is the second half.
I can give a quick one. So I think the pushback that we often see from people who are running networks about having some system like this run online is how do we put faith in a system that is relatively an opaque box? Like while we understand transformer architecture, we don't know which weights are firing to give us the output we are getting. But I think we have better solutions. Again, the solution comes from the machine learning side. But now we have reasoning models. So I mean, arguably, if the model makes a certain decision, we could have it reason and tell us a little bit about why it decided to, I don't know, depeer with somebody, for example. I hope that doesn't happen. But like if that were to happen, previously would be like, okay, the model messed up, but now we could essentially get reasoning traces, and that potentially is a way for us to develop more faith in debugging an online ML system.
Yeah, just want to add to that. So making AI online is not only making the decision procedure faster, but it's also about being able to stream in lots of telemetry data into the decision procedure. Because the more data you can feed, the better decision you can make. But more data meaning that it takes time to collect, takes overhead to transfer to the AI agent. So I think that's also system challenges there to think of the whole end-to-end procedure.
So maybe just one thing I'll add. I think this offline versus online, um, even for humans, like designing adaptive algorithms is hard. I mean, there are very few instances where in real systems we have truly adaptive algorithms. Like maybe on some like larger time scale of like, human intervention, we adapt these things. But generally speaking, it's like we try to design something that is, general enough that it will kind of stay it will operate well enough, and adaptation is slow. So I think that's like a kind of a more fundamental like challenge. I mean, if we have good methodologies for designing adaptive algorithm, which in some areas we do, like there's adaptive control, for example, as a field, right? I don't see why an AI designer couldn't also design like adaptive control algorithms in the same way that humans do. But it's just that if you kind of say, do we actually know how to design adaptive algorithms for all the kinds of problems that we deal with that are going to be, stable and robust and kind of reliable? We actually don't in many cases. And I think that's why we struggle to kind of make that work with AI as well.
All right. I do have a bunch more questions, some from ChatGPT, but maybe I'll open it up to the audience to see if you guys have any questions.
So I sort of have a question to both Mohammed and Rachi on their last 2 points. So let me express it in Mohammed's way, and then I'll express it in Rachi's way. So, the thing with humans, I agree that humans don't know how to solve hard problems. However, we have the equivalent of a reputational thing. So I don't mean this in any negative way or positive way, but we know that some people are better at designing certain things, or we trust some people because X is this. And as much as a mathematician, it's bad to prove by vigorous assertion, it is unfortunately how math has always worked. I don't know how to do that for AI. So when you say AIs and humans are similar, what is the reputation part of it? And to phrase that in Rachi's term, Rachi said, oh, AIs can produce explanation things. AI explanations aren't perfect either. Like we actually had a bunch of us have work that shows that reasoning models are really bad at the reasoning they produce. It's unrelated. So yeah, so I'm curious, like this idea that AI is like human, great, but what about the reputation part of it, which I think is what keeps humans somewhat honest?
I mean, I first want to say that have you spoken to your undergrads? They have Gemini, Claude, and GPT on their phones, and they use Claude for code, and they use GPT for homeworks, and Gemini for something else. So there is a reputation. Different models are good at doing different things. There is some models of reputation, and maybe we could refine that. And that's only partly joking, but I do believe there is a notion of reputation that we could have also for models, that this model is good at, let's say, doing X versus Y. So I don't know why that would not generalize also to AI.
No, that's great. I don't know what else to say. I think our assumptions about what models are good at and not good at, we have to be very careful. This is changing extremely quickly. Like, if you've been playing around with coding agents, there was a step change in December that should scare the heck out of you. It really was. Like, there's no other way to say it. Things that you would not believe were possible with AI are now possible with AI. And I don't know what the next step change is going to be, but there's no sign that like that is stopping. So I think like hallucination, these are all things that happen. I mean, reasoning may be off. But I would be very careful about assuming that what we see today is like what we're going to see a year from now. And it's kind of the reputation question is very interesting. I don't know. I mean, I don't think that I see yet kind of a world where we're really offloading all responsibility to AI. So like one way the reputation may come in is that, like the AI is a partner for humans, and you challenge it. You challenge it like, why does this make sense? You have to kind of prove it to me. And then it's through this interaction that you kind of get the confidence that this is now something that like, okay, I'm willing to try. And this again, it's very interesting because this was not possible with, before we had these language models and that interface of actually talking to them, right? So
I will repeat your questions.
Oh, sorry, I try to speak loud. So I had a question on this online versus offline dichotomy. Most of the places where things are working offline, is the advance more that we have a new optimization technique in the form of stochastic gradient descent that can do non-convex stuff, or is there any true learning going on? This may not be a networking question, but I'm just curious as to whether if it's ultimately we can do an offline search better, is there any real learning going on in that context?
So the question was, what is the real mathematical improvement in the model side to make AI for networking more reliable, more than just hill climbing? Was that a question?
Well, I'm trying to understand whether the advances are coming from a better optimization technique, some new advances in machine learning, or maybe this distinction is not important. I don't know. I'm trying to piece together this stuff from the outside.
I mean, I can try. No guarantees. When people found these transformer-based models have these massive, like very surprising emergent behavior. One way to think about it is you could say every configuration a cat is sitting in and have a rule for it, but you could never have enough rules for every configuration. If you're a cat person, you know this. You would never have enough configurations that you could. And at least this is even pre-transformers, people were like, if I don't want the, exhaustively searching for heuristics, then I want the model to learn essentially the way our brains learn that this is a cat regardless of what configuration it's in. So I think I generalized the same idea to the networking setup. This is even pre-transformers. The model is giving us the ability to understand patterns and trends that no rule-based mechanism could really specify. So in that sense, yes, I do think we get this for free from the model. And it's just that the transformers have more emergent behavior that people have figured out how to use in the language situation. And if we can harness it in the networking situation, say for packet traces or any of that stuff, that would be pretty cool. So I think that is the difference. It's not just that we are doing SGD, but there is really more to it, if that helps.
I want to expand that a little bit. So it really depends on what you parameterize before you start optimizing. Right? If you parameterize the whole thing as just a one single big neural network to optimize the metric you care about, yes, there are going to be a lot of black box behavior. You don't trust the results because it just gives you a blur of neural network weights. But I think recent research in AI for system optimization, that line of research, is more like asking AI to generate the algorithm. Not, I mean, they're not parameterizing the whole end-to-end system. They're just asking AI to generate the algorithm, and in the process of generating that algorithm, it's asking the model to reason about why changing the code or changing the algorithm this way improves performance. So it's not blindly just hill climbing anymore.
So, yeah. I kind of can't help but noticing that in response to Harry's question about online use of AI, we kind of all as a group naturally slid back into offline uses of AI, like Bob's question about who is working with AI for reputation or things. So is the answer that offline use is generally better right now, and online use maybe may happen in the future? Because from the answers that I heard, I didn't really hear anything about online use.
Professors are really good. Change the question. Say what I'm used to. What's the answer?
No, I thought I said like the problem is online is just it's hard, like with or without AI. um, no, but
React like
no, but people, that's right. But network systems, do network systems react online? So like, it's like
they are supposed to be so good. Then shouldn't it be able to react the way humans react to unknown crowd situations or navigation? We all used to navigate without GPS and sort of worked.
I think the key thing is just human in the loop or not. If you're really truly online, then you don't want human in the loop. If human is not in the loop, you must trust the AI, and people don't trust that.
Especially, is that going to happen based on the trends that you guys see?
I can only speak for how network operators, cloud companies tend
It may not even exist.
Yeah. Well,
there's a lot of it's a person who has generational essentially knowledge of running a network. They sit politely through talks about using a better model that will work online. But at the end of the day, when the model doesn't work, it's their job online. So of course, they are very conservative in making these decisions. I believe that may change. But in the near term, I think it's always going to be some version of human.
It's becoming so complicated that it may be beyond human comprehension.
So I think it have to think from the company's perspective, like where do they have major costs? Where do they have major revenue? So I think a lot of the offline problem is a lot of human involvement. So that's where they have a lot of savings where AI can replace engineers. But for online problem, AI I think is there to generate the online code, not really maybe online rules, but not really making real LM informed decision online. I think that's because today's tools are working fine. Squeezing the limit to have a little bit more accuracy probably are not what they are most interested in deploying.
So, AI is what about company sense that what if the questions that development tools that AI researchers can give us, which is not
I think that's a great question. So actually, you can kind of see in I mean this question of online, and really online is kind of about being able to adapt to unexpected situations. And this like extreme long tail of kind of situations that you encounter, which is a problem in other uses of ML as well. But somehow, you could argue that like when we look at some system like the internet, this long tail is like almost impossible to capture through any training data. Which is sort of, I think, in a lot of other areas, like if you look at sort of how people are trying to approach this in autonomous driving and how improvement has happened there. There's sort of still this perception that, yeah, we will be able to capture, get enough training data, large enough in diverse enough settings that actually we think this model is now going to be a good self-driving car. Like, it's going to be able to manage a car. I think a question sort of for networking is that even possible? I can tell you in problems that I've worked on, I've never felt that's actually possible. That you'd really be able to get like representative training data for everything. And so fundamentally, like a lot of things that hinge on some way of continual learning, which is a very hard problem in ML as well. And so I think networking have very interesting use cases for continual learning that could be useful in that.
So talking about building system to make AI better, I think today's AI still consumes the data we used to have for normal systems, still follow the steps. If we're talking about complex tasks that human takes, it's just each step AI makes it better, and still use existing tools like network configuration. All the APIs of controlling the network is also the same where before AI we were controlling. So I think there's a long way to go in terms of redefining all these abstractions to make AI really a native embedding into the system. So how can we reformat the data? So like all these problems Mohammed was talking about can be more obvious to AI. What is the right procedure to think about complex system problems? Like today, I think even in the meta experience, there are still following human runbook to do this diagnosis system. So if AI is able to access rich set of data, do many parallel experiments, what's the right diagnosis decision procedure should look like? And finally, control side, like is there a better tool interface where AI can control better, especially AI for coding this data more possible? And I think these are all good system questions.
I think that in the process of making AI the workload of this decade for us as systems and networking people, we've sort of inherited the legacy of high performance computing, and we've taken it as a given. And when I say the legacy of high performance computing, I'm thinking of collective communication, the style of bulk synchronous. We will all send our data, we will hope it arrives at the same time, and we will wait till it arrives. Is not the model that we used until I started thinking about distributed machine learning, for example. And this model works really well for HPC. It's well researched. I'm thankful that people have thought about this for decades and decades, but it's not quite, we haven't, as systems and networking community, haven't spent as much time thinking about this. And we kind of inherited this legacy. And we are now sort of grappling with the challenges of this model of communication that's, I argue, fundamentally different from how, long, short flows and that kind of stuff was in the cloud computing era. So I think that is one of the things that we, it's going to unravel for us to understand. Do we want this? How much of this do we want? And so on and so forth. So I think in terms of native communication and how we support the abstractions for AI, in terms of the communication itself, that landscape looks different, and that's at least making me think about a lot of different things.
And I can give a concrete example of the AI native abstraction. This is something I've been working on for the last couple of years. So 3 years ago, one of my students, Yuhan, she is actually on the job market these days, and she asked me exactly the same question. If all users in the future are LLM models, there's no notion of agent yet. Back then, she was saying also, if everyone is using LLM, are we still supposed to be working on text or video streaming? Right? So what is the data abstraction for AI models? And it turns out, if we believe transformers will be the future, I mean, all future models will be based on transformers, there is a unique abstraction for these models. It's called KB cache. It's basically the brain dump of this transformer model. It's basically dump everything the model understands the word about, and then it's basically big tensors. It turns out to be something the traditional system has never optimized for. It's not like text, it's not like video. It's much bigger than any big data abstraction. And people struggle to actually build systems in industry these days to cope with that kind of data. And I do believe there are a lot of system optimizations and innovations to be to be made there, not just in system building, but also abstraction. What is the right communication abstraction?
Alex.
Can I ask a very spicy question? So we're gonna take the core, like the core assumption. Okay, let's say that this is all a bubble, and the AI is bubble. Let's just say that, and the bubble bursts in the next tweet or something like this, or next month. This is why it's spicy. And we're building kind of the networks and systems and systems research directions are going towards these like massive data systems, distributed training systems that are kind of uniquely geared towards a landscape which we are assuming is going to happen. But I would argue we don't actually totally know if it will. Do you think that a lot of technological advancements in like network systems that are being made to benefit AI systems and like distributed training systems and big data, in the case that these systems don't actually integrate into our lives the way that we're assuming they will, do you think that these advancements are going to benefit the network systems research space and also industry as a whole if these things don't pan?
I just don't buy the premise that I'm not okay. So bubble will burst. Bubble will burst. Okay, will actually to me it will. But I just don't buy that the connection between the bubble bursting and the technology going away.
Okay.
Okay. I mean, we have seen so many bubbles in history, right? The technological bubbles, and those technologies still persist. They find maybe new ways to more healthy markets to grow, but I mean, internet had bubbles, right? Big data at some point had bubble, right? But the system built for these applications or these technologies still were there, flourished after the bubble bursts.
This is fair. I'm just asking just to that.
Yeah, I think I have been working on data center area for a decade now, so I don't think the objectives of my research has changed actually. Before AI, we were worried about how to provide high performance, high scalable reliability systems for data centers. And now with the AI data centers, I think what makes me excited is just its orders of magnitude requirements on the same metrics: performance, reliability, scalability. And the lucky thing with, even if it's a bubble, is that industry are investing so heavily now that it provides a lot of hardware features that we can leverage, like better computing, storage, and networking devices. I think these will be the, let's say, will still remain and makes our goal of running any type of system much faster. Actually, there are a lot of, when AI just started, there are a lot of optimizations, say, in the networking field that focus on specific workload patterns, say, as we're actually saying, some synchronous patterns, highly symmetric workload. But really, going on, these type of features start to go away, like with multi-agency, with MOE. So what we're facing is really the general workload with a lot of burstness, unpredictable patterns, but it just order of magnitude is more challenging. I think it's actually a very exciting field to be in, to solve these grand challenges.
No, I think everyone covered it. I also agree that I think that, there are these like core sort of challenges around building scalable, like efficient, networks that handle dynamic traffic patterns. And these are like progress in these is sort of very universal. Like, the context changes sort of a bit, but I'll give you like an example. I mean, when I was a PhD student and sort of shortly after, we did all this work on data center transport, and we did some work on load balancing and traffic in data center networks. And there were like there's a lot of sort of thought back then around splitting individual flows across many paths and different approaches to go about it and all of that. And so this was research, like for me, like I was working on this in 2014, 13, 14, things like that. And the reality was it was sort of like ahead of its time in many ways. Like it was not actually needed for the workloads that we were dealing with, but it was still like kind of interesting research and you could kind of pursue it. And that stuff all became relevant in a different form with AI. Now there's like all these standards for how, we're going to split traffic across many paths and deal with those problems. So I think a lot of what's being developed, like if LLMs, let's say the bubble bursts and LLMs are not the solution, as long as you believe like computation is going to kind of need to continue to scale and increase, these ideas will be useful.
So
can I add one sentence? My relatively unsexy interpretation of what we do as networking people is we are plumbers. We build the plumbing. We build it for different buildings, small buildings, large buildings, amphitheaters. But it's at the end of the day, it's essential infrastructure that makes whatever the application is go. And at this point, that application seems to be distributed ML. It could be, it has evolved in the past. It will evolve again. But yeah, like everyone said, the ideas persist.
So we'll do one more question, which I'd like to ask. And this may actually touch on the second panel that's later in the day. And this is really about, I'd like you to address the undergraduates and the graduate students in the room. Because, you use the word scary, and it's just amazing what we can do with these agents, especially these coding agents or research assistant type agents. So if you were an undergraduate or a graduate student, what should you be kind of working on if you're interested in this area? And so one obvious answer is, well, you should work on network systems infrastructure to support AI, but there's a million people working on that. A lot of companies working on that. So if you want to be a little bit, try to do something distinctive and make an impact, what advice would you give to the young people? Anyone? I'll start.
At some point, some of our colleagues in Chicago we were talking and we were thinking, what was the name of the future system? And we come up with this term called Internet of Agents. And well, if I put it that way, there are a lot of internet problems to be reinvented, right? There will be data distribution problems for agents. There will be data analytics systems for agent memory, maybe. There will be security problem as well. So I think I don't have a prescriptive answer to that problem. Yeah. So
good answer.
So I'll differ from what Hari said. Just like a million people are working on infra for ML. I think there's still a place for millionth and first. So I encourage.
There's a million people.
No, I hope not.
Every company is spending billions of dollars.
But the companies will always have a relatively short time cycle. They're not going to take the long-term view that we have the capability of taking in industry, in academia. And I still think that having that discerning viewpoint, that discerning viewpoint where, right now, let's say an example is it's a mad gold rush out there. We need more bandwidth. We need it yesterday. You build bandwidth, I will build more bandwidth. That's what we want. But as academics, we can sort of take a more discerning view of this infrastructure and say, do we actually need this bandwidth here anymore? Do we need the NVLink to be terabits in the next GTC? Do we want Jensen to stand and say, oh, it's now 2 terabits? Do we actually need this? I think as an academic, these discerning questions are things that we have the luxury of asking, even in the infrastructure space, because I think we can take a relatively longer term view and we're not really trying to make money immediately.
It seems a little regrettable that much of this work is ultimately to benefit a few small big tech companies.
Do you mean the infrastructure?
There are a lot of tech companies out there right now. There are a lot of tech companies out there right now.
Yeah, but this type of line of work, ultimately when tech enters the space and starts to make an impact, it becomes a very natural development. You might sustain 2, maybe 3. It's true for every domain that I can think about. The tech starts, and this is good or bad is not the point. The fact. So it seems a little regrettable that all of this work that academics would do would benefit, or maybe not even benefit, just track or whatever it is, but it's a small number of really large corporations that maybe it's the future, but it just seems like that can't be all academics research if academic research groups.
If we believe AI going to transform infrastructure, like it won't only transfer the infrastructure of these big companies like in schools, we have these clusters. They're going to be AI focused cluster. And there are so many companies who have to build this. And like, what's the techniques? They are something about the.
Don't you think the amount of competition needed? I mean, there's 3 big cloud providers. There's probably going to be a handful of more. There's going to be, there are 3, 4 companies. There are 2 own device ecosystems.
I think that
This goes on and on.
if there was a spicy question, Hari, that one's it, right? Like that is the spicy.
You know, it's an interesting conference. There's actually no industry papers at NINES.
Yeah.
So, but that's not true. Okay, but I'm gonna. Sorry.
With papers from Google and Microsoft.
Oh, the usual academics. This is a genuinely serious question for the group here. It just seems like in this particular area of improving AI infrastructure, I just don't see a room for like a lot of maybe there's stuff on the edges, maybe stuff on the phone we could do. But a lot of this work is simply this bandwidth thing. It's I wouldn't Google it about AI.
But my experience working in this industry, they are like much short-sighted than the CPU data center, which is moving so fast that people never retrospect and looking at the whole taxonomy. They're actually asking academia, like knowing I'm academia, they ask me this question, like what's the taxonomy? What are the design choices the other companies are making? How are we comparing with others? Like I think this kind of comparison question is actually what academia has to answer because they're so busy, they don't have time to answer them.
I think even if there were a handful of people who end up deploying this at scale, and this research ends up making their, let's say, decision better, there are scenarios where that's actually good for the world. For example, you may have heard of data centers that required power from 2 different states. Like I think that you probably heard of Colossus. That's the most recent data center. There's not enough power in one state to power this data center. And I think if we make these decisions, yes, it might help XAI, which is the company building this behemoth. Does help humankind a bit. We're not, cutting less trees for running our Codex agent. That's
we're almost at any last words.
I think I want to go back to Mary's question as a student. What area you should work on? I think we should be aware, like Mohammed saying, AI keeps growing. So every time you define a problem, think about if AI gets 10x more powerful, would your problem still exist? I think that's actually a good question to ask. But I think another thing is, as AI evolves, like what are the good infrastructure that could still work with AI together? I think that would be
I'm really sorry. I want to say one more thing because ultimately this community is driven by students, right? Good PhD students, and there need to be a sustainable way to attract top PhD students in this area, and that is one. I won't say crisis, but there is a big problem here, and I think NICE is a nice start, right? Because ultimately these students need to balance their future career and their publication during these 5 years. And if there is a path for them to publish really forward-looking papers, there's the top conference for these kind of papers, while being recognized by industry to be the thought leader in the future generation of technology in this area. That is what's missing right now. And I think that I'll say this is a good start.
Okay.
Yeah, so I mean, I think there's many ways of picking what you work on. I don't think there's any one, like you can pick based on just your own intellectual curiosity, and that's a perfectly good way, in my opinion, of like picking a research, topic. You can pick based on total addressable market, and that's a really good way of picking a different type of person. These are all valid ways of picking, a research topic. I think the maybe the advice I would give though is the world is changing very, very quickly. And it's maybe now like kind of more of it's like a challenge to stay on top of it. So I think like, what we would expect as like, research productivity, research output, like we've had this like idea, I think if you're in the sitcom community or in network systems, like, we expect like a research project, it's going to take a year and a half before you have like a systems research paper. I don't think that's actually true anymore. Not for every topic, like everyone, but there's a lot of things that you can actually do like in a month. And that's really a mindset question. Like, do you believe that you can do it in a month? Are you ambitious enough to go for it? I think like that's like for, undergrads, for people starting out, I would really encourage like, find that mindset, because I think that's actually how the world is going to be. Things are going to accelerate really fast.
Okay. So on that note, thank you guys. Thank you. We're 2 minutes over, so we're just going to get into the next session, and then we catch up during the break.
Into the next session, and we have no time. We lost 10 minutes on the AI conversation, so you're going to lose it from your break. I'm sorry. So anyway, so first paper that we have is a 4-paper session, geospatial and satellites. This is Pascal. I'm going to talk about really cool experimentation to try to see the impact and the value of obstruction and looking at LEO satellite connections.
Thank you for the introduction. I'm Bhaskar Kataria, second year PhD student at Cornell. I work with Professor Rashi Singh. Today I'll be talking about our work, what obstructed skies teach us about satellite internet. And we'll go into what are some of our interesting findings. This work was done with Mas Vintanvir and Professor Rishabh Nityanand from University of Iowa. Let's first look into how satellite internet ecosystem works. Here we are specifically looking into Starlink. So if an end user wants to connect to the internet, what they could do is if they have an access to the user terminal provided by Starlink, they can get connected to a satellite in space. And then the satellite is further connected onto a ground station, which is how they get connected to the internet using the terrestrial links. The traffic flows from the end user to the terminal, then to a connected satellite, and then finally to the ground station. And with this, users basically can connect to the internet from any part of Earth. And this can be used to provide internet connectivity in very isolated areas. It is useful for monitoring power grids in remote areas or for detecting forest fires. But in such isolated areas, it could be that they could be obstructed, the dish could be obstructed by abandoned buildings or trees. So in this work, we wanted to understand the impact on satellite internet under such obstructed conditions And during this exploration, we uncovered some interesting findings, which I'll talk about today. So so the overview of this talk is first I'll talk about our experimental setup. And after that, we'll look into to set up a baseline, we'll look into the behavior without obstruction, and then what happens when there is an obstruction. And finally, we'll look into how Starlink copes with the obstruction. And here we uncover a new phenomena, which we call as responsive routing. So I'll talk about that today. So let's first look at our experimental setup. So here we have a terminal which can get connected to a satellite. And we have an obstruction which blocks the line of sight between the terminal and the satellite. We use a metal sheet for an obstruction. And since it blocks the line of sight, we call this obstruction line of sight obstruction. And it simulates the obstruction due to trees or abandoned buildings. And for the experiments, we used a 2-dish setup where we have a test dish with which we experiment. And the test dish where we place our obstruction, it could be with or without obstruction. And we have a control dish, which is never obstructed. We keep this setup in an unobstructed area so other obstructions don't hinder our experiments. So let's first look at what happens without obstruction. And here on the left-hand side, the right-hand side here, so we have the RTD curve, and we have the curve for over a period of week. Here you can see the orange and the blue lines, which is for control and test dish. They have about similar RTD. And on the other side, we have loss. So here to show the spikes, I have on the positive y-axis, I have loss for control, and on the negative y-axis, I have loss for the test dish. And we can see that loss is again very similar. Both the dishes observe loss nearly about at the same time. And here, one interesting thing we found was these spikes are usually between midnight and morning 6 a.m. So we assume these are from routine maintenance. So what we can say is, without an obstruction, both the dishes perform similarly. And with obstruction, here we have again the RTD and loss. We can see that both the RTD, which is slightly higher for the obstructed dish, and again loss, which is also slightly higher for the obstructed dish. And since this was expected, because of the obstruction, we expected the RTD and loss to be slightly higher. But here the increase is not very much. The RTD increases by a few milliseconds. The loss also increases by a few percentage points. But here it does not affect the performance a lot. But we do see a difference in performance. And with this, we were speculating what could be the reason for this performance. Is it solely the obstruction, or could there be something else? So we've started exploring an hypothesis that they could be connected to different satellites. So for this, what we did was, since there is no publicly available information about which satellite that dish is connected to, so we used a semi-supported API to get so here to get an obstruction map, which basically shows the path of the satellite in the 3D sky, which is projected onto a 2D map. So on the right-hand side here, I show a trajectory map, which can be obtained from the supported API. And the green dash shows the trajectory of the connected satellite. So here, since the satellites are moving, Starlink routinely changes the connected satellite, and every 15 seconds the connected satellite changes. However, the API keeps populating on the same trajectory map. So we first isolate the trajectory of the trajectory map for a particular connection window. And then using the publicly available satellite information, where the information is available only for 6 hours. So we predict the satellite position using known algorithms for every 15-second connection window, and match the isolated trajectory for both the control and the test dishes. And then with this, we find the closest matching satellite. And here with the closest matching satellite, we identify the satellite. This is our satellite identification algorithm. We use it to classify if they are connected to the same satellite or not. And if they are connected to the same satellite, then we say, yes, they are connected to the same satellite. If not, if the closest matching satellite is not the same, then we say they are connected to different satellites. We use this algorithm for our later experiments. And here what we found was that in the case when the dish is obstructed, the test dish is obstructed, for over a period of more than a month, we see that in about 15% of cases on average, they get connected to different satellites. And here, note that here without obstruction, we found that about 97% of the cases, they get connected to the same satellite. So here, because of the obstruction, we are getting connected to the satellites. We are getting connected to different satellites. And looking further into how we are getting connected to different satellites, we look more into the trajectory maps. So here's the trajectory map for one of the connection windows. Here we can see that in the same for the same 15-second interval where the dish was supposed to be connected to a single satellite, there are multiple trajectories available visible on the map. Here we have one trajectory 1, and then we also have trajectory 2, which shows that we call this trajectory 1 as extra partial trajectory. And since there are multiple trajectories in the same window, we again suspected that it might be in the same connection window, it might be connected to multiple satellites. So to understand this better, for a similar connection window, where because the satellite gets changed every 15 seconds, we show that we looked at a fine-grained view of how the connection window would look like. So here in this plot, we have a routine 15-second connection window, which starts at t equals to 12 seconds. Here on the x-axis, I have timestamp, and on the y-axis, the solid lines represent the control and the test RTT, and the dots, blue and red dots represent the test loss, the loss. Here, we can see that after the satellite switch at t equals to 12 seconds, we started seeing higher loss. And then the loss at about t equals to 16 seconds, the loss keep on increasing. At about t equals to 16 seconds, the loss became nearly 100%. The RTT went up to 250 milliseconds. And right at that time, suddenly the loss disappeared. And same goes with the RTT. The RTT goes down to about 50 milliseconds, which was the usual RTT before. So here with this, we can say that at t equals to 16 seconds, it got connected to a different satellite, which is again as shown by the trajectory map that it got connected to a different satellite. Now to verify this hypothesis, we considered multiple different scenarios which could prove or disprove this hypothesis. And here we found that even after we consider all such cases, if we give precedence to all those cases, if we remove all such cases, still then in about 21% of the cases, we find an extra trajectory in the obstruction map, in the map that we see, and which basically means that in about 21% of the cases, the test dish switched the satellites during the same 15-second connection window. Moreover, now we just saw that the test dish, which was obstructed, it switched the satellite between the same 15-second connection window. But another interesting thing that we see was it first it got connected to the same satellite and then switches. So here is the trajectory map for this phenomena. So here we have again the trajectory map from test dish and a control dish. In the test dish, we have trajectory 1, and in the control dish, again, we have trajectory 1. Here we can see that the trajectory 1 nearly overlaps with the trajectory 1 of the test dish, nearly overlaps with the trajectory 1 of the control dish. And here with this, we can see that they both are getting connected to the same satellite in the same region before the test dish moves away due to an obstruction, and which is represented by the trajectory 2. And we again did a similar analysis. So here, in a relaxed classification scenario where we don't give precedence to all such, we don't give precedence to other measurement discrepancies, we see that in about 67% of the cases, both the dishes initially connect to the same satellite before moving away. And even with a stricter classification, where we give precedence to all such measurement discrepancies or other hypotheses, we still see that in about 25% of the cases, both the dishes connect initially to the same satellite before the obstructed dish moves away. To conclude, in this work, we measured the end-to-end satellite antenna performance under obstruction, and we find that under obstruction, the performance degrades, but it doesn't degrade a lot. We uncovered that the satellite ecosystem, they are advanced enough to cope with the obstruction by switching satellites. And moreover, we found that since this is a good thing that they can cope with the obstruction, But we also found that despite the long-lived obstructions, remember that we conducted the experiment for more than a month. And despite that long-lived obstruction and the ability to switch satellites, the mechanism is stateless, and they react they operate reactively instead of reacting proactively, where they could switch the satellite and users can get a better performance. Thank you.
All right. Everybody wants to go for the break? So. Quick question.
Yeah.
So, out of curiosity, has anyone approached, I mean, SpaceX has a monopoly over this setting. So unlike other settings, like when you want to ask Google about what they do in the data center, not a huge competitive disadvantage for them to answer our questions because no one else can replicate this entire thing anyway. So has anyone gone to them with this argument and said, why don't you open up? We'll be happy to solve lots of your problems for free. You know, and
so one of our co-authors is at Starlink, but I don't think I don't think they would prefer to comment on this.
Can I add a little bit of so one of the second author paper graduated and went to work for them. They are aware of this paper in the sense they like enough to hire the guy. As for how open are we to talk about this research and its implications, I've had a conversation with people with their cameras off for an hour. They have all kinds of ITAR regulations. They really are not chatting much for what it's worth. But they are aware of the work and they don't seem to.
I work with Starlink, but I work with them through NDA through Netflix. So their cameras are on.
But they do you made it.
But they do read this work. And it's on their queue for solving a lot of these things, but the system is just very complex. They're in it for making money right now. That's the priority.
no, it's more a question of like some level you're doing a lot of inference of things and making a lot of guesswork about APIs and what this information actually means. That type of information, like, oh, why not just say, oh, this is how you get tell.
Yeah, there's no
what satellite you're connected to. This is what
you could actually a couple of years ago they did exposures. And when they realized they shut that information down. Yeah, there's no incentive. I mean, that's why it goes to the monopoly question, right? Once you get other players, there will be an incentive, but there's not.
No, but I'm actually saying a monopoly is easier. I would argue.
Not
anyone that's not a monopoly always does that. Yeah, I'm gonna tell you anything because the competitor will copy me.
But if you are a monopoly and open it up,
yeah.
The key selling point is that having a bunch of rockets. I mean, that has nothing to do with this stuff. This is off topic, maybe. Let's probably go to the next one.
Thank you for
All right, let's. I love that. But we need to move to the next paper. So Tara is going to keep talking about satellite, but this time satellites and ML, in case you were missing that.
Hi, everyone. Today, I'll be talking about orbital brain, how we can harness training in space. Over the last few years, we've seen a growth in the resolution that these photos take. As you can see, they're used for a plethora of different applications, from agricultural monitoring to forest fire detection to even flood detection. And increasingly, the resolution of these photos continues to increase. For instance, Planet, on their newest generation of satellites, is rolling out 1 meter resolution, and now they're even launching with NVIDIA GPUs. And so over the last few years, we've seen an explosive growth in the amount of data captured. Now, more and more satellites are being launched, and each one of these satellites is starting to take more and more photos a day. So for instance, now their satellites are taking nearly 25,000 photos in a day. And each one of these images is also becoming larger with the increasing resolution and more spectral bands that are being captured. If we look into how these satellites work, how it happens is that the satellite is rotating around the world. And as these satellites start to rotate, they end up taking photos. And once they come into contact with the ground station, they start to downlink all of these images. However, this downlink bandwidth ends up being extremely constrained. And as a result, not all the photos that these satellites take can actually be downloaded. And if we look at a larger constellation, you can end up seeing that the problem continues to increase. And so this core bottleneck is that the image sizes explode the pipe. Even currently, these satellites can only take about 10% of their possible photos that they could even capture. And even if we assume some compression, this only comes out to around 30%. So now we come up with this interesting question of, can we do everything in space? Now, this might seem like an outlandish question at first, but hear me out for a second. Recently, we've seen a plethora of papers which have pushed the ability to run inference and to run models in space. So now we ask this natural question of, can we even train in space? Can we just train the model in space and just not even download any photos? And there's a few motivations for why this is possible. One, we're increasingly seeing more and more compute in space. Two, we're seeing inter-satellite links are now feasible. Three, all of these satellites, as we've talked about a lot, are run by one single commercial entity. And four, satellites are extremely predictable. So let's get into each one of these in detail. One, we're increasingly seeing more and more compute in space. So all of Planet's newest satellites have NVIDIA Jetson GPUs, which are small mobile GPUs. Increasingly, they're even testing out H100s on their latest launch. Similarly, ISLs, or inter-satellite links, which allow one satellite to directly talk to another satellite using a laser link, are now becoming more and more feasible. If we look at the amount of ground-to-satellite connections possible, you'll see that on average, there's only around 10 to 20 connections per day that are even possible. And whenever we take in energy constraints, this only drops to about 5 to 7 per day. However, if we look at the amount of satellite-to-satellite connections possible, since they can just directly communicate with each other, you see that they're on the order of 9 to 10,000 possible connections. And even if we consider energy, it's only around 6 to 7,000. And similarly, if we look at the amount of bandwidth capable, you'll see on the x-axis here we have the bandwidth, and on the y we have the CDF. You can see that while on average downlink and uplink is larger, inter-satellite links also have the capability to have more communication because they're closer to each other and don't have to downlink all the way from space to Earth. Similarly, you can see that satellite orbits are more predictable. Since each satellite has to follow the fixed direction of the Earth's orbit and is governed by the laws of physics, you actually know ahead of time, by about 6 hours, exactly where the satellite will be to a few kilometers. And because of this predictability, you can also predict downstream things, such as how much energy the satellite will consume. So that's simply a function of the satellite orbit. And you can also predict basically the link quality of the satellite to ground station to a few dBm. And we can use this in our future scheduling algorithm. Similarly, there's an energy budget, which is, since you're having to downlink all of the data from space to Earth, downlinking takes around 50 watts, while the GPU only consumes around 7.5 watts, even though the solar panel can only produce 7 watts. And so then we get into orbital. So then we get into orbital brain, where we have 3 actions. And in each window, each satellite has to choose one. A satellite can either do local compute, it can either aggregate models across satellites, or it can perform data transfer. So let's first get into our architecture of how we make this all possible. So we assume a cloud that runs the scheduling algorithm. This is consistent with how satellites are currently scheduled. We use ground stations as relays to basically communicate from the cloud to the satellite, and then satellites just simply execute the schedule that's created. So if we look at this data flow, the ground station will send the compute schedule and the data model transfer schedule, and then the satellite will send local updates back to the ground. And between satellites, they'll communicate directly. So then if we look at our actual scheduling framework, which runs on the cloud, we first run a satellite performance profiler whenever the satellite comes into contact. 2, we formulate model aggregation. 3, we formulate data transfer. And 4, we execute the schedule. So let's go into each one of these steps. So first, the performance profiler is when the cloud collects all the statistics that the satellite sends down to the ground. That's stillness, basically when was the last time the satellite had their model updated, how many samples has the satellite trained on, what's the predicted compute, and also what's the last observed loss. So let's first get into how we actually use these. So there's the compute utility, which is when local compute is most valuable. And this has to do with, basically the idea is that when a satellite has more energy and newer samples, it's more beneficial for the satellite to compute to just train their model locally. Then we get into this idea of when is model aggregation, or MA, more feasible. And the idea here is that we want to use ISLs, or inter-satellite links, to keep models fresh. And the idea is that satellites which haven't had their models updated recently should sync with their neighbors. And so we have a formula to basically measure the amount of quality and utility gained by model aggregation relative to local compute. And the idea is that we want to benefit satellites which haven't had which have a very old model to be updated first. Then we get into this idea of data transfer, which is that we want to fit non-IID, basically unlabeled samples at the source. So the key idea is that each satellite has a fixed orbit. So as a result, recently, some satellites might have just gone over, say, a forest, whereas other satellites might have just gone over the ocean. And as a result, they end up having different label distributions. So if they were to be locally trained, what would end up happening is that you would end up wasting wasting energy to train a local model, which would end up being very poor. And so we want to fix this using ISLs. And we can do this because it's a single operator constellation. And so our first step is that we want to quantify this imbalance whenever the satellite comes into contact with the ground station. So as you can see here on the x-axis here, we have the number of labels per satellite, and on the y-axis, we have a CDF. And you can see that very early on, for example, after 1.5 hours, the satellite ends up having a very skewed distribution, which ends up being fixed over time. So we want to balance this. And so how we do this is we quantify that given every possible pair of nearby satellites, what would be the distribution if both of those satellites shared data with each other. And then we finally schedule based on the relative value of transferring the data versus simply local training. Then we get into our experimental setup. We use TLE traces that planets produced. We have some link modeling and directly released from Planet. And we also use energy and storage that Planet has all released. And for training here, we'll show results for FMOW, which is one of the biggest satellite classification tests. There's also other tests still in the paper. If we look at our final accuracy after 25 hours, you can see that Orbital Brain is able to achieve a higher accuracy than bent pipe, which is the normal way of downloading data and then training in the cloud. And you can also see two other training in space, async FL and Fed space. And you can see that relative to bent pipe, Orbital Brain has about a 5% increase with Planet's constellation and about a 9% increase with Spire's constellation. Now, while this training accuracy might seem relatively small, the time to produce this training difference is much larger. So for Orbital Brain, it takes about 1.55 the time for bent pipe than it does for Orbital Brain to achieve that same accuracy. Awesome. Thank you.
So I'm a little bit confused about something. So there's another paper at NINES, which unfortunately is not being presented in this pod, but this paper is from Berkeley with Google co-authors, where you are an MIT person with Microsoft co-authors. That paper claims that it is actually better in a self-driving car context to have a much bigger GPU, which is running in the cloud, and offload the compute from our tiny wimpy GPU, which is in our car, to the much bigger GPU that is running in the cloud somewhere. You seem to be making in this paper the opposite argument, that it is better to have full resolution images on your wimpy GPU, which is in the satellite, rather than sending. So are these two papers in conflict? Is one of them wrong? Are both wrong? Are both correct? Like, what's happening?
So we actually show in the paper that the best is so we actually show in the paper the best is combining both approaches, where you do most of your compute in space and then you do some additional compute on the cloud, especially for harder samples. So I would say they're both partially correct, and I think both approaches can exist together.
Quick testing setup or email setup question. Since a lot of this relies on like intersatellite links, in your simulation or whatever your system, how many satellites were you assuming that you have in your constellation?
I think Planet at the time was 200, and I forget the Spire number on the top of my mind. Yeah, awesome.
Have you growing like any performance like strategy so far? Because I feel like you're talking about like the energy budget is very like important for like intersatellites, and like if you don't have like photons, it probably will be like tragic on the.
Yeah, so we show in the paper that you can still achieve satisfactory performance if you just use a fraction of the constellation. So if you use, say, 50 or 70% of the constellation, you can still achieve satisfactory training rates.
So thank you for your talk. My understanding is when you say model aggregation, what you do is you individually train a model using data that's only collected on one, and then you somehow synthesize two models to create a third model. Is that correct?
Yeah, you basically, you average them out.
So this is different from how distributed training normally works, where you collect gradients from a unified data set consumed from all of your different edge sensors or whatever, and then you apply like one step at a time to all of the models. So is there a limitation in the satellite context that prevents this from working? Like instead of training a model and then like merging it, you effectively collect and share all your data, and then everyone sees like gradients for their particular data set, and then you can update them all.
I'm not sure. Aggregation is very common in, say, more federated learning contexts, which is very true for a lot of different scenarios.
Okay.
I think, yeah.
Okay. I did have another question, if that's okay. Okay. So do you know what the difference is? I guess. Okay, sure. Go ahead.
Right, once again, he's going to talk to us about OpenFlame. This is a naming system for spatial computing. It's a great paper for the next paper.
Just swap this right I just use the swap state. Yeah.
So you don't have to disconnect if you just button on your computer. Disconnect.
Hello, everyone. Sorry for the interruption. I'm Sagar from Carnegie Mellon University. I'm advised by Srini and Anthony, both of whom are here today. I'll be talking about a system we are building at CMU called OpenFlame. And as part of this talk, I wanted to demo some tools and applications, but turns out screen mirroring is not cooperating with me. But I do have some demos, and if you want to follow along, you can go to our website, which is open-flame.com, and you can try them out yourself and follow along if you want. And we have a hyphen in the name because we could not get openflame.com. Okay. So let's say there are autonomous robots that deliver food from restaurants to their customers. And in this case, let's say it has to deliver food from a ghost kitchen in Pittsburgh downtown to my office at Carnegie Mellon University. It would be nice if this robot had access to a map that could help it navigate from the ghost kitchen to my office. And of course, there are already maps today. But today's maps, like Google Maps and Apple Maps, answer only a part of the problem. So for example, here, they know where the ghost kitchen is and they know where Carnegie Mellon University is, but they do not know where the pickup area is within the ghost kitchen or where my office is within Carnegie Mellon.
That was just one example, but there's a wide range of applications that we call spatial applications that tie their data and logic to physical spaces. For example, augmented reality, inventory management, facilities management, and so on. As part of the systems community, we believe that we have to start building the underlying infrastructure that makes developing these applications easier. And such an infrastructure would host a ubiquitous map or a map that spans across indoors, outdoors, private spaces, public spaces, etc. So why are maps today not ubiquitous? First of all, because indoor data collection is hard. It requires a huge manual cartography effort. And also, to make things worse, many indoor spaces are private and they're also dynamic. Now, you might say crowdsourcing indoor data is a solution to all of these problems. And you would be right. Crowdsourcing is a way to improve coverage of maps. But however, crowdsourcing on a central system, we believe, is not the right way to scale because businesses would not want to arbitrarily expose their indoor map data due to privacy concerns. And more importantly, like Dave Clark told us a few hours ago, we should not be building systems that centralizes power. And our solution is to build a federation of maps, or in other words, a system where independent organizations maintain maps of their own spaces. For example, in this part of Pittsburgh, the Target building here could have its own map hosted on target-maps.com. CMU could have its own map, and so could a museum. And public spaces like roads could continue to be maintained by organizations of today like Google. Now, this looks just like the web today, where different organizations participate independently in the system. But the web has the DNS that associates names like google.com with servers. And we need a similar system for the physical world that associates regions with map servers. And that is what OpenFlame aims to be. The DNS for physical spaces. OpenFlame provides the discovery mechanism to identify maps in the current location. And it also provides a protocol so that applications and devices can talk to these maps and get services from them. So the fundamental unit of OpenFlame are what we call map servers. So a map server is a system that stores map data of a region and also provides services on top of this map for applications. Services like search, routing, etc. And these map servers are maintained by independent organizations. The OpenFlame client that runs on the device alongside applications uses the discovery service to identify maps that are hosted at the current location and then obtains services from these map servers for the applications. So I wanted to show you a live demo of visualization of maps, but you can try it out yourself on your computers if you like. But here I'll just play a video and talk through it. So this is a visualization application, a map visualization application. The bar here on the right shows the list of maps that are currently discovered in the current users. So Google Maps, for example, is already discovered because it has coverage over the entire world, right? And now if we zoom into one of the buildings on CMU campus, we see that several maps that are specific to CMU get discovered here. And if I reduce the opacity of Google Maps, we can see the inside of CMU campus. Yeah, thank you. That's the reaction. And so these maps are being streamed from map servers that are hosted inside CMU campus. And if I go to a different part of the campus, we see that a different set of maps are discovered. And the advantage of federation is that each of these organizations can implement their own access control mechanisms. So for example, here I go to incognito mode and I open the same map. And when I zoom into the CMU campus, we see that CMU map server is discovered. But however, even if I reduce the opacity of Google Maps, we cannot see inside the campus because we haven't authenticated with the CMU map server. And in this case, only users who have cmu.edu ID can view these maps inside CMU. Yeah, so that was the demo. Okay. So the visualization application uses the visualization service that is running on these map servers collects 3D representation of these maps and then renders them on the client. Right? But how did these map servers get into the system in the first place? Of course, they should have registered themselves with the discovery service at some point for them to be discoverable by applications. For example, a straightforward way for CMU Computer Science Department maps to register themselves with the discovery system is through a centralized registration process. So there could be one trusted entity that is collecting all of these registrations and building a world index of maps. But of course, this would be a huge bottleneck and it would severely impede the growth of the system. So when we think of administering physical spaces in the real world, we usually do it in a hierarchy of delegation fashion, right? So when there's a large authority that is controlling a large space, like the whole country, for example, divides it up into smaller units like states and delegates the responsibilities of these smaller units down to lower authorities. So we use the same concept here. So CMU CSD maps, for example, can register itself with the CMU zone, which is maintained autonomously by CMU. Now, if there is a different map of CMU water pipes that the Waterworks department wants to maintain, it can do so in its own zone that is independent of the CMU zone. Now, notice that both of these zones have a lot of overlap between each other, and that is totally valid. And both of these zones could be registered under the city of Pittsburgh zone, which could be under the US zone and global zone. And world scale providers like Google and Apple could be registered directly with the global zone. An important thing to remember here is that all of these map servers and map zones can have a lot of overlap between each other, right? So as a result, let's say there's a device within the CSD department that is querying for maps around it. OpenFlame has to discover all of these overlapping maps that I show on the right that are across these different zones. And another important consequence of map zones overlapping is that these branches that you see in the hierarchy, they're not exclusive, unlike in the real world. So let's say CMU has a quarrel with the city and city evicts CMU out of its zone. CMU can always register its zone with the US zone and OpenFlame will discover it as if nothing happened. Unfortunately for us, this structure is very similar to the structure of DNS, right? So DNS follows the same structure of delegation and hierarchy like we do. So we implement our map zones as DNS zones, and we implement pointers to map servers as DNS records within these zones. And the advantage of doing that is it immediately unlocks the world scale deployment that DNS has, including their caching mechanisms, including its CDNs, etc. And it gives us a way to bootstrap the system without building the whole infrastructure from scratch. But of course, it's not all rosy because DNS does not support location-based registrations and queries off the bat. And also DNS does not support overlaps, right? DNS is very exclusive. Case in point being open-flame.com. We could not get openflame.com. So in this talk, I'll just give a basic intuition for how we solve these challenges, but you can always look at the paper for more details. So first, let's look at how we solve discovery, DNS-based discovery. So going back to the map visualization application that I was showing, the green polygon here is the part of the map that the user is currently looking at. So to discover all of the maps that are registered in this region, OpenFlame generates these domains that we call geodomains that collectively represent this region. And a discovery query basically involves launching all of these DNS requests in parallel. And we generate these geodomains using a spatial indexing system called S2. S2 divides the world into hierarchically organized square cells, like we show here. So registering a map on DNS involves generating a zone file that represents the coverage of the map. And we have a tool to automate this process. And I'll play the backup video that I have here. So registering a map, someone who's registering a map basically draws a border, a rough border around the region that they want to register. And once that is done, they can generate S2 cells that cover that region and then enter all of the details that are required for generating the DNS records and generate the zone file. And the zone file that is generated can be hosted on any existing DNS server without changes in implementation. We have also built several location-based or map-based services that spatial applications can use. So for example, the search service here takes a user's entered string and searches for it in all of the maps that are currently discovered. So for example, here, you can see a result from Google Maps for CMU, and that is for the whole campus. And when that is selected, we see that it zooms out into the campus. And now when a string that is specific to CMU campus is entered, for example, here Gates, we see many results that are specific to CMU maps, right? And when one of those results are selected, it zooms into the specific part of the map that has that string. And this is an example for Arena Labs, which is a part of, which is a lab that I'm part of at CMU. This is an example of routing service that is running on an individual map. So this is the CMU map, for example, and then this is routing service that is running on a map where we have removed CMU and University of Pittsburgh maps. So this map knows how to navigate from one campus to the other, but does not know the internals of these maps. And this is the routing service that is running on a federation of all of these maps. Okay. And this is an augmented reality application that is running on OpenFlame that uses its localization service. And of course, we have more details in the paper. We talk about security. We talk about feasibility, give some preliminary results on feasibility, and also how DNS records handle overlaps. Yeah, that brings me to the end of my talk. Thank you.
One question about security. How do you decide who has the authority to take delegation over a spatial region? If I'm operating one of these DNS servers, anybody could come forward and say, I control this space, I should be the right person to provide you the map data. What framework for the authentication with all of these principles would you propose?
Yes, so that is exactly the reason that we support overlaps, because we do not want the system to make a decision on who is responsible for that space. So anybody can say, oh, I have authority over this space, and then set up their DNS servers for that space. And we think that the actual decision of who has authority over that space should happen out of band, should happen out of the system. And we believe that, you know, the way that we think or we envision that this is going to develop is just like the web, where, like, you know, people can host and maintain their own data, and that's all federated. But then, you know, there are like search engines, and there are blacklists, whitelists, etc. And those are the things that actually make decision for, what is actually exposed to the user. So we believe that, you know, the spatial world will actually evolve in a similar direction.
Right. Thank you, speaker.
Thank you.
Sorry, not all. Charlie, oh my. So I think there's a collaboration going on here between the last paper and this paper. You'll see it connects there.
Hello. Oh, okay. Hello, I'm Charlie. And I'm Om again. Today we'll be talking about scalable routing in a city-scale Wi-Fi network for disaster recovery. As we've seen over the last few years, the internet is becoming overly centralized. Now, across the whole entire world, there's certain few points which serve as a connection to all of the world's whole entire internet. Similarly, if we look at the nation level, you'll see that only a few cities have started to serve as critical junction point for all of our nation's backbone infrastructure. If we zoom into the level of a single city, you'll see that there's single points of failure, where if any of these few places were disrupted, all of the city's internet connection would get disrupted within a whole, would get disrupted. And we've seen over and over again these sort of outages happen, from whole entire regions being disconnected from the world to service providers having outages. And these are due to a multitude of different reasons, from hurricanes and climate change to war and conflict to even routine network upgrades like Rogers, which actually affected Charlie here. However, in so many of these cases, power remains intact. For instance, during Hurricane Helene, many users reported that while their internet was disconnected, their power either remained throughout or was very quickly restored after the hurricane. And it's because of these sort of network outages that we came up with the idea of DFNs, or distributed fallback networks. The key idea is that in these cases of network outages, can we use existing Wi-Fi devices, existing access points, smartphones, laptops, all sorts of different technologies to serve as a fallback network in cases of network outage? And to do that, we present the first realization of this idea called CityMesh. It's a citywide it's a citywide, within a city, fallback system, which uses the millions of devices that are already present in a city to act as a sort of mesh network. This is great for low latency, low bandwidth applications such as instant messaging or 911 communication. And in this talk, we're going to show how we can achieve high deliverability at scale. We'll show how we can get nearly 88% higher than prior works using this idea of a map-driven computation. We'll show how we can do ultra-low overhead. We'll show how we can get 6 to 1000x lower transmission overhead than prior work by suppressing transmissions. And we'll also show how we can maintain a compact routing state, only needing a few kilobytes for cities with millions of devices. Now, this, as many of you might know, this is a very age-old problem that people extensively worked on in the late 90s and early 2000s. And the key idea that most of these works followed is one of two main approaches. One is topological routing, in which devices use sort of control messages to bootstrap information between each other. However, this ends up sending a lot of control packets and is simply not scalable to a large number of cities. There's another approach called geographic routing, in which nodes use their position to inform their decisions. However, this requires extremely accurate positioning. And as we'll show later in our results, even today's state-of-the-art devices, after decades of localization research, still end up having a location error, which makes these protocols infeasible. And so in order to do this, we have this idea of city mesh, which is the idea of can we route via buildings? We change the problem from routing from device 1 to device 2 to routing from building 1 to building 2. And we're able to do this because unlike nearly 20 years ago, we now have accurate maps, as I'm sure you just heard in the last talk. And in our protocol, the devices only need to know what building they're in. They don't need to know where they are in that building. And to demonstrate the feasibility of this approach and to walk you through the steps, I will hand it over to Charlie.
Thank you. So we're taking a map of a city, and we have the shape and positions of those buildings, and all of the wireless devices are all over around in the buildings. So we're able to hop from a wireless device in one building to the other building. This allows us to route not at a device level, but we're able to route at a building level. Let's forget about devices. Let's just look at building shapes and all of the positions of the building. And we can connect nearby buildings within the transmission ranges of a radio. So yeah, we have a building graph. So now we have a graph. We need to find a path. And we have a source building here and destination building over there. And a very naive way to do this pathfinding, well, shortest path, right? And we're able to get a path with minimal number of hops. But this is very risky because packets over long distance, you lost it. And so we design a new path cost. We are taking the distance d between buildings, and it's very simple. We raise it to power of k. And as you can see, if we raise the value of k, we're going to take a very conservative, but it's very safe path, so we're not losing a packet. And now, since we're hard coding off the buildings in a sequence, so what if the packet just got lost? And we observe it a lot when the packet is going from one building to another building. Let's say here, the building in red, the packet is lost at its way to the building in red. And the traditional protocol usually solves this problem by link layer retransmission. So it just keep retry until it gets through. But City Mesh leverages the fact of this transmission. This transmission itself is a broadcast. So not only this red building hears it, like all the devices in other buildings all hear it. And we define something called a conduit here in yellow. And it is a geospatial fence where it defines the area where all of the device and buildings in this area are welcome to participate. So say here, the red building still didn't get it, but we have a building green on the right-hand side and it make it through. So basically, the entire path will be constructed by the conduit. And definitely you'll figure out that we might have all of the buildings, all of devices in the conduit transmitting, and it will induce a lot of transmissions, but we do have some suppression technique. We have actually two. One is in building, one is inter-building. We have it in the paper, but we don't have time to go over them for this talk. In the eval study, we'll show that we're able to reduce the number of transmissions close or even lower than previous state of the art, like those geographic routing. And then as you might notice so far, we have to encode all of the path in the packet header. So it's a huge sequence of building. And this might be too large for us and impractical as a packet header. But we do observe that the path is mostly straight, and then there are some turning point in the path. So we place those waypoints at a turning point, and we encode the waypoint in a packet header. And at the end, what we can do is to reconstruct this path with the conduit by connecting conduit in between the waypoints. And this actually, we did some measurement study, and it gave us around 4x compression over the header. However, the city have different size. And over a larger size of the city, even with 4x compression, it's still too big for the packet header. And what we really want is a packet header that is invariant of the size of the city and it stays constant. And something we can think about is, can we just build a routing table and we just pre-compute all the path for all the building in the routing table? But the problem here is all of the buildings are potential destinations. You'll end up having a routing table with maybe 1 million destinations. And then the way we solve this problem, we introduce a new addressing scheme. We are dividing the city into 4 grids, and we pad them with their prefixes, and we keep doing this subdivision and we keep padding it until some minimal grid where we call it a cell. And now a building will have a new identifier, a grid ID, where the first part of it is the prefix on itself, and then we'll have a unique ID to identify the building in itself. So if we apply this new address scheme to let's say to this example, we'll see that for most of the destinations, they usually share the same next waypoint. So we are able to condense this routing table just like how we are condensing the IP routing table by condensing it to a prefix. Although the prefix here is not IP subnet, but right now the prefix will be the grid prefix representing a certain grid. And we'll show in the eval study that we're able to get a very, very, very small routing table, even for a big city with like millions of buildings. And then I will hand it to Om. He will step you through the eval session.
Great. So just to summarize what we've talked about before, as of now, we have 6 large steps. One is we first create a building graph. Then we run a path computation on that building graph. We then add a geofence conduit redundancy. We then compress this using waypoints. And then we make the packet size constant using the routing tables. And then we also have a 6th step where we do suppression, which Charlie briefly talked about, which we describe in the paper. Now we get into our simulation results. We simulate 70 cities across 24 countries and 6 continents. Sadly, there was no penguins here. And we use OpenStreetMap for all of our map data. And we also add a random localization for error from -15 meter to 15 meter. We measured this using the latest iPhones and Android devices and observed that this is the average precision that they can achieve. So then we get into our main result, which is the delivery rate and transmission required. Here on the x-axis here, we have the average number of transmissions per packet. And on the y-axis here, we have the deliverability, the percent of packets which were able to be successfully delivered. And you can see that the top left is better. We'll first plot all of the cities under 10K on average. You can see that CityMesh is able to achieve the highest delivery rate with the lowest number of average transmissions relative to Weave and GPSR, which are prior state geographic protocols. We see a different trend whenever we look at the 10K to 100K, where CityMesh is able to achieve the highest delivery. Weave has slightly less transmissions because it terminates very early on. And we see this trend continue throughout up to nearly cities with 2 million devices, where CityMesh is able to deliver about 40% of packets. While this might seem bad at first, this is actually fine, because this just means on average devices have to transmit 2.5 times. We'll similarly look at the routing table sizes. We plot the routing tables of our 4 largest cities. On the y-axis here, we have the number of entries, and on the other one, we look at the amount of storage that each device needs. You can see that at max, you only need about 11 kilobytes to store data for a city with 1.4 million buildings.
This was great. By abstracting away a bunch of details and getting the building graph, is there something that we've lost? Like I'm thinking about fault tolerance. When a router goes down, all the other routers today on the internet, they have a link discovery process. They'll figure out what the new graph is and compute the routing table. Guessing the building is not burning down, hopefully. So then how do you get that behavior when you have a stable graph?
So the key idea is that we have that conduit, which can basically act if, let's say, one building is down, a nearby building could pick it up. And we've,
Yeah, and then definitely in the path cost, like you can define the path cost here is more like a framework. So these days the map is really powerful that you can even check the material of the building. And you can define different path costs. And since the routing table size is really small, right? So you can define a couple different routing tables and then you can switch between the tables to explore different ways to route between a city.
It's great to see people using geospatial information for routing. It's great. I wanted to ask, it's a sort of related question, like how online is the computation of the routes and how do you decide what the width of the conduits is? Because for example, you can imagine if you're in an office environment, maybe it's a desert for a big part of the night. It's not MIT. So, you know, like, I guess you're assuming, well, there'll be base stations. There'll always be something there or something, but this also relies on people who run corporate networks, like choosing to enable and allow like their devices to be used. So I guess what I'm asking is, how offline does the route computation really need to be? Are you assuming it's more or less offline and the conduits just handle everything?
Yeah, so all of the assumption is that since buildings change at a very slow timescale, you can actually pre-compute ahead of time all of the routes. We show how to make this feasible in the paper. And in terms of the deployment, what you'll see is that nearly all of the access points are governed by very few providers. For instance, Cisco is the majority. So they could definitely feasibly deploy something on all of their routers, for instance.
Does the customer have a choice?
No.
I mean, this is the social goods for the best.
All right, sorry guys, we're gonna have to stop here. We have 5 minutes of break and then we have a panel. Right.
Bruce Maggs. So Bruce is a professor at Duke. He's worked for Akamai and Emerald. He has a Wikipedia page. You can read a lot about it. My favorite Bruce story is he once drove me to the airport. It was a terrifying journey for me because I was worried they wouldn't let me board the plane. I still remember that conversation as one of the most fun conversations I've ever had in a car ride. So, really looking forward to this. Let's hear from Bruce.
Thanks, Panda. Oh, is this on or does it matter? All right. Yeah, so I was invited to speak, and at first I had a little trouble thinking about what would I talk about because I've sort of recently resurfaced from being down in the trenches at a startup called Emerald Innovations, and I've done this twice in my career. I took time off. I kind of stepped away from the research community and joined a startup, which I encourage you all to do at some point in your career if you can. Many of you have. And so I think some of these stories maybe will sound familiar. And Hardy said, why don't you tell some war stories? Well, that's easy for me to do. I can tell funny war stories, but then I thought I should try to add some socially redeeming content. So for each war story, there will be one or more engineering lessons or a moral of the story that it should be apparent. Sometimes somewhat contrived, but we'll see. I'm going to give you a one slide introduction to a content delivery network. The first startup was Akamai Technologies, where I was the first head of engineering. And in a content delivery network, you have these servers all over the world. And when clients go to visit a website, they send requests to download content from these servers. And if the server has the content in the cache, it gets sent back to the client. Or if not, or if the content's uncacheable, maybe the request gets forwarded to an origin server, which then provides it. And I don't know, maybe even sometimes there can be some misdirection to try to improve on the default path by using the CDN servers as an overlay. That's CDN 101. And I actually, after my full-time stint at Akamai, I stayed there for another about 20 years. And I left in 2019, but at that time, these were some of the, propaganda statistics, which I think are still mostly true. It's a large scale, and it was like kind of roughly doubling every year or two. So I'm sure it's much bigger now, but CDNs are a major component of internet infrastructure. I don't think this audience needs too much more introduction than that. So let's talk about some stories from the early days. So Akamai is an MIT spinoff, and I was lucky to have been on sabbatical here at MIT in fall of 1998 when Akamai started. And we outgrew our office space first here, and then temporary location. And then finally, we moved to a much bigger office 2 blocks from here at 201 Broadway. We got in at midnight when our lease started, and we started setting up a demo, a rack of servers, because we had a big investor that was going to come on December 2nd. One thing we didn't realize was the racks. We didn't know anything about racks. We bought racks that were meant to be bolted to the floor. And that was a big unhappy surprise when we unpacked them. And we had to go out at 4 in the morning and buy 2x4s and try to build a frame. But anyway, December 1st, our first day in the new office, the internet service provider didn't show up to connect our network. And this looked really bad. We're telling people we're going to revolutionize content delivery on the internet, but we're not actually connected to the internet. And I kind of vowed, like, we may fail, but we are not going to fail because we don't have internet connectivity. Okay, we're going to have internet connectivity. And at that time, we couldn't rely on an emergency citywide overlay Wi-Fi network because there was no Wi-Fi. Okay, the technology of the time was called NCR WaveLAN, and I knew a lot about it because I had been a hobbyist at Carnegie Mellon and built a wireless network connection from campus to my home. And I ran around the old NE43 building and I cobbled together 3 WaveLAN network interface cards and some old PCs. And I went over to Akamai and I set up an antenna there pointing to building NE43 here. And the performance was terrible. It just wasn't going to cut it for a demo. And then I had an idea. It involved the Draper Labs parking garage, okay, which is 1 block from here. My idea was put a relay station, kind of like the citywide Wi-Fi emergency recovery network, on the roof. So then I don't have a car. I borrowed a car. I took the battery backup from our file server at Akamai, and I put 2 network interface cards in an old desktop, and I pointed one. Well, I pointed one at Akamai. I pointed one at NE43, and I went up on the roof. This took a long time, right? This was, by the time I got all that stuff set up, it was about 4 in the morning. And I didn't have a cell phone yet either. I borrowed a cell phone, and I'm driving around on the roof of the Draper Labs lot, talking to an engineer at Akamai and asking him to read packet losses. And he's like, 50%, 50%, 50%. I was getting really, really frustrated. So finally I gave up. I couldn't think of anything else to do. And I turned off the computer, and he said, well, it's still 50%. Okay. That was progress, right? So of course the whole thing was manually configured, and I had not configured it to use the relay point. So now that was easy. We fixed it. Boom, it's working. I was a little worried about security because like Draper Labs is this, it's a secure facility, and I've been driving around on the roof all night. I went home, 6 a.m., took a shower, and I put on a suit. And I went in with a lot of confidence to talk to this investor who decided not to invest and lost hundreds of millions of dollars minimum, maybe even $1 billion by not investing. And at the time, I was kind of thinking, you know what, if those guys knew what a fly-by-night operation we were, like me driving around the roof all night, they would have never invested. But later, it occurred to me that if they had known that, they would have invested, right? Because we're not going to give up. We're going to make it happen. So we'll have to have some kind of networking lesson here. I really just wanted to tell that story. So how about static network configuration? It's really caused a lot of pain. So one day, somebody alerted me. I was head of engineering. They alerted me to the fact that one of our servers was receiving properly authenticated messages from an unknown device. And fortunately, these messages were slightly misformatted. They were control messages. They could have impacted the load balancing system. They were kind of one server trying to tell another server how much load it was under. We really didn't want to be receiving fabricated messages of that sort. So we studied this for 2 days and finally discovered this was like the V'ger from the first Star Trek movie, right? It was just one of our servers, and we'd lost track of it. And it was running an old version of the software. And the way we pushed software updates was we had just a master list of all the servers, and we would go down the list and periodically contact them and push the software. Well, okay, that was a bad design decision. Okay, so not only that, it had been doing this for months. It wasn't like we just discovered this attack. So what's the lesson is your server should independently pull configuration data. Don't try to push it. They should pull it. And then maybe also a larger life lesson, which is the commonly known, is you shouldn't attribute to malice what can easily be explained by incompetence. Right? Okay. Here's another interesting one. One day, the authoritative DNS service that Akamai operated came under attack. And the attack consisted of just legitimate requests coming in at high volume. Not super easy to filter out. And at this time, Akamai was operating the authoritative DNS for Google, Yahoo, Microsoft, and many other properties. So the stakes are high. And what happened? Well, the servers didn't crash. They kept chugging along, but the queues started to build up. And eventually the queue size built up to be so big that the amount of time that a request spent waiting in the queue before it got to the head and was answered exceeded the amount of time that the resolving DNS server that issued it would wait for an answer. And then, resolving server may try a couple times, but eventually it will just give up. So this is actually even worse than it sounds, because it's one of these failures where you go along, everything seems fine, everything seems fine, everything seems fine. You're doing great work, and then all of a sudden you're doing no work at all. And in this case, didn't even know it. So how did this happen? So it's not like the engineers didn't think of this issue. They knew this could happen. They knew that if the queue got too large, the delay would get too large and no useful work would be done. So what they did was they ran some experiments. They measured how much time it takes at different queue sizes, and then they set a maximum queue size, and they would just discard requests if the queue size ever got that big. What could go wrong? What do you think went wrong? The machines they used to measure were faster than the machines in the field. Okay. And so the queue size was miscalibrated. So all the DNS requests failed. That was a big embarrassment. What's the engineering lesson? So the first thing is dead reckoning is a bad idea. That was never a good idea. And they should have been time stamping the requests when they came in, and they should have been pruning the queues so that at least some fraction of the requests were being usefully answered, even if you couldn't answer all of them. DNS is pretty robust too. DNS resolvers will try over. So if you're answering, at least doing some useful work, and there's TTL and all that, it would have been better. But also I think there's this kind of failure seems to be kind of subtle. It's called, in gaming, it's called a critical existence failure. It's where you think your character is fine, and then you suddenly die, right? Even though there was no symptoms, no sign of anything, and then like, boom, you went over a cliff. All right. So that don't do dead reckoning. Dead reckoning means kind of just expecting that, you can measure something and go in that forward direction and you'll get where you expect to be. Here's a story. One day we had a big important customer named Steve, and he complained that when he went to his company's website, he couldn't see the pictures of their new PowerBook. And yeah, and we were supposed to be delivering those pictures, and this company had just bought 4% of Akamai or something like that. So it looked bad. And Steve had an assistant named Eddie. He explained the problem to me, and I said, okay, well, let's just tell me his IP address. And we figured that out. And I pulled an all-nighter going through all the logs from the Akamai servers and trying to figure out what went on with these requests. And I couldn't find anything. In the morning, my buddy Satish Rao, who's a professor at Berkeley, but was also at Akamai with me then, came in and he laughed at me. I said, why are you laughing at me? He said, now we know what a millionaire will do for a billionaire. Okay, so I called Eddie. I had to wait for him to get up. I said, we need to do some more tests. Go into Steve's office. He went in there. I said, okay, right now, go to the page. And then I had set things up. I knew where to look. He goes to the page. He says, there's no pictures of the PowerBooks. I said, well, we didn't get any requests. Okay, so that was a clue. All right, so I don't know why it took me this long, but then I went and looked at the source code for the HTML document. And it turned out, like in the early days of Akamai, there was this kind of quite ugly, very long prefix that would get appended onto the URL of the original object if it was to be served by Akamai. The one good thing about that prefix was it had the name Akamai in it, and the browsers used to flash every single URL that they downloaded at the bottom of the page. So there were like gazillions, well, literally trillions at least billions of impressions per day going through people's heads. Akamai, Akamai, Akamai. Well, the webmaster, wait, why did I look? I skipped the most important part of the story. Why did I look at the code? Well, I said to Eddie, can you tell me, Eddie, what operating system are you running? He said, no. It's not, what do you mean, no? It hasn't been released yet. Okay, that was OS 10. I said, okay, but how about what browser? No. What do you mean? No. Okay, well, it was a new browser, hadn't been released yet. It was Safari, right? So that's why I thought, new browser, new operating system, I'm going to go look at the code. The webmaster at Apple I didn't say that. The webmaster he didn't like this long URL. So he put a line feed in the middle of it. Okay? That's not legitimate HTML. You can't have a line feed in the middle of a URL. But every other browser by then knew that people did this. So they would just fix it. Safari, nobody was using it. So they didn't know yet, right? So yeah, there is an engineering lesson. When all else fails, look at the code. Oh, the Mag Center. This is a technical term employed at the company that makes the world's most popular commercial operating system. So one day it came to my attention that millions of times per day, our servers were receiving requests for URLs for domains that we didn't have anything to do with. They weren't our customers. We weren't serving the content. We would get www.mit.edu. I don't know, something we don't serve, right? Millions of times per day. And what did our server do? It said, something like, Akamai server error. So we tried to figure out what's going on with this. Immediately I said, this is bad publicity. So I registered the domain weberrors.com. And it said, now it would say, you have experienced a web error. And yeah. Don't worry about that. I decided not to mention that. So on the page, there was a button you could press to report the error. And what that did was it performed a unique DNS lookup and HTTP request. So I could start gathering some information about this. And there was also a form where you could provide any information about the error. And all of that data went to me, including the handwritten notes. And there were some very angry people. Okay. So they were angry because there was a lot of day trading back then. Okay. And they couldn't get to their site where they're trying to day trade. Or there was certain content that Akamai had nothing to do with that they couldn't reach, and they were very frustrated. Okay. So I had to deal with a lot of hate mail, but I started to learn from, these click-throughs. First of all of these errors were happening to people using one operating system. Okay? Multiple browsers, one operating system, and it was happening across more than one name server. But we couldn't reproduce it. So I wrote this there used to be a thing called a Java applet, which was a Java program that would run in your browser. I wrote this little Java applet that would just go to hundreds of websites, hoping that it would land at weberrors.com. And I distributed this to friends all over the world, and nobody could reproduce this error. And one day, it just occurred to me that I could look at this stream in real time, I had a feeling this had something to do with DNS. Look at the IP address of the resolving name server that was being used. And I made that my name server. And I ran the little applet for a while, and boom, I got the error. And I had run TCP dump too. So I had it in my hands. I knew what it was. Okay, what was it? Well, when you send out a DNS request, you include in the request what port number the answer should come back on, an identification number. I know all this because I use burned slides in my networking class. An identification number, and then also the your query. And when an answer comes back, it should match should come back to the right port. It should have the right ID, and it should repeat the query you answered. So I'm looking at the TCP dump. I guess for you guys, it's Wireshark now, right? Or Bro, or I don't know, something. It's some packet capture thing. Okay. So notice something weird. The answers were coming back to the right port with the right ID, but it was a completely different query. It had a different domain name, and then it had the IP addresses for that domain. So the name server was broken. It was just sending back bad answers. And then the operating system was accepting them. So I was a little frustrated by the company that wrote this operating system because they wouldn't let me talk to any engineers. I thought, I was kind of, as a professor at Carnegie Mellon, and I'm head of engineering at a company that they know about, but they wouldn't let me talk to operating systems engineers because those guys are higher up than I am, way higher up than I am, sort of pecking order, until I could reproduce the error. So I reproduced it. Only this time I reproduced it where I tried to go to their website, but I went to Playboy instead. And I sent them the TCP dump. And I waited, and I was pretty sure they were going to say thank you. And then I finally was able to talk to somebody, and they said, well, yeah, we're not going to fix it. I said, what do you mean you're not going to fix it? And they said, well, you already 100% trust your name server. It could have sent you the right query back, but just gave you the wrong IP addresses. There's so many different things it could lie about. Why should we fix it? And I didn't think that was very acceptable. Okay. I think maybe Dave, was this your quote about being liberal about what you accept, but conservative about what you put out? Oh, John Fastel. Okay. Anyway, it just didn't seem right to me. Okay. And so I finally went back to it and I said, look, okay, guys, but the name server, it's also your name server. Okay. Just fix one or the other. Right. And so they did show me some email trails where this thing was called the MAG syndrome internally, which I like. So I think the end of this story was it wasn't fixed for a long time, eventually got fixed. In the meantime, somebody at Akamai figured out we had a web page that was being viewed hundreds of thousands of times per day, and they started selling ads on it. Okay, so engineering lessons. Okay, sanity check your inputs. Check your outputs. And follow the RFC, which said check that the query matches your query, not just the port and the ID number. Okay, so that was some stories from Akamai. Now, I've got a couple of stories from Emerald. I came here again on sabbatical. Ari was my host in 2019. And I got sucked into Dina's startup. So Emerald Innovations is another MIT spinoff founded by Dina and three of her former graduate students, Rahul Hariharan, Rumen Christoph, and Zach Kabbalik. And it's also a block away from here. And what was fun for me about Emerald was I got to learn all about a completely different technology. This stuff did come out of the SIGCOMM community, but it's not really about networking. So Emerald has developed what I call a human radar device. So this was a picture of my apartment in Proto here in Cambridge, a block away from here also. The Emerald device is on the wall there. It's got an antenna array and a computer inside, and it sends out microwave radio signals. They bounce off things in the room, most importantly, people. The reflections come back. And then there's a lot of signal processing and machine learning that tries to extract useful health information from the signals. And this is used, Emerald's business is to provide a service to pharmaceutical companies that are conducting clinical trials of new medications. You want to know, is the medication effective? So for example, one of the early things that Emerald developed was a way of measuring what sleep cycles you're going through: deep sleep, light sleep, REM, awake, based on your breathing signal, which the device was able to extract. And it's an example study might be a pharmaceutical company has a new antidepressant. They want to know, does this disturb the subject's sleep less than previous antidepressants? That's just an example of the kind of thing the device might be used for. So it can capture breathing. That was the first big application. It can capture heartbeats, although I don't think Emerald does that in clinical trials. Sleep cycles. I'm going to show you maybe one of the most impressive things that it can do, and that is it can reconstruct the pose of people in a room. So the goal here is to come up with a sort of a 14-point skeleton model of every person in view of the device. And I'm going to show you a demonstration. Now, in this demonstration, there's a camera, but the camera is only being used so that you can see what the real people were doing. And these are MIT students here, probably in this building, I don't know, somewhere on campus. And down below, we have the reconstruction of the pose of the people based entirely on the radio signal. Okay, and so it does a pretty good job. You can even see activities, like at least some basic things, like did someone sit down or stand up? And these skeletons are to scale, like shorter people will have shorter skeletons. They can be used for simple things like understanding, how fast can someone walk? How steadily did they walk? This has been used in a number of studies of treatments for Parkinson's disease, for example. And I want to talk a little bit about how this works. Now, it turns out at this radio frequency, the human body is specular, which is a word I didn't even know before I started working at Emerald, but it means that the radio waves bounce off the body according to the angle of incidence, like a pool ball off the side of a pool table, right? So when you send these radio waves out and they hit people, they're not all going to bounce back to the sensor. Some of them are not going to ever make it back to the sensor. Others are going to hit the roof and come back to whatever. But the point is that as somebody is walking across the room, some of these waves are going to go back to where you want them to. So you go back to the device, and others are going to go in other directions. And so you can't, from one kind of snapshot, you can't reconstruct the whole body. Now, I like to think of the sensor as producing a movie, except that instead of a light camera, it's sort of a depth camera. And we're really literally just kind of counting in every direction, how long did it take for the radio wave to hit something and bounce back, but it doesn't always come back successfully. So if you look at over time, at different instances of time, you see little portions of the body. And what you want to do is reconstruct, maybe I don't have the whole slide. You want to reconstruct the entire body at all those steps. And so there's a big machine learning model. And guess what? It's a machine learning model that kind of needs to look back over time. So what's the architecture? I don't know, it's some kind of transformer thing, right? And well, you saw it works. Mostly it works. At least, in this picture, it works pretty well. So we had this live demo. This is a really impressive thing. People walk into your office and they walk by the device, and then up on the wall, there's a projection showing their reconstructed skeleton. One thing I noticed early on that was quite annoying to me was that when I did it, periodically I would jump up to 6 feet high. Okay? Why is that? Well, because it can't always see my head. Because, I don't know, it's just the angle's not right. And it was trained on a bunch of people who aren't my height. Right? So when in doubt, it would say, okay, well, you're 6 feet tall. You're 6 feet tall. That's a safe thing. Everyone I was ever seen in training is 6 feet tall, so you're 6 feet tall. Another thing that's really crazy is like it was trained with the device mounted 100% of the time at 1.4 meters. Right? Okay. Well, what happens if you lift the device up 10 centimeters? Ankles rise 10 centimeters off the floor. Because it learned the stupidest thing. Ankles are 130 centimeters below the device. Okay, that was a hard and fast rule that never failed. Well, it turns out that when you go and start deploying these in people's homes, they sometimes have like a couch. And the couch is like covering up 1.4 meters. So you got to put the device, right? Kind of learned this thing the hard way. And by the way, so Emerald's is still not a big company. It's a medium-sized company. It was a small company at first. We had this big contract to put the devices in the homes of subjects in an Alzheimer's trial in Miami. And normally in these clinical trials, there's the pharma company, but they outsource a lot of the logistics of a trial to what's called a clinical research organization, a CRO. And we would depend on the CROs in a case like this where where the subject couldn't install the device themselves to do the installation for us. And the CRO kept screwing it up. So we decided we'd do it ourselves. This was a major miscalculation. So I made 19 trips to Miami. And I was living in North Carolina on the weekends. And I would fly up here, then I'd fly to Miami. I did this 19 times. I installed about 50, 60 devices. I learned a lot by doing that. I learned that you really only had to do two things. Get the darn thing on the wall in the right place and connect it to Wi-Fi. Okay. Here's a networking lesson. Every home has its Wi-Fi misconfigured in a different way. Oh my God. So yeah, eventually I installed a cellular data modem in the device too, just as a backup, so we could always get in if we had to. Well, here's a war story with zero to no networking content, but it's a good one. So one day, sitting on the sidewalk, and the sun is beating down on me, and I don't have a hat. And I'm holding this big box, and many of the subjects didn't speak English, and my Spanish is very poor. So I have a translator. I'm on the phone with the translator back in Cambridge, and he says, this is Manny, he says, she said, just let yourself in. I said, no way. Okay. You guys have sent me to the wrong house 3 times. I'm not letting myself in. I'll sit here 5 more minutes, but if no one comes to get me, that's it. So, but I will say the subjects were super nice to me. And every home I went into immediately gave me Cuban coffee. And by the 3rd or 4th home, my ears were ringing. I had so much caffeine, it was unbelievable. So okay, so one thing was, yeah, so the model, it would fall back to 6 feet tall. So basically, and it was sensitive to the height of the device. So the problem was it hadn't been trained on diverse enough data. Okay, that's a simple lesson. Yeah, you know that. And also it didn't remember enough about the past. Like if it had seen my head, people's heads don't change height that much. Okay? But something extremely disconcerting was sometimes in demos, the head didn't follow the body. So the solution to that, you think? We just hard coded it, right? That no matter what. That's a real engineering lesson. So let me finish with one last story. So I thought this was pretty cool. And by the way, I get no credit for any of the machine learning stuff. I did a little work on the signal processing, but these models were all designed by, initially here at MIT or by Emerald employees. And one of the coolest models was a model that detected scratching. And so this is a video of Emerald's anonymous test subject at his apartment. what we're going to see is a model that predicts whether or not this person is scratching. And we'll start it up here. Okay, it's running. There's no scratching going on, and the model says 0, 0, 0, 0, 0, 0, 0. Well, there's a little scratching. Okay. Well, it really works. It really works. And one of the cool things about this radio frequency is also it can see under the covers. So you can be lying under the covers and scratching, and it'll be like scratching. So this is interesting because there was a lot of activity in designing drugs for diseases like atopic dermatitis, which makes you itch. And the nice thing about the Emerald device is like you don't have to put anything on. You don't have to wear something, which is annoying if you're itching. And the idea about measuring when someone's lying in their bed is that people scratch when they're asleep, and that's involuntary. So you're not worried about is somebody counting how often you scratch. So we had a number of trials, and in this is getting annoying. In one of these trials, the customer said, "This sounds cool, but we want to really make sure it's accurate. So can you guys build a camera? And we're going to get volunteers who will agree to the placement of the Emerald device in a camera in the bedroom, an infrared camera." And I was like, "Oh my God, you want us to engineer a camera?" And I suggested, why don't we just use Google Nest cameras? Or, I don't know. There's a lot of cameras out there. They said, no, no, no. All the data has to be kept in-house. You guys build the camera. So we built a camera. And we also built a video labeling system and outsourced the labeling of all the video to, it's kind of like a Mechanical Turk type of thing. So this was a pain, but it also meant an invaluable trove of ground truth data. Now, so just so it's clear, I mean, obviously, I don't want a camera in my bedroom, but this is done with the full paid consent of the participants. And not only that, but the camera had a big black button. You had to walk up to it and turn it on. Okay. So there's no question. There's not like some kind of secret surveillance. Okay. And so here's something I learned. So a buddy and I at Akama, at Emerald, every week we would go and look at a little bit of video from every camera just to make sure it was working, just to make sure the camera's working. What I learned is that people who agree to a camera in their bedroom have no sense of modesty. They'll walk up to the camera and press the button, and we're like, oh man. And I think that is my last lesson of the day.
For 7 questions, so. Entertaining as always.
No, thank you. Karen?
I know. Do you have lessons from fixing the Digicom thing down on the first floor?
So yeah, you may have noticed, especially if you're visitors, something that looks like a giant old-fashioned pinball machine downstairs, which is called a Digicom, right? And for my advisor Charles Leiserson's, I forgot to mention I'm really happy to be here because I went to MIT and I've seen a lot of old friends, and I was born in Cambridge, which makes me, I'm a local. I'm a Cantabrigian. And we bought that machine for Charles's 60th birthday celebration. And it looks like a pinball machine, but it's actually a computer. You send these balls up and it can add and subtract and do all sorts of things. And it's mechanical and it breaks down all the time. And at one point when I was here on sabbatical, we bought lab coats. Digicom technician lab coats, and TB and I spent a lot of time trying to get that thing to work. And I'm skeptical about whether it's still working because it requires a lot of attention, but you might want to go downstairs and check that out. Brad?
Go first. I don't have a question. I have an anecdote to build on one of yours.
So Bruce, you restricted your talk, which was great, to actually, I know, a small subset of your practical experience. I wonder if you could just spend less than 60 seconds talking about your vast experience in computer game development.
So not too many people know about my background in computer game development, but I was very fortunate as a 12-year-old to have a Plato terminal installed in my home. My father's a law professor at the University of Illinois. He's still there. He's been teaching over 60 years. He's in his late 80s. And he was an early computer hobbyist and computer enthusiast. And he put a Plato terminal in our home. And for me, at first, this was like the greatest gaming paradise of all time. Computer game. Plato had cool computer games. I played a Star Trek based game called Empire. I really worshipped the people who wrote the game. So my friends and I, when we were in junior high school, decided that we should be the ones receiving the worship. So we launched multi-year effort, which is a big deal when you're in junior high. It took us about 3 or 4 years. We wrote a early, popular, maybe even possibly at one time the world's most popular multiplayer Dungeons and Dragons game. It's called Avatar. And one time, just this is a confirmation that I'd really made it big. My mom is riding on a city bus, and she hears these students talking, and one says, are you still in engineering? The other says, nah, I had to drop out and switch to liberal arts. I played Avatar all night, every night last semester. My mom, who's got a PhD in comparative literature, was very annoyed with the consequences there. Yeah.
Thank you. Out of time?
One question.
It's not a question, but I thought there were no other questions. Your story about trying to get Microsoft to fix a bug, I have a story to build on that, which was that when I was a graduate student at Harvard, Bill Gates and Steve Ballmer donated money to build a new computer science department building at Harvard, which involved demolishing the old building, which was a bit of a burn pit, really. And so we had decided that this was in the heyday of IP multicast. We're going to do a live IP multicast video of the demolition, a camera inside the building where the feed would just go dead at some point as the building came to its demise. So I was the person who proposed this, and I had sent instructions to the whole CS department at Harvard how to watch video on IP multicast, which was a bit niche at the time. And at the bottom of the email, only very far at the bottom, we had if you were on a Sun machine, if you were on a DEC machine, whatever. And he said, if you were running Windows, what I wrote was, well, you can't watch because IP multicast just doesn't work on Windows reliably. But if you run Windows, you're used to being punished. Harry Lewis, a senior faculty member at Harvard, without reading to the bottom, forwarded my email to Steve Ballmer saying, look how excited everybody is about the new building. He got a one-line email back saying, how rude to Win95. And there was a message on my answering machine when I got home that night from an engineer asking me what's wrong with IP multicast, Brad, in Win95.
Yeah, I guess you had to go through the right channels.
Thanks, Bruce, again. Cool. Yeah. Okay, so we're going to move on to the next session, and then we have break after this session. So, okay.
Right. So while waiting for these setting up, the next session is the operating system and architecture support for networking. So we're featuring 2 interesting talks. The first one is presented by Jian-Chang Su, who is a PhD student at University of Connecticut. And his research interested on cloud computing, system security, and machine learning systems. And he's going to talk about the use eBPF to accelerate distributed communication. Thank you. Thank you for introduction. I think I need a minute. That's
Yeah. Sorry, I don't make exception.
no, so that makes sense. Okay, we got it. Thank you. Hi everyone. My name is Zhenjiang Su, and from the University of Connecticut. Today, I'll be presenting the ACBOS, our system for accelerating distributed communication, by moving the application and broadcast the operations into Linux kernel by using eBPF. Broadcast and aggregation are two fundamental communication primitives in distributed computing. In the distributed ML, including TensorFlow, PyTorch, and federated learning, workers constantly synchronize gradient through aggregation and receive update parameters through broadcast. Every distributed ML framework implements or reduce which aggregate followed by broadcast. In the big data, the frameworks like Spark and MapReduce rely on shuffle operations, which are sensory broadcast plus aggregation. And these operations are the bottleneck. A 10 TB per second network communication can dominate ML training time. Suffer is a major fraction of MapReduce job time. Okay, and the key point is that these two patterns, one-to-many and many-to-one, are so fundamental that optimizing that will benefit virtually all distributed systems. So we asked, where does this overhang come from? We instrument the entire packet path. The sender side takes about 70 microseconds, but the receive side takes over 65 microseconds. Yeah, it's 4 times that slow. This asymmetry comes from the receiver side complexity, interrupt handling, validation, and memory copying. And the key observation is that the bottleneck is user kernel classing and stack traverse, not the network wire. And this tells us exactly where we want to focus. Okay. This overhang composed with the scale. For broadcast, the sender pays the overhang m times for aggregation. The aggregator pays receiver overhang for every incoming packet. And both scale linear with the class size. And this motivation and this motivates our core idea. If we process the packets before the full network stack, and we can eliminate most of this overhead. As we know, the traditional approach is the trade-off. Use the standard socket, but we need to pay the full stack penalty, or bypass the kernel entirely by using the DBDK. But the RDNA requires the rootless fabric degrades under the conjunction and only work within the data center. And also, the DBDK burns the dedicated CPU cores, unsustainable for the shared and multi-tenant cloud environment. Okay, so here's the question. Can we get significant speed down on commodity hardware without these dedicated resources? Yes, we have. Instead of going to the kernel, we go into it. And the modern Linux kernel provides a programmable code through the eBPF. And the eBPF let us to run safe, verified code in the network stacking. we attach the two fundamental hooks. The XDP can handle aggregation near the NIC, and the TC handles the broadcast by cloning the packets on the egress path. Because that, we skip the expensive network stack and the socket layer. And the result is performing approaching kernel bypass with simplicity of the standard networking. But eBPF comes with several constraints. So firstly, it's a 500 terabytes stack limit, and also it doesn't support the floating point arithmetic. And it's a stateless execution, and with the straight verifier, this constraint invalidates all traditional protocol design. So we need to fundamentally rethink how we build these primitives. Okay, let me walk through these two hard disk constraints. So the challenge one is the memory and instruction limits. Each eBPF program get only 500 terabytes of the stack, but the package payload can be 50,000 bytes or more. Each function can handle at most 256 bytes. Our solution is core chains. We split the processing into chunk, and it's handled by a separated program, and then we chain using the BPF tail core. Because the eBPF tail core can process a chunk of the fixed payload, so this let us aggregate the arbitrary large payload within the eBPF constraints. For the challenge two, the ML gradient aggregation requires the floating point operations, which eBPF are forbidden. We use the edge quantization, which means multiply the flows by 10 to 8 and convey to the integer aggregate into the kernel, and then recover them in the user space receiver side. So here in example over here, we think this arrow is a double because even the SGD, we have the SGD noise, and as a bonus, you have the bandwidth. eBPF constraint actually both the simple and the better design. Okay. Let's put all the things together. Our system Agabos has three components. First, a user space runtime library with the simple API. Broadcast, send aggregate data, and get aggregated data in the user space. Application integer with just few line code with our system. Second, in the kernel broadcaster on the TC hook, our eBPF program clone the packets via the using the BPF clone with direct to send all destination in the kernel space. Third, in kernel aggregation on XDP hook, we processing the packets right at the NIC level. It use that tail core chains with the edge quantization, like I just described before, and then deliver the result to the user space through the ring buffer. Then the core eBPF core is only about 500 lines. We evaluate on the public cloud. Importantly, our baseline is not naive socket. It uses the optimized UDP with the symmetry and memory map socket. So this is a fair comparison against the well-turned traditional approach. For broadcast on the left, you can see Agabos achieved over 80% latency reduction in both average and P99 latency. And the tail latency improved is important because it shows consistent performance, not just the average case gain. Yeah. And on the right side, we can see the aggregation. Our system aggregates achieve nearly 4 times the throughput. And the key trend is that we get wider with the large data size because kernel-based processing avoid the memory copy and context switching overhead that increasingly slow down the user-based approach. Okay, let's show some real-world applications. Here, for the parameter service training, we use the 3 model to converting vision, text, and audio. Agbar's consistent reduce the gradient aggregation time by over 50%. And this data holds across all these 3 machine learning models, which show the broad impact. For map reduce on the right side, we use the word counting. Agbar's dramatically outperforms the baseline. This is because word counting is computationally simple and the bottleneck is entirely in the communication overhead and also the kernel and the user space crossing. And you can see the baseline flat while the Agbar's scales because kernel space aggregation remove the user space and the kernel space crossing bottleneck. To work out, our system Agbar shows that we can work with the kernel constraint rather than bypassing the kernel. Tail call chance and the edge quantization turn eBPF elimination into advantages. Our results are substantial on commodity hardware, and several constraints can drill into the innovation rather than limit. Okay. Here's our result I just showed. Thank you. So we have time for 1 or 2 quick questions. So, okay.
Just one quick question. I think the results you presented were for 10 gig NIC. Is that correct?
Yeah, so in our evaluation environment, we use the 10 gigabytes network.
Do you have any predictions about how the technique would scale 100 gig or 400 gig interfaces in the future as we see things sort of going in terms of the ratio of the compute of your technique to the data rate?
So actually, as I showed before, our system made it reducing the user space and the kernel space bottleneck, even with the high-end network device like 1 gigabyte or I don't know, very fast one. But the bottleneck is maybe still in the user space and the kernel space of crossing. So I think our system can also outperformance than the naive. Can I answer your question?
I guess maybe the question would be, do you eventually wind up needing to do RDMA or something like that? Like, even if you reduce the compute as the line rate increases, the amount of compute that you would need to do per unit time, I suppose, increases even with these optimizations, right? So it might be faster than the baseline, but how up to what link speed does the optimized version keep pace with the data rate coming in? That makes sense.
I guess given the time, we could take some discussion offline.
Yeah, sure.
Let's thank the speaker again. So our second speaker is Amr Mohammed Nazari, who is a PhD candidate in Yale University Computer Science Department, advised by Professor Robo Soleil and Rajit Monaha. So his research focused on computer architecture, high-performance I/O system, and network architecture.
Okay. Hello everyone, my name is Amir Mohammad, and today I'm excited to present our paper, Axio Rethinking OS Architecture Co-Design for Next Generation I/O. This is joint work with my advisors, Professor Manohar and Professor Soleil at Yale University. So we love OS abstractions, but they are slow. In the recent years, we have seen great performance improvement in I/O devices. We now have network devices that can support 800 gigabits per second or even more. Meanwhile, the single thread CPU performance has stagnated. We have reached the end of the NRZ scale, and we do not expect to see much improvement in a pair core CPU performance anymore. As a result, the operating system abstractions that were once low overhead are now sitting on the critical path of I/O. But what is the difference between these conventional OS abstractions and the high performance ones that we have today for I/O programming? So here are the two ends of the I/O design space. On one side, we have the POSIX API that prioritizes ease of use. Using POSIX, you can create a socket and use system calls like open, close, read, and write to send messages over the network. By doing that, you let the OS handle device multiplexing, handle memory management, and header processing. On the other side, we have kernel bypass platforms that favor performance. Using these systems, most complexity is pushed out of the kernel and into the application. And now the application developer has to configure the device, has to set up the queues, and use polling APIs to receive data from the network. But how are these two actually different in practice? First, let's talk about a kernel-based network stack that implements POSIX. So consider the system architecture that we have a NIC, we have a CPU and a memory, and the CPU is running either on kernel mode or on user mode running an application. Consider also this simple application that creates a socket and tries to receive data from the network. So this system call will go to the kernel and will wait on the socket for it become available, to become ready. And whenever a packet arrives at the NIC will do two things. It will copy the packet to kernel buffers and it will generate an interrupt. Then the kernel will get that packet, processes its protocol headers. It will find the socket and application corresponding to that packet. It will copy the packet into the application memory and eventually runs a context switch to give the control back to the application. And now the application can read the data. So there are a lot of overheads in this process. But what are they? Where is the time being spent here? To figure that out, we run a detailed breakdown experiments. It turns out that from the time that the packet arrives at the NIC until it reaches the kernel, it accounts for 25% of the time. 15% of the time is spent on header processing in kernel, and the rest of it, which is a 60% of the total latency, is spent on context switching and copying to user space, basically user space delivery. And so this has a lot of overhead here, and a lot of prior works have attempted to optimize different components in this pipeline. For example, one class of work would focus on leveraging hardware accelerators and using offload engines to push functionalities into the NIC instead of the OS. Another class of work would focus on optimizing the operating system itself by using techniques like zero-copy I/O. But the one approach that gives us the best performance is kernel bypass. And it does that for us by giving applications direct access to the I/O device. And by doing that, it basically eliminates two of the components that we had. It eliminates user space delivery and from kernel and also header processing. But what does kernel bypass actually buy you? To answer this, we run this simple ping pong experiment between two directly connected servers. And here you can see the CDF of the total latency for different applications written in DPDK and using OS sockets. We can see that DPDK applications achieve significantly lower latency compared to the OS sockets one. However, as we try to add some features back to the DPDK application, such as multiplexing, we lose performance. Here, by adding multiplexing functionality to the DPDK applications, we lost 20% of the latency that we had. And this raises an important question. Is there a fundamental trade-off between the performance and the ease of use? To actually find an answer to this, we wanted to see how we can get, we're wondering how we can get both of these things. How can we get kernel bypass like performance and still maintain the same old like POSIX API? To find an answer, we look to a successful precedent in computer systems, that is virtual memory. So virtual memory that has been evolving for 40 years now gives applications an indirect memory access, but with the same performance as a direct physical memory access. And it does that by adding a hardware structure called the TLB that caches page tables. And the OS would just manage TLB and core data structures. But the key insight is that in virtual memory, the hardware avoids OS in the common case, in the good case, and only invokes OS in exceptional cases. So we were wondering how we can do the same thing for I/O. And this leads to our proposal. So we propose Axio, which is a novel hardware-software co-design that achieves high performance and maintains POSIX APIs. So unlike previous works that were reluctant to change CPU architecture, we make some modest modifications to CPU microarchitecture. We also use the NIC as a hardware accelerator and offload header processing onto it. And we also modify the operating system to support these new features. So far we've talked about the motivations behind Axio. Now let's talk about Axio's design in more detail. So let's revisit the system architecture. We still have the NIC, have the CPU, the memory, with a clear separation between the kernel space and the user space. We add two components. First is a user space library that provides a POSIX compatible API. And the second is a transport protocol engine on the NIC that handles header processing for us in the NIC. Now, for connection setup, applications can use familiar abstractions as before, like socket, to create a connection. Here, we want to give applications a fast and direct access to some important information about the network, like whether a packet has arrived or not. As a result, we add a new hardware structure called the I/O connection table that stores essential information about connections and their associated process. So we store information like where the TX and RX buffers are, whether a packet has arrived or not, or like information about the process, like what state is it is in, like is it suspended or not. And when we create a socket using Axio, the kernel will populate an entry into this I/O connection table for us. Now let's talk about a read scenario in Axio. So when we call read, when we want to get data, so either data has already arrived and we will have to read it, or that means we are in the good case, or we have to wait for it. So let's first talk about the good case. So data has already arrived at the NIC, and our NIC is able to communicate with the I/O connection table to notify it that the new packet has arrived, updates its state. And based on the information there, it will copy the packet directly to the application memory. So now when we call read to get data, we go to the I/O connection table, we see that the packet is already available, and directly go to memory and read. So in this system, we are not running any system calls in any case. As a result, we get the same performance as kernel bypass systems. But this is a good case. So what happens if no packet is already there? So in this case, we again call read. We go to the I/O connection table, figure out that no packet is available. We have to suspend the application now because we want to maintain the same APIs as before. So we run a system call to suspend the application. And here we also need a way to wake up the application as soon as the packet arrives for it. As a result, we add another hardware structure called the I/O ready queue that stores information about ready-to-run threads that are Axio managed. This structure is regularly updated by the I/O connection table. So when a new packet arrives at the NIC and the NIC updates the I/O connection table, this will also get updated. And so the NIC gets a packet, send the packet to the application memory again. And now here, only since the application is suspended, we will generate an interrupt. We will generate an interrupt. Our scheduler first checks with this I/O ready queue, understands that our application is ready to wake up, and it immediately runs a context switch, giving the control back to the application, and eventually application go to the memory and read the data. So note that here we are using an optimized interrupt delivery system, as well as the hardware-assisted thread scheduling, and these two will allow us to have almost immediate wake-ups for our applications. But why are we making changes to CPU in the first place? So the core problem is that user space needs some information about the network, like whether a packet has arrived or not. But it shouldn't. It should be isolated from other processes. It should be protected by some entity, by the OS, to not mess up the states of other applications. And the one entity that can update this information about the network is the NIC. And it's just that existing CPU abstractions, whether they are RDMA or sockets, they don't give us a clean and fast way to do it. And we have to make modifications to the CPU to support these features in a fast manner. So the remaining question is that whether this co-design actually delivers lower overhead or not. To figure that out, we built this hardware-software prototype using an FPGA. We integrated Axio into an open source RISC-V rocket core and on the CPU. We implemented both the NIC and CPU on the same FPGA, and our whole hardware implementation consists of 36 lines of chisel code. And this prototype allows us to evaluate the system under realistic conditions. So our FPGA is obviously slow. It runs at 50 megahertz and has a simple microarchitecture. To account for this, we have to adjust the time that it takes for packets to travel. We take measurements, we take timestamps at different parts of a send and receive request, and we scale the execution times that happen on FPGA by two scales. One is the 40x that accounts for clock frequency, and one is the 200x that also accounts for microarchitecture differences. And now we present our evaluation results. We begin with packet processing latency. We use a UDP ping pong benchmark here. And we can see that at 40x scaling, Axio achieves performance similar to RDMA. So note that here we have a 40x and 200x estimates, but then we expect under realistic deployment, our performance would lie between these two regions in this region, but we expect it to be more closer to the 40x region because of the pure clock frequency adjustment. And we can get almost up to 30% better performance than DPDK in packet processing. And we are also maintaining POSIX API. We also evaluated throughput using a UDP benchmark, and we saw that we can saturate the FPGA bus bandwidth. So it is lower than that of modern servers, obviously, but we expect a realistic deployment to saturate a 100 gigabit per second link easily. And finally, we examined CPU utilization using an Axio-based UDP server, and we observed up to 66% reduction in CPU usage compared to kernel bypass systems. We are even outperforming OS sockets. And in summary, we presented Axio, which is a co-design that delivers high performance and maintains POSIX sockets, same familiar abstractions as before, actually. We accomplished this by making modest modifications to hardware. We add an I/O connection table, an I/O ready queue. We also use optimized interrupt delivery systems, and also hardware-assisted scheduling. And we all showed that using an FPGA prototype, we can get low latency, high throughput, and reduced CPU usage using Axio compared to kernel bypass systems. Thank you so much, and I'm happy to take any questions.
So, okay, this is sort of an interesting trade-off that you're making. You are changing to keep support of POSIX, an API that several people have argued makes it impossible to actually utilize hardware fully because it has obvious points of synchronization. So I'm curious, why is maintaining POSIX compatibility so important if you want high performance?
Thank you. That's a good question. So we want to keep POSIX. So we argue that POSIX makes life easier by first having simple abstractions. One may say that, okay, I like DPDK abstractions more. But the thing is that using POSIX, we basically delegate, we put a lot of decision makings onto the OS, onto someone else. And the application developer, when it's using POSIX, it doesn't generally make a lot of decisions here.
So can I ask a follow-up? So POSIX is, not the only API. I mean, look, again, who's another made fun. Microsoft has no problem with that. But one of the few things I think NT did get right, and actually FreeBSD, which you used as your example, does follow, is the notion of KQs, because again, the idea of having multiple KQs or multiple IOQs was it made parallelization easy. But even then, even if you hate Windows, even if you hate the KQ interface, there's been like decades of other interfaces. So POSIX is like one point in the design space, but all of the interfaces, I would argue, do exactly what you said. So that's a weird reason to say POSIX is good.
So I don't want to argue that POSIX is like good basically here, but I wanted to see here that we can have the same blocking APIs as before. Like if you use kernel bypass systems, most of the time, like basically all the time, if you want to get performance, you have to use polling APIs. You have to poll the device to get new packets. But using this, we are maintaining like a good CPU utilization as well as keeping the same performance as you could get with a kernel bypass system. Like,
So are you attached to like blocking APIs, or are you attached to like POSIX blocking APIs? Because there are other like just like people have mentioned, like worked on DPDK and so on. People have worked on blocking APIs, like Shenango as an example, where it is a blocking API, but it is not a POSIX blocking API. It's like vaguely inspired by POSIX, which I don't think it's possible for us, any of us, to build an API that's not inspired by POSIX anymore. But it's not POSIX. It's not POSIX compatible. So would that be an alternative that is acceptable to you, or is like something about POSIX special?
So I would say yes, that would be acceptable. We can implement this with all sorts of blocking APIs. And we can get good performance with them too. It doesn't depend solely on POSIX. It's just a way to have like good blocking API, fast blocking API for our systems.
Okay, so given the time, so we move more discussions offline. Let's thank the speaker again. We'll have a break.
So we're going to break for 10 minutes, I believe, at which point we'll be back with Brad and Vern and others. But please try to come back in 10 minutes as opposed to like staying out for.
Okay. with fireside chat.
Thanks, everyone. It's a pleasure to close out the New England NINES pod today. I'm Brad Karp from UCL, and I'm here with Vern Paxson from CoreLight. I'll be interviewing Vern, and I just have to make a brief disclaimer that I'm here in my personal capacity and I'm not representing either of my employers, Google or UCL, in anything that I say today. So just by way of introduction, because there are many, we span a wide range of ages in the audience. It's a real pleasure to be interviewing Vern. I think the first time I saw Vern's name was sitting in my dorm room as an undergraduate, downloading over a modem a copy of the Flex lexical analyzer and seeing his name as the author of Flex. Vern has held a number of positions in the course of his career. This is something we'll be discussing a little bit from after his PhD at Berkeley, being on the staff of Lawrence Berkeley National Laboratory as a researcher. Then when I met him more in person at ACIRI, the AT&T Center for Internet Research at ICSI, down the hill from Berkeley, then as a Berkeley professor, and now at CoreLight as a founder and chief scientist, having crossed the Rubicon into industry. Vern's many contributions are probably well known to you. I was also, I think, one of the second time I heard your name was when I wound up running a measurement site at Harvard for your PhD thesis for some of the TCP traces that went into your thesis. If I were to describe a summary of Vern's contributions, people often describe Vern as working on measurement and working on network security, among other things. I feel that it would be better to say that Vern is a researcher in insight rather than measurement. The thing that I find remarkable about Vern's measurement studies is just how in a pile of data, like in that TCP thesis from sites all over, extracting meaningful insights that teach us all about the way systems fundamentally behave. And so it's a pleasure to have you here today.
Thank you very much. And thank you for that very nice intro.
Sure.
I'm really happy to be here.
I think I wanted to start actually by asking about some of that arc of your career a little bit. So having worked at a Department of Energy funded national laboratory, a research institute that's a nonprofit, as a professor at a university, and now at a startup, can you tell us a little bit, because we have graduate students in the audience who are charting their own career path, maybe some professors who would like to chart their career path. What was it that led you to make these changes at these points in your career? Was it that the field was changing, that your own interests were changing, that the nature of the job was changing for institutional reasons? Can you tell us a little bit about how you knew when to make these moves?
It's very haphazard story. And I was reflecting on this a little bit, and funding and money played an enormous role, which I wouldn't have thought. So I did my PhD on measuring the internet. I thought the internet was a boring topic, and I had to do the internet because Lawrence Berkeley Lab was paying for me to do my PhD, and I wouldn't have done the PhD had they not done that. And so there I am, and Julian Jacobson says, no one's measuring this thing, you should measure it. And I thought, oh, shoot. And went off and measured it. And when I was done, I did a job search, and the nice, fit, and I had the opportunity to continue at Lawrence Berkeley Lab. That was great. And we had this group with Steve McCann and Sally Floyd and Dan, of course, and for some of it, Kevin Paul. And that was fun, and it was a really nice group to work. Funding was precarious. And Scott Schenker approached me to say, I've got this thing lined up with AT&T. This is right before the bubble popped, where they'll fund us at least 3 years, guaranteed. And then they'll roll over, each, after the year one, they would make a decision year 4, year 2, year 5. Great possibilities. And in contrast to at LBL, where all the time Dan had to figure out how to scrape up more money. And so there was that opportunity of stability and colleagues who I knew would be a ton of fun. And so made that move, driven by those two factors. After how long, 7-ish years, well, AT&T funding ended after 3, after their contractually obligated 3, because the dot-com bubble burst, and AT&T is like, this is crazy. So we were scrambling for funding. And after a number of years, we had success. I'm very grateful for that. But Scott Schenker said to me, you know, you should think about a campus appointment, you know, faculty at Berkeley, because that's just way more stable. And you get a bunch of colleagues in the process. And so I went after that very naively. I'm still mortified if I reflect on my first year trying and how my job talk ran half an hour over. No one wanted an hour and a half job talk. No one told me it's not really an hour and a half. And joined the faculty, and to my sort of delight and horror, discovered I really like teaching. So I was dreading the teaching, and then when I started doing it, I thought, this is actually fun. But it also will suck up however much time you have. It can always be better. And if you care about that, there goes all your free time. I did that for a whole bunch of years. And then we had, and I'm just always going to call it Zeke. Bruce, you were mentioning Bro, the old name. I just call it Zeke. We changed the name. I'm not going to go into that here. So I started working on Zeke as a grad student, as sort of the thing that paid the bills for the grad work. And it became a very interesting open source project. It needs money. And we benefited hugely from the National Science Foundation put in, like, the big chunks totaled nearly 7 million. And then there was a bunch spread over other things. That was fantastic. We could see the community building up. But we also knew that NSF couldn't keep doing that because it's not even the mission. It's not research, right? It's full, you know, sort of infrastructure line. And so we created Correlate, whose sole vision of conquering the internet and everything was actually just bringing enough money to the open source program. We didn't manage to do that. And I learned a lot about business models, and business models that don't work. And I was still professing. I was watching my co-founders wander in the desert as they put it. And they finally found the right business model, and things started taking off. I thought, oh, there's actually something for me to do. And so I took leave in Berkeley. It's great. Makes that easy to do. And did that for a couple of years. And then I came to the, you know, Rubicon decision. All right. The vice or the provost made it clear, you know, these are 2-year gigs, you need to come back. And I thought, I'm enjoying that a lot more. I would find a path to early retirement. And here I am now, full-time Correlate.
Yeah, excellent, excellent. And so you said that funding at various stages had something to do with it.
Totally.
Early on, but then at the end, it was sort of love of the work that in your most recent
that kept me there. But actually, so it was only part of it, right? I could go back to being a professor, and there was lots I liked about it. What did I not like about it? There were 2 things I really didn't like about it. One was funding, and how much work it took, and storytelling and care and feeding of the PMs and so forth. And, you know, that's just the ecosystem, and a whole bunch of you live it. But it wears, and I've done it for decades. And whereas being at a startup and not the CEO, I don't have to raise the funding. The CEO has to raise the funding. So there was that. And the other thing was this shift in demographics where when I would teach, the last time I taught the undergrad computer security course, which is a fun course to teach, except it was 500 students. And at that scale, you get to know almost none of the students. You get all these, you know, 3, 4 sigma weirdo problems popping up because it's a big population. And it just feels kind of soulless. And I was dreading having to teach it again, which was really a pity because it should have been fun. So it was that pair.
Excellent. No, it resonates with some of the things I hear from colleagues in the academic community. So I also wanted to touch on the sort of dual of the institutions that you visited, which is the areas that you've worked in, because you've done a lot of work in congestion control, a lot of work in internet measurement, of course, the intrusion detection work, but then more broadly, sort of really cool studies on ecosystems of um, uh, abuses of various kinds enabled by the internet, credit card fraud, and so on. And so I wanted to ask, and how have when your interests have evolved and you've sort of shifted topics that you've worked on, um, again, how did you know that it was, or it was not something you thought about consciously and you just sort of followed your interests of the moment? Or were there moments where you thought, I don't want to keep mining this area that I've been working on. It's time to do something else, because this is something everyone faces in their career at
Yeah,
times.
yeah. And I think the resolution varies by your style, personnel, and so forth. For me, I've never been good at persona. I never know anything's going. And the internet, come on. But when I hear someone's vision, I am good at responding to it and knowing what I like about it or not. And a huge part of my research career just benefited so much from collaboration with Seth, who that guy is exciting, visionary, and he would tee up these things that were, hey, what if we got inside a bot? Like, what? You can do that? Yeah. and we would then pursue them, and they were very fruitful to pursue. And so I knew what jazzed me. I just wouldn't identify that new thing that would jazz me. And I'm totally fine with that. It's led me to great places. Another was my shift into work on censorship, which came from some colleagues who were passionate about it and knew a lot. And it was a different world than I thought it was. And I wanted to learn more. So.
Excellent. I wanted to shift gears into a little bit more of a technical topic, perhaps a timely technical topic. Some of us today have tried to avoid this topic. Some of us have embraced it, and that's machine learning. As I was preparing for this interview,
not AGI.
I said machine learning. So as I was preparing for this interview, I went back and looked over some papers you'd written over the years. And there was one in particular that struck me. It was an Oakland 2010 paper that you wrote with Robin Zoma, which began, the title's a bit long, but it began Outside the Closed World. And it was a sort of critique, if I could call it that, of the use of ML in security, in particular in intrusion detection up to that point, which had seen quite some attention in the academic community. And the sort of paper did a lot of explanation of, led with the observation that we hadn't seen a lot of deployment of these ML techniques in 2010 for intrusion detection, and tried to articulate why it was that that was the case. Here we are in 2026. I noticed that CoreLight's webpage appears to say that AI is part of what CoreLight is doing.
Yep.
And so I wanted to ask, looking back on that paper, what's changed? Is it purely that that paper was before transformer-based models and LLMs changed everything? Or is it about the scale, the increasing scale and context windows of those LLMs? Or what is it that's changed that's made AI maybe more deployable?
Yeah, this is a great question. And by the way, Robin Summer, my co-author, was also one of my co-founders. So there's several things. I would say that for detection, LLMs are not the thing. And they're just you feed it 1 billion tokens and say find it. But they have other uses, and I think we'll get to that. Supervised ML has come a long way with both understanding of quality labels, how to attain them, with explorations of feature power, which is really important. So you kind of understand what is it. And and sometimes even the feature power will tell you, you know, there's a structural algorithm to do this. It's even better. And just do that because it points up the features. And then I think there's also, so part of the paper, so the paper made these points, you know, and one of the points the paper made was you need to think about, you're looking for a needle in a haystack. You're not trying to tell apart an A from a B with, you know, you got a bunch of data. You're looking in a billion events or, you know, two that happen to have some property. And that's very challenging. Why I've tended to emphasize structural approaches, because you kind of can winnow down the problem and go after it more directly. But all that said, the use of apt ML has been great for these problems where there's just a whole bunch of features and you really don't know how to do it structurally, and the ML can figure it out. So for example, you know, is this a dodgy domain? That's a good problem for ML. It's a hard one for structural approaches. In addition, one of the things we were reacting to back in 2010 was anomaly detection. And the core issue at the time was the essentially bad logic of attacks look suspicious or look weird, look anomalous. Therefore, a thing that looks anomalous is an attack. Just not how the logic works. It's like it might be an attack, but it might be a thing that's anomalous. One thing I got really excited about, and this is not a thing I did, it's what our data science team did, which is I don't lead, was come up with an anomaly detection framework based on neural collaborative filtering, which is essentially finding implicit relationships in your data so that you can, and I'll just do it in high level abstract terms. You know, if this system connects to this service, you've implicitly figured out a lot of other systems that are like it, they use that service. So the fact that this system did, it's not anomalous. Or they don't use that service, it's anomalous. And you get much better knowledge out of this sort of approach that, wow, that's a 6 sigma thing in a billion events, which of course.
And on a related note, when one of the things that distinguishes the security workload as opposed to, say, file system performance is the adversarial nature of the workload. So using ML in attack detection, there's been some work in the literature on concerns about adversaries knowing that ML is in use and working to defeat ML, such as by putting spurious features in their attacks that a classifier over-indexes on, or trying to mistrain somehow a classifier. Have these things come up in the uses of ML and security that you've looked at? Do we need to worry about the adversarialness of the workload in trying to use ML?
Essentially, no. And so they're not a thing we worry about. And the reasons are, first, when you're doing sort of classic supervised learning, you have a lot of control of labels and how you figure out what are the labels of and so forth, and where you get the data. And you know, you get the data from 2 years ago. Well, did they figure out back then to poison it? Probably not. In anomaly detection, in the more powerful type I mentioned, what you worry on is, you know, you're generally training over some rolling window. If the attacker can slip in not anonymously and slowly move, and you know that's a real hazard, but I think it's not anywhere. That issue is so much smaller than just the ability to identify that system shouldn't be talking about system. You know, that gets you so much of the problem that if we're left with this the sneaky evasive step, okay, that's the next step. It's always the next.
Right. And also on the topic of ML, I promise this is the last ML related question I'm going to ask. where do you see ML falling as a tool for attackers versus for defenders? Because if I think about it, my naive view, I could sort of imagine that asking even an LLM to find known misconfigurations in a configuration, they seem pretty good at doing that kind of thing. Nothing fancy, just known misconfigurations. Tell me what looks off here. And I could use that as a defender or as an attacker, presumably. But if you're trying to do architecture for defense, like, I want to design an application that won't give up sensitive data when there's a code injection. Seems a lot harder to use LLMs for that kind of thing. So do you see LLMs as being symmetrically useful for attackers and defenders, or more useful on one side versus the other?
Yeah, it's a great question and top of mind of lots of people. I think it's a lot of apples and oranges. So what is what are LLM driven threats? The way I think of them is one thing they do is accelerate attacks in general. We've already lived in that world a whole lot. It's, the toolkits that have gotten incredibly good, Metasploits, things. So it's going to shrink those time constants yet more, and it's going to allow a broader pool to use these things. So that's going to suck. It's a higher amount of attack. I don't think of it as qualitatively different. Think of it as acceleration. What is qualitatively different? Two things, I think. One of them is social engineering, which we are not good at, at recognizing well-crafted, misleading information. They pre-LLMs, the success of spear phishing, continual success is really striking. And, it's a great problem for as a researcher. And that stuff's just gotten way better. So that's unhappy. And
Sorry, you mean the attack side has gotten way better?
Yes. And the other that I think is totally up in the air at the moment is attacks on agentic AI. And what are the interfaces? What are the assumptions? What are the wow, what a huge set of headaches. And we didn't used to have those headaches. So that one is a plus for the attackers. But on the defender side, and this is hard. From academia, I think it's hard to appreciate how important this is. And from industry, it's like right in your face. There's zillions of enterprises out there who do not have well-trained teams. They're trying to get by. And the real power for LLMs and agentic AI is helping the defender make sense of the signals. So it's not find the signal. It is, you got this pile of alerts and you've got this pile of asset information. And, how do you figure out which one to look at? And how do you figure out what's the likely path to validate it and to